I gave 6 security researchers advanced Web3 security training for 4 weeks. And now I'm bringing that training to you. I recorded over a dozen hours of lectures and walkthroughs on advanced attack concepts, low-level EVM concepts, and especially fuzzing and smart contract testing principles, and many, many other things like auditing approach, how you should approach the marketplace, and even more. I even gave them an exact walkthrough on the process that I used to get started and start selling audits myself, and I gave them some advice on how I would approach the marketplace and exactly what I would do step by step approaching the marketplace today. And now you get to watch it all. Training will be in 2 parts as the YouTube video length limit won't actually let me upload the whole thing in a single video. So we're going to do 2 parts of this advanced security training, and this is part 1. And one more thing, throughout the 4 weeks, the students completed several assignments in pairs. And so what I've done is I've included all of these assignments in the description below so that you can actually follow along and complete them as we go through this training. All right, and of course, before we get started, my name is Owen, and about 2 years ago now, I founded Guardian Audits, and ever since then, we've been auditing DeFi projects, and we've uncovered easily over 100 different critical vulnerabilities, with myself spending easily over 2,000 hours at this point auditing smart contracts. And my goal with all of these videos and everything that I put out is to distill down everything I've learned from these 2,000 plus hours spent and give it to you so that you can ultimately become a much better security auditor, blockchain engineer, whatever it is that you're looking to be in a fraction of the time. Now, of course, with this training right here on YouTube, I won't be right there with you to answer your questions or audit with you or review your code or give you feedback on findings or anything like that. So with this training being released, I'm announcing Gateway. Gateway is a boot camp that takes newer entry-level security researchers and turns them into advanced auditors. Now, I'm still absolutely committed to putting out all of the free content that you need, and I fundamentally believe that content and knowledge itself should not be gatekept. But of course, if you want to speed up the process of becoming a skilled security researcher and you want to get hands-on training from lead auditors, then of course you can go down below and get our guide on becoming a senior auditor in 6 months and apply to join the Gateway program down below. All right, now I sincerely cannot wait for you to get to this massive Web3 security course here that we have waiting for you. So without further ado, let's dive into part 1 of this massive Web3 security course. All right, amazing. We are literally just a few minutes away from getting started here. I honestly cannot wait for you to start digging in and getting started with part 1 of this course. And right in front of us here, we have just a handful of the topics and ideas and things that we're going to cover in depth throughout this course. We've got everything you can think of here, from Ethereum cryptography, formal verification, front-running attacks, reentrancy, EVM stuff, upgrade patterns and upgrade vulnerabilities, and DOS attacks and Oracle manipulation, and how to draft findings perfectly, how to do code walks, some select findings that would be good to understand and apply in the future. And the list goes on and on and on and on and on. And these aren't even everything that gets covered in depth here. But before we go over the course curriculum and the structure of how we're going to follow each section and what that's all going to look like, let's go ahead and have a look at the course Notion here. So we've got a Notion set up for this free Web3 security course, and this has everything you need to know about the course. We've got the course structure laid out here, roadmap, collaboration, missions, side quests, some notes to take away from the course, code walk guide, and of course a breakdown of the course where we'll have the timestamps and links so you can go to each of these chapters here. So the overall structure of this course is 20 plus hours of Web3 security training. with 3 missions. So 2 missions being released with part 1. These are basically projects that you're going to dig into and hopefully partner up with somebody else if you can manage it and work on this project. And this is going to help you understand some DeFi concepts at a really deep level. And then of course we've got 2 side quests. So 1 side quest released in part 1 here. And then we have a Discord to collaborate to go along with this course. So if you're not already, you should definitely join lab.guardianaudits.com and go ahead and get in the Discord here. We've got a gateway course directory here with a course chat and a chat to pair up if you want to find a partner to go through this course with, which I would highly, highly recommend, and we'll see why in just a second. And in here you can basically ask questions related to the course. Hopefully other folks who are a little bit ahead of you are able to answer those, or hopefully ideally pair up with other folks, and there's a VC here as well if that is useful. Now we've got the roadmap here, which we're going to go over in just a second. But now let's look at the collaboration, right? Why do we want to have partners for this course, right? Well, first of all, it's in general just a good idea to have a partner for anything, just so you can have somebody to ask questions as they come up, somebody to help overcome these obstacles, and especially for the missions. So we're going to have a look at the missions in just a second, but these in particular are going to be basically some in-depth projects where you're actually going to be building your own code base, because I think this is especially important when you're looking to become a Web3 security researcher, that you actually have an in-depth understanding of what it's like to be on the other side and actually be creating one of these DeFi protocols. That way you're going to get a much deeper understanding of some common DeFi patterns, and then of course the common issues that developers deal with, like decimals and things like this. So to tackle these bigger projects, you're going to certainly want to have a partner to bounce ideas off of and work through the obstacles that come up. So 100%, if you can manage to get a partner to go through this with, then definitely go ahead and do it. So what you're going to want to do is come into this pair up channel and go ahead and just post something like, what is your time zone? What is maybe what's the timeline that you're looking to complete? So I might say like time zone is EST, timeline, maybe I'm looking to do this in 3 weeks or something like this, however long you're looking to complete the course in. And then I would post that and try to find somebody that is going to be able to pair up with you, and you guys can sync on some of these missions here. And then also for mission number 3, you're going to want to connect in the Discord here, find another team or another individual student who has completed the prior missions for mission 3s. Now we're not going to reveal exactly what mission number 3 is just yet, but just letting you know that collaboration is going to be extremely useful in this course. And then finally, if you want to do a code walk with some other students, first of all, we'll learn more about what a code walk actually is, and you'll see that in practice in this course. But we've got the code walk guide laid out here, and you'll learn more about what a code walk is later on. And if you want to do a code walk with other students, then that can happen in the Discord community here. So with that out of the way, let's have a look at what are these missions, right? So the first mission here has to do with Perpetuals, and we'll get a full introduction. We have a full session introducing this Perpetuals mission, and then just introducing the concept of Perpetuals in general, because at this point you might not even know what are Perpetuals contracts, how do they work. That's a completely normal thing to not know, and we're going to introduce that in this course. So we've got, of course, a motivation section for this mission, and then a goal and deliverables section, which says, exactly, here's everything that we're delivering and submitting for this mission. And then we've got details, and we go in depth on every piece of the deliverables and like everything that you're supposed to create. So There will be a whole session that overviews particularly mission 1 and mission 2. And mission 2 will have the same sort of outlay there. And you're definitely going to want to have a partner to consult for mission 1 and 2 there. So other missions, as part 2 gets released, will get put under missions here as well. I don't know why I'm making a comment there. Now, side quests. Right now with part 1, we've got one side quest having to do with Yul and memory. So with every side quest, you're going to have a goal section, some instructions, and then questions. So essentially, all you'll do in a side quest is you'll read over the instructions and then answer the related questions. And working through the questions will be really helpful to actually go ahead and apply the stuff that we're learning. And then we'll have a session included in the course that we'll see in just a moment, where we actually go over all the questions and basically work through all of the questions here live. So definitely complete the questions before we get to that session. All right, fantastic. And then, of course, we've got a code walk guide. You can read over this when we get to the concept of code walks in the course. And then we'll have a complete list of all the timestamps to each session linked down here below. And this is just for part 1. In fact, the table for part 2 is going to be even longer. So without further ado, let's go back. We can get rid of these now. And we will have a look at part 1 here. So you can see we've got part 1 and part 2 laid out next to each other, and part 2 is actually even longer than part 1. But we're just going to get started off with some security basics. So we're going to go first from a high level. We're going to look at principles of smart contract design. We're going to go over to external call attack vectors, as this is really a fundamental area of security as any kind of external calls. And then, of course, building on that, of course, any external calls are particularly prone to reentrancy, and that's a bit of a more complex type of exploit for external calls. So we've got an entire session, an entire guide on reentrancy. And then we're going to go to the principles of smart contract testing. We're going to learn what does it look like to test smart contracts really thoroughly and actually have a really strong standard for verifying the behavior of smart contracts and verifying that, yes, they do indeed do what we want them to do, and they can't be used to do things that we don't want to do. We're going to learn about invariance and verifying those invariants with tools like Echidna and Foundry fuzzing and things like this, all covered in that session there. And then after we've gone through these security basics and we understand how to design good, maintainable, safe smart contract systems that have as little attack surface as possible, all of this stuff is important to understand as a security researcher, because when things are not that way, then you understand exactly where to dig into the code and exactly where bugs probably lie. After that, we're going to go towards an advanced DeFi concept of perpetuals, right? So this is relating to mission number 1 here. What we're going to do is we're going to fully break down and introduce this idea of perpetuals, and we're going to continue to build on this theme of perpetuals throughout the entire course, right? So this is just the introduction to perpetuals, and we're going to continue to have missions. Mission number 2 and mission number 3 are going to be related to perpetuals in some way. And so throughout this entire course, you're going to go very deep on this idea of perpetuals, and you're going to have a very strong understanding and familiarity with perpetuals protocols. And then from there, you can use that particular niche DeFi knowledge, and that applies to other DeFi protocols in the sense of liquidations, in the sense of collateral ratios, and et cetera, et cetera. So then we're going to move on to some front-running vectors. We're going to understand what do front-running attacks look like, how do front-running attacks work. Then we're going to have a look at, okay, building on top of front-running attacks, what is a sandwich attack? How does a sandwich attack work? And then we're going to have a look at some audit training here, where we're going to actually go ahead and use some interesting methods to actually get audit skills and actually see more of an approach of what auditing looks like live. So we've got a live audit in this session where I walk through with 6 other security researchers, and we're auditing live, we're following my process, and they get to ask questions as we go through. And then we're going to do student code walks, and in this session you're going to learn what a code walk is and how it can be used to really improve your reviewing abilities. And of course we're going to kick this section off with a guest lecture from Patrick Collins, which is going to be great. And then after that, we're going to have our second session diving deeper into Perpetuals, and this is going to give us mission number 2. And then finally, we're going to wrap things up with some EVM mastery. So we're going to start off with the EVM intro, we're going to do a memory guide, and then before we reach this third session here, the Yul Masterclass, I recommend that you finish side quest 1. So you watch these first 2 sessions, you're going to have everything you need to know to complete side quest number 1. And then in this masterclass here, we're going to basically just go over the answers to side quest 1. And we're going to work through all of those problems together. And then finally, we're going to understand everything about call data, and that is going to complete our EVM mastery section of the course there. And that will be everything for part 1. So I cannot wait to get started. I hope that you are excited and you are ready to blast through this thing. Definitely don't try to take it all in one day or even maybe in one weekend. Try to do, maybe a section a day or a section a week or whatever works for your timeline, and take it chunk by chunk. But beyond that, we're ready to dive into security basics. So let's get started with the principles of smart contract design. Okay, cool. So we're going to get things kicked off here. Let's see, I've got a ton of stuff open. So first of all, I've got my notes for this talk here, and I've put this under the sessions category. So this is, first of all, for me to make sure I stay on track and cover all the things I want to cover. But this is also for you guys to have to refer back to, and if this can be useful for you. So we're going to have that. You guys have access to that already, and we're just going to get rolling. So there are a few major things that I see are pretty core to just what does a well-designed, actually secure smart contract look like? What are the commonalities? What are things that you want to avoid? What are things that you want to try to do? And how do we sort of make a framework for what a well-designed smart contract looks like? But a list of key features and an approach that you want to take when you're designing smart contract systems. So a lot of this stuff might be obvious. You might already be well familiar with these things, but we're just going to go and list all of them, and we're going to talk about each. We're going to look at some examples of specific instances where this is an example of why I think this is bad, and some pitfalls that you can fall into. And then we can basically take this and apply this and say, hey, when you see this in the wild, it's probably something to dig into there. So let's see, the first thing here is going to be the most general, which is really just an ideology of let's just have less code, right? Let's keep this as simple as possible. The less code that you have, the less bugs are able to come up, right? So if I can write a smart contract and it can only have 100 lines, then let's do that. Let's not write a smart contract that has 1,000 lines. In fact, I think there was a study done, and I don't remember what it was called, or I can't cite it, so this is basically hearsay, but I remember reading a study where they basically analyzed code written by developers. Now, given this wasn't smart contract code, this was, like JavaScript code or something like this, and they found that for every 1,000 lines that developers wrote, on average, they wrote something like 17 bugs or something like this, which is pretty wild if you think about if I was going to do a smart contract audit on a 1,000-line contract, you're going to get 17, and a bug is something significant, so 17 critical or high vulnerabilities. That's pretty excessive. So especially when it comes to smart contracts, we just want to have less code, because in general, bugs and code have the following relation. If here we have bugs and here we have code, it is a parabolic relation. So if maybe, this is like the 400 line mark, and then this is like the 1,000 line mark, and this is like the 2,000 line mark, really what we've seen is the more lines of code that you add, the more exponentially more bugs you're going to have. And we've seen this with the GMX v2 code base, which was over 10,000 lines of solidity code, and it was, well designed. Like the GMX developers are like some of the best developers in the industry, but even with that, if you write 10,000 lines of code, you're still going to have over 50 critical vulnerabilities and over 30 high vulnerabilities. And so even with great developers, we ended up uncovering, I would say, probably 80 plus different critical and high vulnerabilities over all of the engagements that we did of that code base. And so it goes to show that if we're looking to just build the most secure contracts, really take the time and invest the time up front to be over here, because you don't want to be over here, and you certainly don't want to be, if you can help it, over here. And so, okay, how do you actually design contracts that have less code? Personally, I think the best way to approach this is to be extremely picky about your storage variables. So in smart contracts, storage variables are, kind of like the data model that you're working off of. And if you can simplify this as, make it so that there's no extra cruft on them at all, you're gonna lay a really solid groundwork to where you're not gonna be writing superfluous code in your functions to update superfluous storage variables. It's gonna set you up for success. So one example I want to look at where you can notice that this is not done, and then dig into that and see that, oh yeah, there's probably going to be a bug there. Some code bases pulled up here. So I'll just give a quick overview of what's happening here, and then we'll look at why this is an example of not having the most whittled down storage variables, and we'll see why that can be a bad thing. So here they've got a function for modify position, and what it's doing is basically taking an order. So an order is like a request to increase your position, a request to decrease your position, a request to create a position, things like this. And this is for a Perpetuals exchange. So we're going to ignore all of the implementation here, and we're just going to look at two fundamental things. They have a order to position ID mapping, and they also have just an order struct. So the order struct, if we pull it up here, and I'm going to put this on the right hand side, we can see the order struct has all these things. It's got an order ID, it's got a market ID, user address, order type, is long, is limit order, it's got all these things. But, and orders are stored in a mapping from order ID to order. Now we've got this extra mapping that goes from order ID to position ID. What they should have done here is they should just put a position ID on this order. So this extra mapping here is completely superfluous. You've introduced a storage variable that didn't need to exist, right? So that's fine. Maybe it's, just extra. It's something that's just inefficient. I would argue that this is much, much worse than being simply inefficient. What you've done is you've introduced a massive opportunity for a critical bug. So instead of just having, these pending orders mapped from order ID to order, that's the only mapping you need, and you have the position ID information on the order itself. Now you've added this second piece of state that also presumably tracks exactly the same thing. Now there's just an opportunity for these things to get out of line. So for example, if maybe this was pointing to an outdated order that was, this had an old position ID and that was not what this order was intended for, or if somehow this order to position ID mapping got, maybe corrupted by somebody else was able to modify the position with the same order ID or something like this. You've just introduced many, many different possibilities where the value that's in this mapping might not match up with the order that's actually in this mapping. So removing these superfluous, like extra storage variables, like if we do that, now we can just literally go off of the order mappings for pending orders. And that simplifies the code a lot then. You'll see if they do remove that mapping, now they're going to be able to remove all the logic that goes and accesses that specific mapping and handles that, handles setting that, handles clearing that. You can remove all that logic. So just from removing that one storage variable, they're going to be able to remove, maybe like 50, 60 lines of code, which might not be a ton, but if you have multiple storage variables like that, it really adds up. And they would have probably seen that reflected in their audit costs, to be honest, because most audit firms are, what they do is they just charge by solidity lines of code. And, 50, 60 lines can easily translate to like $1,000. So that's number one, just a good idea to have as little code as possible so you don't get quoted super high, but also just have less surface area so that these little mismatches cannot occur. So that's our first sort of principle, is to have less code, and a way that you can do this is to lay a really good solid groundwork by just being very picky about the storage variables you have. We don't want to have any extra cruft. And then beyond even just storage variables, one thing we want to think about is how much of this logic can be done off-chain. How much of this logic is just, it's not necessary to happen on-chain. We should remove all of the logic that isn't absolutely necessary to go in a smart contract and let the front end handle that, or let the keeper handle that if it's just some conversion or something like this. So we'll look at an example of what something like that might look like. So this is in a concentrated liquidity AMM protocol. We don't need to understand anything about what that actually is or how this works. The only thing we'll look at here is that we're taking this params.amount, so an amount that a user wants to remove from their position, and then we're converting it and reassigning it. And the conversion here is to go from a percentage of a position's liquidity amount to an actual liquidity amount. We don't need to worry about what those numbers are. Really what's happening here is we're just doing an unnecessary conversion on-chain. This should be done by the front end. This should be done by a keeper. But instead, we've introduced this complexity and these few extra lines of code that, yes, at the base level, cost extra gas when you're using this transaction, but I would argue much worse than that, you've introduced complexity into your code. And now there's an opportunity that, oh, well, is there somewhere where you didn't convert the params.amount? Is there somewhere where there's a bug inside of this convert function? Is there an edge case where a user can pass a liquidity percentage above 100%, and can that cause a bug? There's all this superfluous logic that is now happening at the smart contract level that does not need to happen here. So this again, if the team removed this conversion logic, they could also probably clear up 50, 60 lines of solidity code and reduce just these unnecessary points of failure, right? So that's another example of where we just want to cut out all the cruft. We just want to do the absolute basics of what needs to be done without any extra conversion or anything like this, and do it as succinctly as possible with as few storage variables as appropriate. So honestly, this might be the single most important sort of fundamental approach to designing really good, clean smart contracts that are going to be resistant to exploits. But that does take time and brainstorming to figure out, okay, what's the best approach to do this? How can we really minimize the implementation? And like I said, I briefly did the mission 1 assignment over the weekend, and I do believe that it can be done in around 200 SLOC or something like this. So that just goes to show that really there doesn't have to be a lot of Solidity code to achieve, a lot of functionality. So really, as you're going through this exercise, I'd encourage you to try to spend that extra time to think about how can we make this simpler? How can we make this easier without, ignoring some of the things that need to be addressed and just oversimplifying, but how can we make this as simple as appropriate? So that's the first main point, but that's kind of amorphous, of course. So let's go into something a little bit more actual, implementation wise. So first of all, of course, for loops, right? I think this is probably the number one thing that I see that less experienced Web3 developers do is they use for loops and they use them a little too liberally. And this pretty much always ends up in some sort of DOS attack or just a design that doesn't really make sense in the context of the EVM. So I'm pretty sure that you guys going through the Johnny Time course have already become familiar with why this is not a good idea. But for example, like in our Perpetuals context, if I wanted to, let's say, calculate the total open interest of a market, I cannot loop through every position and then just add up the size of that position. And I can't do that because, well, that would basically limit the protocol to only have enough positions that can fit within the block gas limit in that loop. Otherwise, the whole protocol is just DOS'd. So as much as you possibly can, we want to avoid for loops, while loops, things like this. Anything that has an indeterminate amount of gas or an amount of gas expenditure that scales O of n, or even anything that's really not constant time logarithmic like algorithm, then you don't want to have it, right? Ideally, you don't want to have it. Now, of course, there are times where maybe you have a swap in your protocol. Well, a swap and a swap path, you probably need a loop to loop over the swap path. That's fine. I mean, just be sure to limit the swap path so that people can only do as many swaps as makes sense for the block gas limit. So for loops, they do have a time and a place. They are necessary for certain things, but often they're a lot rarer than you think. And oftentimes when you think there's a for loop necessary, there can be some other approach. Like for example, what we talked about yesterday with tracking the market total open interest and the market total open interest in tokens. And this way, I immediately already know what the net open interest is, and then I can compute based on that the net P&L of the AMM or the protocol. And so often there will be a solution like this, which comes from tracking the aggregate and then deriving whatever value you want to get from that aggregate value instead of looping over every individual position, every individual user, or anything like this. So that's just a long way to say that you should avoid for loops at all costs. And I will say that I didn't use a for loop for this mission 1, and I also don't think that you'll need any for mission 2. Okay, cool. Now let's talk a little bit more about some security specific stuff. So it is my belief that we should be very explicit about what we want to allow users to do in an application. They should not be allowed to pass in inputs and make actions that we don't expect. So an example of this is, what if a user wants to make an order on a Perpetuals exchange, but they want to create a position with 0 size, and they also want to create a position with 0 collateral. Well, that position doesn't really make sense to exist, right? If I have a position that has 0 size, first of all, that alone seems like it doesn't really make sense, because that basically means that you've borrowed nothing, you don't really have an open position. But then also with 0 collateral, that also seems like, well, there's nothing backing your position, even if you did have a size or something like this. It's my belief that we should specifically disallow that and have, perhaps excess validation, that any unexpected inputs, any unexpected paths are just explicitly straight up cut off at the beginning of function execution. And so why is this actually a really big deal? So let's envision function execution of, if I want to create a position like this. So if I call the function, there's a certain range of parameters that I can use, and there's a certain number of edge cases. Now, some of these might be expected, some of them might be stuff that it's like, oh, well, if you provide that, I don't really know why you did provide that. That's just not really a valid thing. So if we enumerate all of these, and we have just all of these parallel different paths that a function can follow, this is hard to verify. So in terms of, just an auditing perspective or a manual analysis perspective, or even a formal verification perspective, this will take more compute to actually go and verify every one of these paths. And especially with formal verification, having this many paths might literally make formal verification, at the very least, a lot more time intensive, or in some cases impossible. A lot of times in formal verification you have to manually come in and cross off these paths. So my belief is that if, let's say, I do something invalid, 0, 0, 0 size, 0 collateral, let's just cut that off immediately, right? Because if we don't cut it off, if we allow that, it might actually go through, and it might do something unexpected. So right here, maybe what you'll end up with is, I don't know, you might end up changing the P&L of the pool by 1 way due to some rounding thing. And then if I can do that a ton, if I can spam that, maybe it can have a meaningful impact. Maybe it can even end up DOSing the pool by, having so much P&L that the P&L is greater than the deposited amount, and then when you try to subtract that, it causes some sort of underflow revert or something like this. Anything could happen. We don't know what could happen, but we just want to cut it off early on and completely not even allow that ability for something bad to happen down here. Because if it's unexpected in, chances are you're going to get something unexpected out. So what I like to think of when I'm auditing is, okay, looking at just this function, what are all of the potentially unexpected edge cases that are actually allowed here? And really what the developer would have benefited from is doing the exercise themselves and then just cutting off all of those things. Because that's how we get a lot of findings, is we say what unexpected things are actually allowed, and then what do those things do. So if you cut out all of the unexpected paths, and there's now only the valid path of like, hey, I want to open a size of 10, and I want to give you $5 of collateral, that's good. That's allowed. Expected in, expected out. So that's one thing that is honestly huge and honestly really overlooked, at least from my experience with contracts that we've audited, is to limit the expected inputs. And of course, you have like zero address checks and things like this that people commonly do, and those are great. That's just a small part of this. It should be also protocol specific, right? So if I don't expect you to provide this, or I don't expect you to provide a swap path that has 2 of the same markets in it twice, that seems unexpected, that seems malicious, you should disallow that. Okay, so after just these first three, do you guys have any questions thus far? Anything you guys want to talk about on these?
Yeah, I have a small wondering, I guess. So there are certain required statements that you always see, required that the address is not zero and stuff like that. But I've also seen contracts that kind of go overboard with that. Like they have a lot of required statements, which I guess can make the code like really heavy and gas expensive. So where kind of do you draw the line of saying like, hey, like, okay, this is not a smart contract issue. This is a more of a maybe UX issue. Like, how do you think when it comes to that? I guess.
Yeah, it's a great question. So there's definitely a trade-off in gas optimization and pure security. So the pure security point of view is let's put non-reentrant on every single function and let's have all of the require statements for every single function. I tend to lean more towards that side of things because I've seen all the vulnerabilities, and this is what I do. I do security. So I tend to lean personally towards the side of have all the require statements that make sense. Maybe don't like copy and paste them for every function. Maybe put them in a modifier so that the actual slok isn't something huge, and you can get your bytecode down if that's a concern. And then sure, throw a non-reentrant modifier in every function as well, just to be safe rather than sorry. And we will talk about reentrancy here in a little bit. But of course, if you are deploying on mainnet, then it is a consideration, and maybe you do only want to have the require statements that absolutely make sense. I think at that point, it's more of a trade-off that the protocol itself has to make, and then you just have to go and you have to spend that extra time and that extra due diligence to manually verify that each of these, instead of if you were to remove a require statement for this, for example, well, you had better have auditors specifically check this edge case and make sure that it doesn't yield something down here, right? So that's my take on that. But does that answer your question?
Yeah, absolutely. I guess like one of that was one of the thoughts. I recently competed in like a code hawks competition, and that kind of became a discussion topic where people kind of said that yeah, sure, like, but some of them are user input, and we shouldn't be over concerned about user input when auditing smart contracts, because that's front end, that's user experience. But on the other hand, of course, like maybe we should be concerned about security. So kind of just a thought out there, like how to think about it. But yeah, definitely answered my question.
Yeah, 100%. Every protocol developer says that you shouldn't worry about user inputs like this until a user input like this causes a critical bug. So yeah, definitely if it's, verifiably like, okay, it's fine if the user puts 0, then that's good. Then that's fine. But always there is that case of, you want to block this out because it could cause something later on. And that might not even look like 0. It could look like something that I think specifically that we end up recommending to most protocols is if it's like one way. I think this actually gets a lot of folks is you want to prevent these really small inputs. Now, we can look at a finding that has this as like a core root cause if we have time. But if I provide one way, almost always that's going to be unexpected. And what ends up happening is usually what you're going to do is you're going to abuse this to manipulate the rounding down quote unquote feature of division in solidity or cause something else to happen. But usually it's going to be, to take advantage of truncation. So, I mean, of course, if you're familiar with the inflation attack, that is exactly what that does. Anytime one way is provided, or maybe even, you know, a denial of service attack if you are using a for loop, which is another no-no, then just open a bunch of positions that have one way of size, right? And then that's how you do S. But this is always a great one that we recommend, is to have some minimum. So have like a minimum size. So for example, we got GMX in this way where we were able to create a position that had a number of way, and it was a slightly more advanced attack, but the root cause was that we were able to create a position with a really small size that ended up rounding down to 0. And then through that, you're able to, you know, essentially manipulate the system in, you know, a combination of steps. But the root cause was that they didn't have any minimum size checks. So this is one such example of where we should just limit this entirely, so that there is no potential for manipulation based on this. And then that's what they added. They added a minimum size for the positions, and it completely wiped out that entire class of manipulations where you're providing just really small values that are like, you're not actually trying to open a real position with this because this is a trivial amount. You're trying to manipulate the exchange. We're just not going to let you do that. So that's like perhaps a better example of, you know, something like this. But yeah, that's 100% a good thing to call out. Okay, let's see. So before we move on, anything else on, you know, less code or, you know, for loops or limited inputs?
I have one question. So is it custom errors? Would that be like helpful with all the different required statements if you did need, or if you do have to use so many?
Yeah, absolutely. 100%. Yeah, that's a gas optimization that honestly should be used pretty much always instead of require statements. But yeah, that will definitely help, especially if you're going on mainnet, which honestly most applications that we audit now are not. Most applications from our perspective are going on L2s. But yeah, okay. If there's nothing else, then we'll move on and we'll have more time to ask questions and things like that. So let's see. Yeah, so the next thing is going to be it's somewhat related, but a little bit different than limiting expected inputs, is we need to make sure to handle all cases. And this might seem obvious, but it's actually really hard to do when you're just creating a protocol, and from your point of view, you think, oh yeah, this is what the user is going to do, this is what's going to happen, these are the situations that are going to arise. But there are a distinct set of cases that maybe you didn't think of initially, and that, you know, they're not necessarily something that you can just limit with require statements or validations. These are things that fundamentally are going to arise depending on market conditions, depending on, you know, if a stablecoin depegs or something like this. These are things that are going to come up. So often what this looks like is like a stablecoin depeg. So if you ever see a protocol basically assume that USDC is always $1, well, you have like a high finding right there. Another thing that's like more specific to perpetual protocols is an insolvent liquidation. I think in every perpetual protocol that I've reviewed, we always get them with something surrounding insolvent liquidation. And even the options protocol that we had to look at, they have issues with insolvent liquidation. So what is an insolvent liquidation, and why do you need to handle it? So if we look at what we were going over a little bit yesterday, we've got these cases of people, you know, making money, losing money, and then getting liquidated. And we'll notice they're $1,000 in collateral, minus $500 in losses, minus liquidation fee, which we're just assuming to be 0. They get back $500. Now what happens in the case where somebody has $1,000 of collateral and they have $1,100 of losses, right? Now as a protocol builder, you might not think about it like that. You'd be like, well, we have a keeper to liquidate them far before they ever get to that point, right? And that's what should happen. It should always happen, ideally, but things come up. Prices crash really quickly depending on the token that's being traded. If there's like a liquidation cascade, keepers sometimes go down. There could be reorgs, there can be block stuffing attacks, there can be, you know, DOS, like front-running style attacks to delay a keeper's transaction. All of these things can come up, and it is possible with, you know, arguably a non-negligible % chance that the keeper doesn't function perfectly. And so from a smart contract perspective, that keeper functionality is not encoded in the smart contract. So the smart contract itself needs to handle the cases where the keeper messes up. And this is going to limit the losses and limit the incentives to make such a scenario arise. So in this scenario, if you don't specifically handle this and account for this, what does $1,000 minus $1,100 equals? Well, in solidity, it equals an underflow panic revert. So that's not good for the protocol, right? So what this will mean is you basically won't be able to liquidate a position if it ends up losing more than it had in collateral. And this is especially dangerous if I have one such protocol where I'm allowing you to actually put down $0 of actual collateral and cover this by your quote-unquote profit that is unrealized. Because if the price of that token changes really drastically, well, if you go even $1 in loss, you get underflow panic revert. And these are the kind of edge cases that always need to be handled, right? They need to be thought about, they need to be handled in a specific way. And if you don't handle them, then something that maybe turns from, oh, well, the liquidity providers just don't get remunerated for that $100. So instead of it being $1,000 minus $1,100 equals negative $100, which is like, okay, yeah, granted, they did lose $100. That's bad. But that compared to not being able to liquidate that position in general, that's a lot better. So we want to make sure that this case is handled at all times. And a lot of, there's often complexity around that, where you also have to have logic to manipulate the liquidation fee if it is an insolvent case. That was another issue that we've seen in the past. But basically handling all of these cases that are not necessarily seen in the smart contract if you just look at the smart contract code, but they are dependent on the outside environment. So let's see. Okay, here's a classic one. So let's talk about parallel data structures. Okay, so this one is, somewhat related to, it's more of a specific case of having less code and being really smart about your storage variable layout, your storage variable choices. So parallel data structures is having two pieces of storage, or even, it could be memory on a function level, just two pieces of state that are tracking the same thing. So, for example, if I have a mapping, so let's say I've got a mapping from address to position, and this is, positions mapping. And then I've also got a positions list here. And these are supposed to track, this is supposed to track all the open positions on a Perpetuals protocol, this is supposed to track, you know, the same thing, only now you can pass in the user's address and they can get the corresponding position. So two ways to access the same data, except these are both storing in different slots in the EVM. So fundamentally, we are duplicating, ideally, if everything works correctly, you are exactly duplicating this data from, you know, being able to be accessed in a mapping in this way and being able to be accessed and iterated over in the list this way. Now the huge issue with this, as you can probably already tell, is that, well, what happens if position A is in the list, but it's not in the mapping? Or what if I update position A and the updated version is in the list, but the updated version is not on the mapping? You have an outdated version of the mapping. And this one really hits home for me because I made this mistake early on when I was building our first DeFi protocol. So actually, I'm going to pull up, I got some, okay, cool. So we've got Phantom Scan pulled up here. Back when the Phantom blockchain was larger than it was and a lot more popular. This is my first DeFi protocol. It's called Minimum Finance, and it was designed to basically optimize rebase tokens, which is in hindsight a terrible idea. But we'll ignore all of the implementation details of this contract, and we'll just have a look at the key error that actually resulted in a critical bug that we had to sort of, in a panic, figure out what the root cause is, and then go and address it, and actually we were able to save our users funds. But so let's have a look. So we committed this exact issue in a way. So what we have here is a mapping. So there's some complex like business logic that has to happen here because of the way that bonding works with rebase token protocols. We don't have to know anything about that to understand this bug. But to handle that, we have this claim object. And we have a mapping from the user to the claim. But we also have a list of claimers so that we can know who was, you know, pending their claim of reserves to withdraw from the vault system. Now you'll notice on this claim struct we have an index. The index refers to the index that somebody is at. Now if we go and we have a look at what happens in the function _claim when somebody's actually claiming, this is how we remove somebody from the claimers array. This is kind of like the, you know, accepted way to, this is the most efficient way in terms of the EVM to remove somebody from a list. It's to take the person from the last index in the list and to move them to wherever the person that you are removing is at. So you overwrite that person and then you just remove the last person in the list. That person was moved to this index. So if I was to draw that out, just to make that a little bit more clear, if we have A, B, C, D, and let's say I want to remove this guy from the list, what I do is I take the list and I do this, A, D, so I take the last guy, put him here, and then I just pop this off. So we go to A, D, C. So that's what we're doing. That's like presumably the most efficient way to remove somebody from a list in Solidity. The key issue with this, and the reason why parallel data structures were not a good design decision for us, is because we neglected to update the index of this last person in the claim struct. So if we go back to the beginning, this claim struct, the index for D, for this person D, right, their index is 0, 1, 2, 3. But we moved them. We moved them, and now their index is 1. But we didn't update that. And that ultimately ended up in funds being literally locked in the protocol. And so that's a critical bug that got past an audit. It got past all of our tests inexplicably, somehow, because we didn't test with enough users and withdrawing in the right order to be able to catch that. And it made it into production, and it made it into a vault with, real TVL deposited in it. And so this is always something that whenever I see it in a smart contract, it got us. And so I always have red alarms going off in my head when I see other people doing it. And oftentimes it does lead to issues.
Sorry, Owen, can I ask a question?
Yeah, absolutely.
I know it's in hindsight, so it's easy to discuss it, but to me it seems like it's almost always a bad idea to have parallel structures, regardless if it's Web 2 or Web 3. It's very bug prone. Would you share why you took this decision in the first hand, or is it ever a good practice? I mean, would you ever consider it?
Yeah,
like,
I think
what is the benefit of instead of just enriching one of the data structures?
Yeah, I think no, you're 100% right. It is almost always a bad practice, and it should be avoided. The reason why we needed this list of claimers is if we needed to upgrade a vault, we wanted to have a way to be able to iterate over everybody who had stuff in this mapping and force out their money so that we could upgrade the vault to the next thing. Now, this is before I knew, obviously, or was, familiar and comfortable with a delegate call, proxy upgrade pattern or something like this. So this is a classic example of just a novice Solidity developer, right? This is just something that, it doesn't need to happen this way. This is easily solved by having a proxy where instead of having to, needing to push out funds of this current contract, just, proxy upgrading to the next implementation. So yes, it could, in the vast majority of cases, unless there's really something niche going on, it should almost always be avoided. And so that's made clear by this example. Yeah, and I'll also say they have obviously there's the enumerable mapping from OpenZeppelin, which if you need to iterate over the things in a mapping, that can be done. So also an enumerable mapping should have just been used here. So there's many other ways to get around things like this, right, without using parallel data structures. So yeah, to summarize, the best way to handle this stuff is to consider, if necessary, if it has to do with the mapping in a list, which is often, how I see it being done, funny enough, can you use an enumerable set, an enumerable mapping, things like this to replace that. And so that would be the appropriate approach. Yeah, almost never it's a good idea to have parallel data structures. So let's see the next thing. Yeah, let's talk about external calls, because I think these are, beyond just design mistakes. External calls are the most impactful, the most dangerous part of any smart contract. This is probably, I think there was a study that found that the most common exploits were Oracle manipulation and external calls, and they were basically neck and neck. And so external calls have a number of ways that they can lead to terrible, nasty things happening. I'm sure you guys are already well aware, but we'll just talk briefly on the things that we want to really consider when we do decide to implement an external call in our system, and how we can do that as safely as possible. So of course there's reentrancy. There's also denial of service. We have to think about return values if we're expecting return values from this external call. And gas. We do have to think about gas. So in terms of reentrancy, of course we know that you want to use check effects interactions, right? You want to have your effects, your state updates occur before this thing, before you have your actual external calls, your interactions with the outside world. Of course, we know that, and then of course we also want to put, when applicable, non-reentrant. When, for example, maybe I need to make an external call because I rely on a return value, and based on that return value I update a piece of state, I have an effect. Maybe, depending on your design, which maybe you can redesign it, maybe you do need non-reentrant, and that's actually literally required. But also it's often just helpful to put non-reentrant, again, leaning more towards that security side, to put non-reentrant on every function that changes state, but it's a better safe than sorry thing. Now, let's talk quickly about where both of these, or at least non-reentrant, fails. Oftentimes I see functions that have non-reentrant in them, and I can still use a reentrancy vulnerability to get them to do something bad. How is that? How am I able to do that? It's because there's multiple contracts in the system. So, multiple contract reentrancy, you'll remember that non-reentrant only applies to the storage of a single smart contract. And so it just protects against me reentering from one function in a smart contract into any other arbitrary function in that same smart contract. But if there's multiple smart contracts, then sure, if you update the reentrant state in contract A, then okay, cool, I can't enter into contract A again in the same transaction. But if there's a contract B that's a part of the same system, well, I can enter here, and then I can choose to, in the same transaction, enter B, and if B reads some state from here and then does some stuff after that, well, that's a reentrancy. I've just reentered in the same system. And what if these are different systems? Well, we actually know what this exact situation is, and that's called read-only reentrancy. So for example, this is somebody calling a function on curve and changing the balance of a curve pool. Now, you can't re-enter into the curve contract itself. Now that they've changed the price of the curve pool, but there are other systems that read the price of the curve pool from the view function. And so if I've changed the price of the curve pool, and then I'm using, in that same transaction, talking to XYZ smart contract that relies on that price that I've manipulated to go up or down within this transaction, now all of a sudden we've got read-only reentrancy. So that is the reentrancy risk. And whenever you make an external call, you need to look at not only the functions you've exposed in that single smart contract, you need to look at the system as a whole. You need to even look at your view functions and consider, okay, if there were systems and people integrating on top of this, like they want to build on top of my software, which is, a big proponent for DeFi's composability, how could they be exploited? We need to think about that as well. And a lot of protocols don't. And that's why in most of our reports lately, we have read-only reentrancy risk findings. Okay, then the next thing we need to consider is, of course, DOS attacks. So if I make an external call, can it just fail, right? And then I can shut down, a potentially really important feature of the protocol. Is there a callback on a liquidation where a user can choose to just revert in their callback contract and make the liquidation fail? Or is there a liquidation that sends Ether, so a native token, to an address? And then if that address is a smart contract that doesn't accept Ether, then it fails. So are there ways to DOS whenever we're interacting with the outside world? That's a second consideration, something that I ask myself when I see an external call. The next thing is return values. When I see any sort of return values getting parsed in. So obviously those just need to be, checked for all possible values. Like this is more context specific to the system. So there's that, but there's also, you know, is it some unexpected bytes? So when I return something to you, I can technically return any arbitrary bytes. I don't have to give you exactly what you're expecting. So for example, I think, yeah, what we can have a look at is, let's have a look at the GMX code base. Here's a really interesting exploit. So if we go to project files and we go to callback, now what they used to do here in this callback utils function is they used to catch bytes error data. They used to do this, bytes memory error data, and they used to basically load this in, and then what they would do is they would try to parse the error into, you know, whatever, a string, into a string to get the revert reason, right? And then emit that revert reason. But this can be arbitrary bytes. Now if I try to parse that as a string, there's a number of sneaky, dirty things that an arbitrary callback contract can do to make this error data cause a revert when you're parsing that. And so that's another thing that we need to think of. We need to think of, we can't assume, if we're going to be accepting, you know, trying and catching errors, catching bytes, we can't be assuming that it is in the format that we expect it to. Otherwise, you need to really trust the address that you're calling and getting that expected value back from. And the final thing here is going to be gas. So when you call an external contract and you don't specify a gas limit or anything like this, you're going to forward all the gas, right? And I think if you guys have been through the Johnny Time course, we talked about gas and gas manipulations a little bit. But we need to be wary that if not trusted, don't forward all the gas, right? We need to give them the amount that we expect them to actually use, instead of actually, you know, giving them literally all the gas except for 1/64th, and then opening up the ability for gas griefing and things like this. And these are all the, you know, high-level issues that I look at when I see an external call. And so when you're choosing whether or not to add external calls, all of these things should be a consideration. So any questions on any of this? Okay, fantastic. So we're almost coming to the end here. I know we're going a little bit over. So we've just got this last idea of post checks. So I'm just going to move this list over here. Post checks. So this is getting more popular recently, this idea of always enforcing invariance after a transaction is done executing. So what does this look like? This looks like if I expect my contract to always have, you know, X balance, so at the end of a function call, then I'll just assert, you know, with a, you know, a validation that the balance of the contract is greater than X after you're done doing your thing. Otherwise, you took some money that you shouldn't have, and we're going to revert. And then we're not going to let you do that. So it's almost like a, you know, break class in case of emergency, last resort effort to, hey, even if you were able to exploit this protocol, we have checks for that, and we're just going to revert, and we're not going to let you do it. So one great example of this that I actually do like their implementation of is GMX v2. And there's actually an issue with this that turned out to be an issue, a finding, and we'll look at why that was an issue, and that will tell you, you know, here's some things you have to consider when you're writing checks like this. So they have this check, get expected min token balance. This is to essentially implement what we just drew out here. after a transaction, they want to validate, hey, just checking, is the balance of this market token greater than these X amounts? So in each market token, they have a single contract for the market token, and then they have, within this contract, there's, an amount stored for collateral. Some amount of this is, some fees or stuff like this. So they add up all that stuff and they say, hey, is that stuff in here? And then if it's not, revert. If it is, we're good to go. So what they do is they add the pool amount, the collateral amount. There's, extra things that we don't have to really worry about or think about. But one issue that they did make with this validation is that they included the collateral amounts in here. And it makes sense conceptually to include collateral amounts in here. But a key thing about their implementation is that when people are claiming their funding fees, they're actually able to claim the funding fees before that collateral has been deducted. And basically what that means is if a user claims the funding fees, which is fees that get charged to other positions, and we will go more into depth on those at a later time, they're claiming it from other users who have that amount stored in their collateral amount. But that collateral amount doesn't actually get diminished until that user comes and updates their position. So this user here took that funding fee amount, which was carved out of this person's thing, but this amount wasn't updated. And so without getting into too much detail, they essentially just ended up DOSing people claiming funding fees. And so this is just to highlight that whenever you do write a validation like this for this expected min balance, we want to make sure that we're not introducing literally a DOS attack for expected behaviors, right? So we want to look at exactly how, this will behave. We don't actually want to give an attacker another knob that they can use to cause a DOS attack on the system. We want to just add, some validation that in all scenarios should be met, but in unexpected cases is going to fail and save us. So that's basically post checks. And then in terms of documentation, I think I just wanted to share a really good README that I found, and I think this is a great way to do a README. Is they have this protocol summary, describe, high level, what are we doing, protocol components, here's the Blueberry Bank, this is this contract, this is these types of contracts, this is what they do, and then they have a component interaction flow. So this is what the user expects to do, and this is how that whole transaction plays out, and then even example execution, and then other things about the Oracle. So I just wanted to share this README. I think this is a great, especially drawing out the user execution flow. That helps auditors get context. It also helps you put your ducks in a row and share this with team members that you might bring on to your protocol team or anything like this. So that was a lot that we just covered, but are there any questions on what we did cover? And then we can get into office hours.
Someone can call, and then they'll restrict it to maybe a trusted user of some kind, the owner, or some other mapping that is trusted.
Yep.
Is that the standard way of solving this, like arbitrary external calls, or have you seen other ways? Because it seems to be this like trusted, they're trusted, so they can do whatever call they want to do.
Yeah, the classic solution, right? Well, they're just trusted. Yeah, that's 100%. It'll be something that if you do get into like solo audits, or you work at a firm, you'll definitely see that, maybe you'll recommend that, hey, there should be some validation on, the ranges that an owner can assign for this, or maybe the owner shouldn't be able to make an external call to an arbitrary address or things like this. And then people say, oh, well, it's trust. It is my opinion, first of all, on those on those findings, that they should be, medium, like centralization risk, like findings. But beyond that, how do we do external calls the right way, and how can we make an arbitrary external call that can even be initiated by the user? How can we make that work for a protocol? And I think we're going to be, unfortunately, I'm going to be sharing a lot of GMX v2 code, but I think GMX v2 addressed this in a really good way and they made it work. So we'll just talk about, let me just revert these changes. We'll talk about how GMX v2 actually does have a completely arbitrary external call that in fact anybody can invoke and is actually completely safe. So let's just draw out sort of like what GMX v2 has in their setup. In an order, so an order is basically a request to add collateral to your position, increase the size of your position, decrease the size of your position. You can even make swap orders, but that's another thing. On your order, so there's an order object, basically, or a struct. There is a callback contract. And this is, the reason they have this is for third-party systems to be able to integrate with GMX v2 and build stuff on top of GMX v2. So for example, there is a after order execution callback. So when your order completes and it is successfully recorded and the position has been updated, we're going to go ahead and call back to the callback contract. And so the callback contract could be like a vault on, for example, Dolomite. So Dolomite is integrating GMX v2 into their like cross-margin system. So they need to basically make vault contracts that are able to open, not open positions, but deposit liquidity. And they're using the after deposit execution sort of quote unquote hook to handle all of that logic and make it work for their system. So the callback contract is specified by the user, whoever's opening the order, and it can be any arbitrary address. So that seems like a huge risk. How is it even remotely safe, right? So we can look at, let's have a look at where some of these are called. So this after order execution, it's unfortunate that IntelliJ is not going to work nicely. Okay, so after order execution, you can see where this is called. It's called in order utils, after execute order. So after all the logic happens for an order, we call this callback. Now, this is partially using CEI. It's after all of these effects, which is the bulk of the effects for handling an order, but it's before paying of the execution fee and then some other things that are, potentially after this, if an order gets canceled or things like this, but we don't need to get into that. The answer is that to make stuff like this work, you have to have auditors spend a lot of time verifying that all of the logic after this cannot be gamed in any way. And with a system like GMX v2 that has, a lot of code, there's a lot of potential like gaming that could go on. So it's dangerous. It's dangerous from just a risk point of view, but we've spent 6 months or so verifying that everything that happens after this is not gameable. It might still be gameable. there's a 0.001% chance that there is something that was not considered, but what we've done just on the reentrancy side of things is, okay, everything after here is not gameable. And then furthermore, if you go on to, let's have a look at, some of their entry points. So if we have a look at the order handler, and I am sympathetic to the fact that, we're jumping around in a really big code base and a lot of this probably doesn't make sense because there's not a ton of context for it, but we'll notice that this external function has this global non-reentrant modifier, as well as this update order has a global non-reentrant modifier. as well as cancel order, global non-reentrant. So what is this global non-reentrant modifier? This is solving for the issue of cross-contract reentrancy that we talked about. So within the GMX system, if we find where this is defined, what we have is a contract that is actually instantiated and handled. So every one of these order handlers inherits from the base order handler, which inherits from the global reentrancy guard. What they do is they have a single data store for the entire system, and instead of setting the reentrancy status in this explicit contract, in this single order handler contract, they set it in the data store for the entire system. And so now once I enter even just a single function in this system, now every other function across not only the order handler, but also the withdrawal handler, which is a contract I promise, but it's not popping up, or the deposit handler, which is a contract. This is also a global reentrancy guard. So none of these handlers can be entered into, even if you enter into one of them. So that's another sort of mechanism to protect against reentrancy, even cross-contract reentrancy. In terms of, so let's go through the list. Let's go through all of these things, right? Because these are all things that we had to consider when we're auditing this. So reentrancy, those were our protections against that. So what about a DOS? So let's go back to callback utils. We wrapped it in a try catch, right? So if the thing fails, we are not going to allow that to affect execution in any way. We're just going to try catch it. And if it does fail, we'll emit an event, be like, hey, by the way, this thing failed. And that does create an issue for protocols integrating to be like, well, hey, I mean, if this thing fails, that might, cause issues for us because we don't really get any sort of ACK that failed. But that's another issue that, we're working through now with those teams. But from the GMX v2 viewpoint, this is the smartest thing to do. Is you don't want to allow that to affect the execution of this. So return values. So we said, earlier we had this, they originally had this bytes memory return data, and that was bad for that reason that we went into with, you don't know what this is actually going to look like. Additionally, if they tried to set some return values from this and then have those affect the system, then that would be something that needs to be looked into of like, okay, if they provide 0, is that going to work? If they provide a single way, is that going to manipulate anything? If they provide the maximum uint, is that going to do anything? So that would be a consideration. And then gas, we'll notice.
Sorry, I have a fast question on the catch one.
Yeah.
But so when you are calling that IO callback receiver, it does, if it fails, it does still return error data. But in this case, we're basically not parsing it or just letting it be.
So at the EVM level, we are not copying that data into memory. So as soon as you add this, you add bytes memory return data. What this is doing under the hood is, if you go and you actually go all the way down to the opcode level, is we're doing a return data copy, and that will copy this data into memory. Even this alone is actually bad. Even if you don't use this return data, just having this here is actually a bad thing for the following reason. Even if I don't use or reference this memory later on, we're still doing that return data copy, which is going to take that memory from, where it's located at currently in return data, and then we're going to expend all of the gas necessary to allocate this much return data in memory. And memory has a quadratically increasing cost for every incremental unit of memory that you allocate. And so what I could do is really unexpectedly manipulate the amount of gas that the keeper who's executing the transaction that's currently, executing this, they could end up expending a lot more gas than they expected. If I just gave you 1,000,000 bytes of return data, and then you had to copy that all into memory, that could cause an out of gas error, which will make the transaction revert and can be further used to game the order. So that's a reason, another reason we don't want to catch that. But does that make any sense?
Yeah. So is the solution basically, when you do these arbitrary external calls, to not have any of that return data be saved to memory? Is that the only solution, or is that one of the solutions? Or
yeah, that's a solution if you're worried about gas expenditure. So for example, in this particular scenario, this is a keeper executing this, and if I can cause this keeper to expend more gas than they expected to, then that is a very negative thing, because first of all, on the surface level, the keeper is just going to need to spend more gas, which might not be what was covered for by the execution fee. So just at the surface level, there's a little bit of a potential loss for assets there. And now digging deeper, if I can get this transaction to cost more than the block gas limit, I can cause the order to not even be executable, period. And then what I can do is I can, at a later block, allow the order to then be executable. And then you execute it. I'm forcing you to execute this order at a later time when the prices in the market might have changed. But if it's a market order, for example, the way that the GMX system works is I have to execute you with the prices in the block or around the block in which you created that order. And so there are a few ways to game that. Now, it's not always required to do this. So for example, if it wasn't a keeper calling this transaction that, ultimately ended up getting here, maybe it's a user that is executing this and they're the ones who assigned the callback contract. So in a sense, if this was here and we were doing bytes memory revert data, they would just be griefing themselves, right? Because if the user is the one doing this and they're the ones who provided the malicious callback, well, they're just costing themselves the gas, right? And then presumably that's fine to be loading that in there and then potentially even doing whatever you want to later. So it all definitely depends on, what is the context within this is being executed. And if it's a bad thing, if I cause you to spend more gas than you were expecting, then that's when we need to, have these extra considerations about loading in data like this. But does that answer your question somewhat?
Yeah, 100%. Thank you.
One quick question, please. In this case, why we don't use Yul to don't automatically copy that byte return data into memory?
Why don't we use Yul to do that, like explicitly?
Yes.
Yeah, you could if you wanted to copy those. So like the whole reason they had to remove this is because we explicitly do not want to copy that. So we don't want to have the Yul logic that does that, right? So having this is, effectively isomorphic to having that Yul logic that does that copying, right? And that will cost the same gas amount of, copying that return data into memory. But yeah, does that answer your question?
Yes, totally.
Okay, cool. So yeah, that is all of the considerations around like that. And I think it might also be helpful to look at another instance of this. So let's see if I can find it here. Okay, so this is what I think maybe a little bit related to what you're saying with like an inline assembly block. So here we're actually using an inline assembly block to specifically avoid loading in the return data. So this is a different instance where we want to call this receiver and we want to send them an amount of ether. And this is an arbitrary receiver, so a few things can happen here. Now, number one, the receiver can give us a ton of return data. We're only forwarding them a certain amount of gas, so that's protected. But they could give us a ton of return data, And if we were to just do a high-level call, we would have to load that return data into memory, and we wouldn't really have a choice about it. But if we do a low-level call, we're going to use and specify that I don't actually want to load in any of this outsize. So if I gave this, an offset of like x20 or something like this, then it would actually go and copy, 32 bytes of return data in, but we're just saying straight up 0. I expect 0. And that way we're avoiding any kind of that manipulation. And we're explicitly doing that in an assembly block with this low level call. And this is just a ether transfer, like a very basic thing. So yeah, hopefully that makes sense as well. It's kind of on the same sort of topic. And then, yeah, this is also, so gas is the final thing. They have a configured callback gas limit, and there's the appropriate validations around that. And then also with this as well, there's a gas limit defined for that. So those are all the things that you want to have checked off, and you want to be very solid on when you're making dangerous, arbitrary external calls, and any user can initiate them on the exchange and make the keeper have to call these addresses. Yeah. All right, great. So in this video, we're going to cover 4 different types of reentrancy, and with each example, we're going to get a little bit more complex and nuanced. So first of all, we're going to cover the classical example of reentrancy. We're going to cover the canonical example, and then we're going to make things a little bit more interesting, and we're going to look at a cross-function example of reentrancy. And then we're going to go a step above that, and we're going to have a look at what I like to call cross-contract reentrancy. And then even more mystical and mysterious than that is, of course, the read-only reentrancy. And then after we cover all 4 of those, I'm going to give you the method that I personally like to use to uncover every sort of potential reentrancy attack vector and find the maximum impact of an arbitrary external call. Okay, fantastic. So let's start off with the basic classic case of reentrancy. So we've got Remix pulled up here, and we can see that here we have just a canonical vault contract, and you could probably very quickly, very easily see what the issue is here. So we can see that in this withdraw function, somebody can have already deposited a balance into the vault, and then they'll get called right here. And this is, importantly, before the balance of the person who's withdrawing is updated. And so we'll see this as we go throughout, but this really helps to illustrate the fundamental problem with these reentrancy vulnerabilities is simply that there's a piece of state that is outdated or not yet updated at the point when we essentially hand over execution of the transaction to an arbitrary external address, in this case, the message.sender. So when we .call the message.sender, we're going to be sending them this balance, and we're going to be executing either their receive function or their fallback function, and essentially letting them have control of the execution. And so we can go and see the exact attack that could be used on this, and we can see that this attack contract here can go ahead and first deposit it into the system to get some sort of balance, and then when we withdraw, it's going to withdraw back to this contract, because this contract is going to be the message sender. And then when we withdraw, it's going to hit this receive function. And then what's going to happen is we're going to continue to withdraw until we essentially take all of the balance out of the contract, and you cannot withdraw again. And so if we go back here, what happens when we continue to withdraw is we continue to hit this line here and then execute another withdraw and just keep taking ether. And then at the end, we will simply just be deleting the balance, which just sets it to 0. So ultimately, the attacker is able to loop the withdrawals and take out some multiple of whatever their balance was and essentially drain the vault, right? And so this is all stemming from the fact that this balances is out of date by the time we are handing over execution of the transaction to an arbitrary external address. They can execute arbitrary code, right? And so, one solution is, of course, you could add a non-reentrant modifier here, but an even better solution, as we'll see as we continue to make things complex, it will become very clear that the best solution here is to have everything actually updated before you make any external calls. And of course, this is very commonly known as the check effects interactions pattern. And that basically is saying that your function should be organized in such a way where at the beginning of the function, you have all of your require statements, all of your validation to make sure that inputs are correct and the state is what you expect it to be before the function is called. And then you go into all of the effects of the transaction, right? And the effects are you updating a particular piece of the state? Are you emitting a particular event? And things like this. And then only after all of your checks have been done, and then all of your effects, all of your state updates, any sort of event emissions and things like this, after all of that is done, then and only then should you be making the external calls. And so this way, when we do our effects before making this external call, this interaction, then now what we've done is we've essentially neutralized the message sender from being able to sort of, arbitrage or exploit the fact that this balances mapping is out of date. Great, so we've really understood and picked apart this most basic example. Now let's step things up a single level and look at this cross-function reentrancy. So pause the video here for just a second and try to see where the exploit is here. I've already given you a hint that it's essentially a cross-function reentrancy, but try to see how it could play out. And so maybe you've seen that the message.sender is, of course, similarly to last time, we're not following the check effects interactions pattern here, but we did add a non-reentrant to the withdraw. So there's no way for the attacker to re-enter into withdraw and pull off the same exact exploit as last time. Like this very simple reentrancy attack here is not going to work because the second time we try to enter withdraw in the same transaction is going to, of course, revert. But what we do have is some other functions that could be reentered into. And more specifically, the transfer function here that might have stuck out to you because it's the only other function that was added here is something that's going to be vulnerable to a cross-function reentrancy, right? So when we enter into withdraw, we know there's a piece of state that is outdated here, and that is the balances. The balances have not been updated in this contract before we are sending around assets and doing our interactions with the message.sender here. And of course, this should be payable here. These are roughly pseudocode just to go through, but of course that should be payable. So what can happen here is we hand over execution of the transaction to the message sender here on line 16, and then before the balances have been updated to this, the balance minus the original balance that's cached here minus the amount that they want to withdraw, then the attacker can call this transfer function and essentially transfer a balance that should no longer exist to another account. And then the balance will just get set to the amount that it should have been before this external call was made. So if we have a look at the attack for this contract, we could see that it's somewhat similar where first you just want to get some deposit, and then on the receive function, when we get execution, when we get control over the execution of this withdraw transaction, then we're going to get the balance that we have that's for this attack contract, and then we're going to transfer it to some other address to the owner, whoever wanted to sort of end up getting this. And then of course, after this withdrawal, when it goes back into the withdraw function, then we're going to actually set the balances to the balance minus amount. So this is whatever was subtracted here is basically going to get overwritten, and essentially you can duplicate tokens this way. Okay, so obviously when we're thinking about reentrancy, we need to think not only about single functions, because as we saw, this one was non-reentrant. We need to think about every function in this contract. But then, of course, what happens when systems start to span multiple contracts and they start to have several points of entry into the system? So, of course, what this means is there's going to be exponentially more attack vectors and surface area for especially a reentrancy attack to take advantage of the system. So let's check out two contracts that I have here for sort of like a pseudo system. So we have, first of all, a two-step swap manager, and then we have a two-step swap executor. And so this is, of course, somewhat of a contrived example. Of course, there would be a lot more complexities involved in these two contracts here, but this is somewhat inspired from the GMX v2 codebase and an issue that they had very early on. It was, in fact, slightly different than this and a little bit more complex, but essentially this is a very simplistic approach to how we can have sort of cross-contract reentrancy. So we'll go through the two-step swap manager. Here somebody can sort of create a swap, which is sort of like a request to have a swap executed, and then on the manager they can also cancel their swap and basically get their swap amount back. And then there's another contract in the system which is concerned with actually executing these swaps. And of course, this is a very simple contract, but you could imagine there would be a lot more logic here to set prices and other things like this. And this contract is meant to be interacted with by the swap executor, which is a different role. This is meant for the permissioned keeper to be interacting with this contract. And so you'll notice that this function is non-reentrant, as well as all of these functions are non-reentrant in the manager as well. And so if everything is non-reentrant in the system, then you might be wondering, how could this have any sort of reentrancy attack? So I'll go ahead and pause the video here. I'll encourage you to look at this, see that there's an execute swap function, and then note that the swap here could end up calling the user and giving them execution of the transaction while they're sending them Ether. And then note the functions that we have here on the manager, and go ahead and try to come up with a cunning way to impact the system and essentially have a cross-contract reentrancy. So you might have noticed that there is an interesting contract here, or an interesting function here, where you can cancel the swap, and what this will do is it will transfer you back your tokens. And this is, of course, non-reentrant, but it's on this manager contract. And so if we go to the executor contract, we can see that one key thing here is that the pending swaps, this should, of course, be interacting with there should be some function. Really what this should be is it should be something like this, and then .delete. But of course, this is, of course, roughly pseudocode. So pending swap, it gets deleted. This state is only updated after this swap here. And this swap is where the execution of this transaction, of the transaction that the keeper started on this executor contract, is started. So if we look at things from an idea of what is happening with these non-reentrant modifiers, is as soon as the keeper calls execute swap, now this non-reentrant is going to have, you know, if we have a is reentrancy guard here, this is going to essentially flip the switch for this contract. And so now this contract, everything that is non-reentrant in only this particular contract, is going to be able to revert when it is entered a second time. And that's because, of course, this inherits from reentrancy guard, which means that this is storage for this particular contract. And so now when we go to the manager, this one will, of course, also have is reentrancy guard. And this one will have a separate storage that will be in this contract, which will store whether or not this manager contract has already been entered into. And of course, when we are just calling execute swap, at this time, the reentrancy status for two-step manager is not entered. And so we will be able to call a function on the two-step swap manager if we're receiving Ether and we get called on this line here. And so what can we do? We can essentially cancel the swap mid-execution, right? So what we can do is the keeper will come and execute our swap. And then when we do we're in the middle of the execution of our swap and we're literally receiving the Ether that was resulting from our swap that, presumably used our tokens, then we can come here and just cancel it. And so after it's literally already executed, but it just hasn't been deleted yet, we can cancel it and get these ERC20 tokens back that we put into the system. And so we get a very risk-free, we get the money we put in back, and we also get the amount that we got out. So this is a very cunning way to sort of across contracts, across a system that is spanning multiple contracts, a way to re-enter, even when everything has a non-reentrant modifier. And of course, it's very much worth noting that this, again, is a symptom of not using check effects interactions, right? Because this iSwapper.swap, this is an interaction, and this delete here is an effect. So this effect should be happening before this swap here. And so now everything is up to date before we call any external addresses, before we potentially hand over execution to any arbitrary external address. Great, so now we've gone over really the highest order of complexity of reentrancy, which is cross-contract reentrancy. But now let's discover and sort of dig into the mystical idea of this read-only reentrancy. This is most famously known for some of the recent exploits with curve pools, utilizing their callbacks. And however complex it sounds when you start to read about curve pools and how they work and how this was able to be leveraged, it's actually a very simple reentrancy vulnerability that we actually already understand, having gone through these three examples here. And what we're going to do is we're going to make it as simple as possible and remove it from any of the sort of DeFi jargon or anything related to curve and show it in its simplest form. So it's actually very digestible and you'll be able to see it directly right away. So the fundamental idea behind read-only reentrancy is exactly what we've been saying thus far and exactly what we've been seeing. And it's essentially that some piece of the state, some effect has not happened, a state has not been updated before an external call is made. Now, any systems that rely on this particular piece of state, which is updated at the time that an attacker has access to the control of the transaction, now these third-party systems built on top of, a curve pool or any type of system are going to be reading inaccurate, outdated state. And so now these third-party systems are going to be able to be exploited because of this outdated information. And that's it. That's literally all it is. That is the fundamentals of the read-only reentrancy. It is literally just like any other reentrancy attack. Somebody is exploiting a piece of outdated state. And you might have noticed that read-only reentrancy is essentially just a way to execute what is really just a cross-contract reentrancy, but instead of re-entering into the same exact system, you're going from one system into some third-party contract system. So let's dive in and look at a read-only reentrancy case. So here we've got a very simple scenario where we've completely removed it from any sort of DeFi, curve pool information or anything like this. We've got a similar sort of vault contract here where you can deposit and you can withdraw. And we'll notice classically there is, of course, a withdraw function here that hands over execution to the message.sender and subtracts from the balance here. Now, of course, this withdraw function is not going to be directly manipulatable because you'll notice we're actually subtracting from the balances each time. And if this goes negative, of course, it will revert. So there's no direct reentrancy vulnerability in this contract here, but the key is there's this view function here, which seems absolutely harmless, but at the time when we are handing over execution to the message.sender, they've essentially withdrawn their ether, right? They've gotten their ether amount. It just hasn't been reflected in the state here in this vulnerable bank contract. And so at the time when the message.sender is called on line 17, is allowed to withdraw for this original amount is going to be, of course, true, because of course we assert that it's true before we even get here. So of course it's going to be true, but it might not be true after the withdrawal is actually happening and it's being accounted for in the balances state. And so now immediately any third-party contracts, any system, even any front-end systems like this are going to, at this time, if they read in between this transaction, now they're going to see a false, outdated value for is allowed to withdraw. And so depending on how these third-party contracts are structured, this could be potentially very bad for them, where they're seeing that somebody's allowed to withdraw this amount, but they actually don't actually have that amount left in the system. And so this is exactly similar to the cross-function exploit that we saw, or even the contract exploit that we saw, where somebody was just able to leverage an outdated piece of state. And so however third-party systems integrate with this is allowed to withdraw function, they should know that it could be manipulated in this way. And essentially the vulnerability, the core of the vulnerability definitely lies within this vulnerable bank contract, because it of course should use check effects interactions here, where we subtract from the balances right there. And so this is a very simplistic read-only reentrancy example that makes it very clear that it's nothing really crazy or complex or mystical like it sometimes seems. It's actually really just the root cause of reentrancy, and that's just literally some piece of state being outdated at the time of an external call. And so the idea when this was translated to curve pools is essentially that somebody would make a swap, and then before their impacts of the swap were recorded on the price of the token, they would have what is essentially a callback that would just end up passing over execution of the transaction to potentially an arbitrary address, potentially malicious address that could leverage the fact that the price impact of this swap had not been recorded yet. And so this could be used to exploit any sort of systems that were relying on reading that piece of state from this curve. Great, so those are our 4 high-level examples of reentrancy. We got a little bit more complex as we went along. And before we jump into my system for detecting reentrancy vulnerabilities, I want to quickly cover, of course, ERC 721 token reentrancies and then ERC 777 reentrancies. So for ERC 721 reentrancies, of course, there is a on ERC 721 received function that is called on the receiver of any NFT, any ERC 721 token. And this is called on like safe transfer from, when you transfer from an address to an address, and it essentially invokes this function on the to address if that address is a contract. And so this is of course something to remember, as it's simply just another external call that could pass over execution of the transaction to that arbitrary address when potentially there are state variables that have not yet been updated. And then of course, similarly with ERC 777 tokens, these tokens just expose callbacks that will potentially hand over execution of the transaction to either the from address or the to address, or whatever the implementation of the token is. So at this point, we've seen virtually every case of reentrancy. We understand exactly how it comes up, why it comes up, and now I want to equip you with my system that I personally use to be able to detect any kind of reentrancy vulnerabilities. So of course, we've noticed thus far that the root cause of a reentrancy vulnerability always starts with an arbitrary external call. And it is particularly centered around state variables not being updated before this call, right? And that's why check effects interactions is so effective, because we want to make sure to update every piece of state before we do our interactions and make external calls. So the first thing I like to do is simply enumerate every external call made by the system, especially the ones that are made to untrusted accounts or arbitrary addresses, and especially the ones that occur before state updates. And it's great to use a static analysis tool like Slither to easily just enumerate all of these external calls that are made before pieces of state get updated. Okay, great. So once we've collected our list of potential external calls that are risky, then we want to collect another list of just knobs that somebody has during the time when they control execution of the transaction. And so this is going to be any external call that could be made in the system, and every piece of state that is outdated at the time when that external call is made, when the transaction execution is passed off to an arbitrary address. So make a list of every piece of state that is outdated, include that for each of the external calls that are risky. Say exactly for this external call, this risky one, it is risky because I can call this arbitrary address and X, Y, and Z state vulnerabilities are outdated, or they have yet to be updated at the time of this arbitrary external call. Now we've got the list of all of those external calls with the list of state variables that are potentially vulnerable. And then now we make a second list of all of the external calls that an attacker, a re-enterer, has access to on the system, right? So what's the surface of the system that an attacker could enter into? So now we have a deterministic closed form way to sort of go through and for each external call, examine each individual surface that the re-enterer can re-enter into. So really now we've made it into a very manual process that we can go through, and for each thing we can consider each scenario and consider the impact of the outdated state variables for each external call when we're re-entering into any of these functions that an attacker has access to. And so it might help to think about it this way. What advantage can I gain when I'm re-entering into this function when I know that X state variable is about to be updated to Y? And of course, when it comes to detecting read-only reentrancy risks, of course, any deviation from check effects interactions could be potentially risky, as any outdated piece of state that an external third-party system might rely on at the time of an external call that hands over transaction execution could be leveraged to damage any of the third-party systems that are built on top of the system and reading that particular piece of state. Okay, so that is entirely the ultimate guide to reentrancy and exactly how I like to approach uncovering them and really identifying each of the vulnerabilities and risks of reentrancy across an entire system. And so I hope that really made things quite clear to you, and I hope that you saw some new ways and some new nuances of reentrancy in this video. And I hope that you'll be able to apply what we've talked about here to your next audit and your audits coming up along as you continue in your journey. So today we're talking about testing smart contracts. So last time we talked about design, and I would say just as important, maybe even more important, is testing. So of course, I mean, you guys all have some, a decent amount of, like whether it be Web 2 experience or, just development experience in general, you guys are already familiar with, what does it look like to test and how important testing is. Well, if testing is important in the Web 2 world, then it is like unbelievably crucial to the Web 3 world, because now instead of, UI bugs where users click and then something doesn't look right, now we have, hundreds of millions of dollars of assets at stake where users click and then they send a transaction to the zero address, right? So the testing is really severely important, and I think that having a strong basis of understanding, from my point of view, what is the ideal approach to testing will be really helpful for you. Not only, if you ever do become a part of a protocol team and you want to build out an effective testing suite, but if you want to start your own audit firm or you want to be a solo auditor, this is something that I think is really often overlooked, is the entire testing side of the equation, right? So everybody's, in my opinion, really over-indexing on manual analysis at the moment, which is, definitely a huge part of it, and it's probably the most time-intensive part of what we do. But the testing side of it, and really understanding things like fuzzing tests and things like good path-dependent tests, which we'll get into today, is really, I would say, at least 50% of the equation, maybe even more than manual analysis. And it will give you a lot more leverage. If you're very good at writing fuzz tests, you can find a ton of critical vulnerabilities in an hour. On the other hand, it might take someone, days to find those with manual analysis. So this is what we're going to dive into and really understand today. So first of all, of course, we have to talk about just the basics of, the basic type of tests, right? So obviously we've got unit tests and we've got integration tests. We all are familiar with this sort of paradigm, right? So both of these are useful. Some of them are more valuable for certain things and at certain points in the development process. So unit tests, at least personally, I believe that these are really good at catching bugs early on before they become more insidious. Like if you have a low-level library function that is just doing some arithmetic, if that is well unit tested, you're gonna ideally have chased out any potential bugs right there, stop them at the root cause before they can potentially become a part of a more complex system as a whole, and then lead to really tricky bugs, which if you catch them with an integration test are a lot harder to debug, right? So unit tests will generally just is a sign of a really well-tested code base, as if I can have tests that are discretely testing individual functions and would catch any bugs at that level, versus the integration tests, which are designed to catch bugs at the composability layer, or at the the protocol as a whole layer. So these are going to be tests that are more focused on what is the user interaction flow and things like this. But this is, of course, the basic stuff. We all know this. Now let's talk about code coverage, because of course both of these things improve code coverage. So everybody talks about code coverage, say, you should always have 100%, you should always have 100%. And yes, that's true, but let's understand what exactly that means. 100% code coverage should, yes, always be strived for, because, if you have like 60% code coverage, well, there's 40% of your code that's going to have dumb, stupid errors in it. So of course, let's have 100% code coverage, but let's understand exactly what that is. It's actually not that powerful when you think about it. Let's have a look at an example of a contract here. Let's have a look at this ticketer contract. So I've got a contract here that just has two functions, and it's just meant to collect tickets. So I can buy a ticket, I can buy a certain amount of tickets, and they cost a certain price, and then I get that amount of tickets, and then the owner can come and claim the tickets. And I've gotten some tests here written for this contract. So let's run the tests and let's see how good is our test coverage. I've just run them here, and let's do forge coverage.
Owen, can you zoom in just a tad?
Oh yeah, here we go. How's that?
Much better.
Okay, cool. All right, so let's run forge coverage. And we can see that our ticketer contract is tested beautifully, right? It has 100% code coverage. So there should be no bugs here, right? Should be no, this should be a really solid contract, right? Really well tested. Should be no issues here, right? Do you guys see any issues with this contract? We tested that people can buy tickets.
Owner collect should be protected.
Yeah, 100%. There's zero security here, right? We tested every single line. So everything was tested, but I can still come and literally steal the money that's gone into this contract, right? It's ownable, but we're not using an only owner modifier here. So what I can do is, in our ticketer tests, we're missing a very specific case where the owner, somebody who's not the owner, so if Alice is collecting this, and then the owner balance afterwards is still 0, but Alice's balance is now 1 ether, we're missing this test case, right? So if we come here and we do, and we run these, we get an error. And we can see Alice is able to collect for the owner, and she's able to take the ether out of the contract. So 100% test coverage, we need to take that, with a grain of salt and understand that, well, I can cover every single line of the code base and still we can have a lot of interesting things that happen beyond that can be entirely exploitative, right? So of course we want to strive for 100% code coverage, but we want to understand exactly what that means and that it's not like the end all be all, right? So that's what we want to understand. And then hopefully what we can have is when you have POCs like this, for example, if you undergo a security review and you get, somebody, if there is a review and it points out, hey, somebody can collect for this owner address, and there's no access control, ideally what happens is the protocol team takes that POC and they actually turn it into a test case and they sort of invert it, right? You would, vm.expect reverts and then have that as a test case in your code base so that as stuff changes over time, which inevitably it does, then it's still asserting that, okay, that previous issue is not able to come up again. And this is what we'll see in a few minutes here, sort of how we handle this with our clients and how that ends up looking with, more interesting POCs and things like that. So let's talk about some more interesting tests. So of course we know unit tests, we know integration tests, but let's get a little bit more specific about, what does it mean to have coverage of not the code lines of a project, but the space of potential edge cases and the space of scenarios. So how is it that I can cover every single line of a code base and that's all the lines are tested, but it's almost like there's this three-dimensional space of edge cases. So like, if I'm going to attempt to draw in 3D, here's what it looks like to have code coverage. You've got all this filled in. You covered all of that surface area. But here's what it looks like in reality, right? It's actually, it's a great cube. It's actually, there's all of this surface area that goes completely untested. Maybe you've literally just filled this one bottom layer here, and that's what you've tested. So how do we test and come up with a framework for testing this, the actual volume of the different possible edge cases for a specific protocol? So first of all, we need to talk just a little bit about an idea of, path dependence versus path independence in terms of, software. So what is a protocol that is path independent, or an interaction that is path independent? It is, for example, if I just have an ERC20 token and we're doing, let's say, Bob transfers to Alice 20 DAI, and then that's followed by Kevin transfers to Alice 20 DAI. The net result, no matter if you do this one first or you do this one, first, whichever the order is the same, right? So it doesn't matter what path you take, you still get to the same outcome. So doing transfers like this, as long as we're assuming everybody has enough tokens and approvals and things like that, simple transfers like this are path independent. So there's not a lot of volume to things like this. But there becomes a whole lot of volume when you talk about something like an AMM, right? And this is where we start to care about ordering, right? Of course, we've heard about sandwich attacks. Ordering really matters, in fact, when you're buying things on an AMM. So if Bob buys Bitcoin at, hopefully it doesn't go to $40, $50,000, let's be bullish. And then Alice buys Bitcoin after him at, $50,010. This is the net result of this is that Alice ends up with, a little bit less Bitcoin, and Bob ends up with a little bit more relative to how much they put in. But if you reverse the order, the outcome actually changes. And so this creates a lot more interesting of a protocol when it comes to integration tests and writing specific integration tests, specifically path-dependent integration tests. So I can write a quote-unquote integration test that is, let's have Bob opens a perpetual position. That is an integration test. Depending on what your protocol looks like, this could span across multiple contracts. It could, maybe you have to call a view function on the LP contract or whatever that might look like. So this is an integration test. This is also an integration test. Is Bob opens a position long ETH. Alice opens a position long ETH. These are both integration tests. This one is starting to follow a path, right? So a path of actions. Now, it's not too interesting how our protocol is laid out just yet, because in most scenarios, whether or not Alice opens her position before Bob or Bob opens his position after Alice, usually it's going to be basically the same outcome. The only thing that's really going to change for us at this point in time is maybe Bob opens a position that's so big that there's no open interest room left for Alice to open her position. Maybe this reverts because it fails the validation. But you could imagine in a much more complex protocol, like for example, if we had like a GMX v2 or something like this, instead of just reverting as being like the only small edge case that could change what happens depending on the order, well, now you have things like price impact. So she gets price impacted much more negatively versus maybe Bob gets price impacted positively. And the short answer of what exactly price impact is it's just the same sort of idea of on an AMM. When you open a position, it's going to change the price of the underlying thing. So what GMX does is they arbitrarily change the index token price that you will experience depending on how much you are offsetting the balance of longs and shorts. That detail is not entirely important right now, but it just goes to show that in more complex situations, in more complex code bases, we get these more path-dependent tests where things start to vary very widely depending on what order things are happening in. And I want to briefly show you guys one protocol that is probably the path dependent to the max, right? So we don't need to understand fully what this protocol does, but I want to show you a way that the development team decided to structure their tests in such a way that really truly helped them build a much more effective testing suite in probably a fraction of the time by specifically focusing on these types of path dependent tests. So if you can imagine, what does a really strong path dependent test looks like? Not having a ton of integration tests that just look like this, where it's a single thing that's happening, because then if all my integration tests look like this, is just testing this one feature, one functionality, you're missing all the volume of the volume of edge cases and scenarios that can come up. But if we start to do an integration test that looks like this, and we go through and we validate, okay, everything is happening as expected as we follow this path, now you're starting to hit a lot of the volume here in the edge cases that can arise. So let's have a look here at Poolshark Limited. So to give a very brief overview on what Poolshark Limit Protocol is, without getting too in the weeds, it's not too important to understand entirely what is happening here. Essentially, it is a concentrated liquidity pool that allows for one-way limit orders on-chain. So in Uniswap v3, people can make positions of concentrated liquidity. When the price moves through it, their position trades from one token to another. The only issue is, as price moves back down, that position trades back the other way. And so I can have a position that turns from USDC on, if price is over here, my position could be entirely in USDC. And then as it moves over here, my position would be entirely in ETH. And so that would be like akin to me setting a limit order and having that limit order getting filled. The only issue is that as the price goes back the other way, your limit order gets unfilled, which is not what a limit order does. So Poolshark's limit essentially allows many different traders to come, and you want to set your limit positions from this range to this range, this range to this range, and they come and as the price moves up, you get filled. As price moves down, you don't get unfilled. So you can imagine when you have a lot of traders that are coming in and then price moving around and people getting filled and things like this, it's a very path dependent protocol. It depends on where does the price move. It depends on where are people creating their positions. How much liquidity is in that position? Did somebody create a position ahead of mine and so they got filled and that ended up restricting how far the price went, which means I didn't get filled, or I only got filled a percentage, or maybe price only went halfway through my position. So it's not important that we fully understand everything to do with that protocol, but to just see that as protocols get increasingly complex, there are exceedingly exponentially more paths that can be taken. So here's how the Poolsharks team sort of addressed that. They have their limitpool.ts test file, and this is, of course, they're in hard hat, so this is not in Foundry. But what they did is they changed the configuration such that the tests ran one after another, right? So it's not this single test case running and then everything getting set up again, and then the next thing running, and then everything getting reset, and then the next one running. It's in fact one long path where every test case that gets added is added and appended to the end. So you could imagine, write a new test case. I have test case number 5 here, and it's not basing off of just the pure setup. It's based on everything that happened prior. And so now this is basically testing one super long path of different edge cases and things that come up. And so we're able to hit a lot more volume. Like for every test case that I add, I'm not only testing this for, that one case, it's also applying to, it's building off of everything in front of it, and then it's adding to everything that comes after it. So you almost get a squaring effect of the effectiveness of a test case. And so there's one other thing that the Poolshark team did that was really beneficial for them. So what they did is every time we had a POC, which gave some sort of critical result, what they did is they came and they added it, they appended it to that list of, okay, we're going to issue a fix, and then what we're going to do is we're going to add this specific POC to our test suite and show that it specifically works now. And so this is what they did, and they added, multiple of these POCs that we came to them with. And so that's a fantastic way to solve for really complex code bases that need to be tested for path dependence. But we're doing it in...
Isn't that hard to support afterwards?
Yeah, in terms of maintainability?
Yep.
Yeah, I would definitely say so. Yeah, but in terms of getting this code base tested fully, it served them very well. And now something does go wrong, yeah, it takes time for them to debug, for sure. But any questions on that?
So in the example which you gave, does that mean that they'll have like the same test, basically testing the same function, for example, minting, pretty much the similar test, but in a different situation?
Yeah, 100%. So, for example, they have only a few functions here, right? So they've got, you can mint a position, and then you can burn a position, and you can swap a position, or you can swap as, somebody who's using the liquidity in here and get some of these positions filled. So there's only like 3 main functions here. There's really, this is where we start to see the difference between code coverage and like real edge case coverage, because here's what this code base looks like. This code base looks like, here's the actual code coverage. You might cover all of it, but the volume is huge, right? There's all of these different edge cases that can arise. This is what this code base looks like. And so what has to be done is we have to test, those 3 functions can yield massively different things. And we found, I think, a dozen plus different critical vulnerabilities just between those 3 functions, depending on what the situation was in which they're being called. And so I'm going to show you guys in a second a better way to do this that isn't so hard to, you don't want to be debugging things like that. And yes, there is the point of maintainability, but there's a key problem with this that we'll discuss in a second. But I guess just based on everything we've covered so far, are there any questions?
Nope, an interesting approach. Haven't heard of it.
Okay, great. So, like Demo said, of course, this is really not friendly for debugging stuff if you do happen to get a error and it poses maintainability issues in the future. There's another, fault with just doing this approach, is that what we've done here is sure, we've created a single path that we're following, and it hits on a lot of different, quote unquote volume of edge cases, but it's essentially one hard-coded long path, right? It's not generalizable per se. So what we want to do ideally is we want to come up with something that completely fills out all of this, not just going through in one path. We want to hit the entire volume of edge cases, right? And then this is real code-based coverage. This is not just covering one, the base of the cube. This is covering all possible edge cases and all of the possible things that can happen, right? And so this is more powerful than just following a straight path. This is literally filling the entire cube. So how on earth do we do that? So this is where fuzzing comes in. This is where we can really start to leverage testing infrastructure and things like this. So firstly, what we'll do is we'll look at like a basic example of fuzzing and see how it can be helpful on a small scale. And then we'll go and we'll really scale that up, and I'll show you how we used it to go from, you know, what they had with this sort of approach to completely filling up the entire edge case area and offering really a strong level of verification for the protocol. So we'll get started. We're going to have a look at this calc contract here. So does anybody see any issues with this right off the bat? This function is just intended to take in an integer, given a minimum magnitude and a maximum magnitude. It will bound it within that, and then it's supposed to basically return that integer with the same sign, but with the bounded magnitude. Okay, so seems like it could work. Seems like it makes sense. Let's go ahead and fuzz test this thing. Let's see what can we, you know, can we verify that it does what we expect it to, right? So we're taking in a value here in this test. So this will be the thing that is like the random value for our fuzz test. And then, so what we want to do is we want to get the bounded result. So we'll call this calc contract bound magnitude. So we're going to give it the value, and then I've just got min and max here hard coded at the moment. You could, if you wanted to further improve the fuzz test, you could also take a min and a max as, you know, variable. But we'll just do a basic fuzz test here. And so what this is going to do is we're going to get all sorts of different values bounded to 5 and 120. So what do we expect a bound magnitude function to do? Of course, we expect the bounded result to have a magnitude within the bounds that we declared. So we're going to add an assertion. So the result, the magnitude of that should be less than the max. Do you guys agree with this assertion here?
Yeah, sure.
And then similarly, we should also bound the result, the minimum. So the magnitude of that should be greater than the min. So what we're checking here is that when we do run this bounded magnitude function, we should always get that value bounded to this magnitude. And it looks like it should work, right? We get the magnitude, which is just the absolute value of the value, and we get it gets bounded to, you know, if it's less than the min, we set it to the min. If it's greater than max, we set it to max, and then we need to just get the sign of the thing, and then we multiply that by the sign. So
I guess in that example, we don't have anything if it's equal to the min and max, right?
Yeah, so if it's equal, then it will just return, right? And that should be fine, right? It's bounded. I guess the definition of the function is that it will be equal to or less than the max.
Yeah.
So this contract is called calc test. So we got a counterexample. So this is what it looks like when we find something that doesn't match our assertion. So what we got is 240. So 240 as the value. We bound 240. So 240 is definitely greater than the max. It should get bounded to 120. And it should, so this bounded result should be 120. And then, of course, that's less than or equal to 120, right? So obviously, something's gone wrong. in this calc function, in this bound magnitude function. So let's step through it. So we have an integer of 240. The magnitude is 240. This is less than 120. So the magnitude must therefore become 120. That's the min check. So actually, right here, this one's 120. So we're obviously 240 is greater than 120. So then we do 240. We just assign it to 120. So the magnitude is now 120. So let's get the sign of this value. So if the magnitude is equal to 0, which it is not, it is equal to 120. So we go into this else case of the ternary. We do value divided by magnitude. So usually value divided by magnitude will just give you that, unit vector that will just give you the sign. But this isn't actually the magnitude of the value, this is the bounded magnitude. So what we're doing is 240 divided by 120. This sign variable is equal to 2. And so then what we have is the magnitude, which is 120 times 2 equals 240. And so that is something that is obviously going to be a failure case, right? So we're returning 240, and obviously that's not less than 120. It's actually double 120. And so that's a way to not even, I could have been terrible at manual analysis. I could have looked at this, my eyes could have glazed over, and I could have been like, I don't even want to read this function. I just want to read the documentation, and I want to see what is this function supposed to do. Let's actually verify that. And this is infinitely better than having to read stuff for 6 hours and still being, prone to human error. Maybe you overlooked something or didn't consider some edge case. So let's go ahead and let's fix this, right? Let's fix this function. So how do we fix this? So instead of dividing by the magnitude after it's been bounded, we could, just get the actual straight up magnitude of the value. And so this right here, this should give you always, 1 or negative 1. So in this case, we would get 1, and then we do 120 times 1, and then we do 120. So does this function look good to you guys? Should be fixed now. I don't see any other issues. Yeah, so let's see. We changed this. Let's run it. Manual analysis passes, right? I read this function. I can read this function for 6 hours. Doesn't look like there's any issues here, right? We should always be getting the sign. So I was getting capped to the min or the max. And then we're just returning the capped magnitude times the sign. We got a counterexample. And that's because the value needs to be equal to 0. So there's an easy one. It will just do a divide by 0 revert, where you're going to have issues. So if the value is equal to 0, we just want to return 1. All right, now there can't be anything wrong with this now, right? Absolutely, this has got to work. Even if the value is 0, we're just going to return 1, and then you'll get this result. So let's see. Did I save it? I saved it. Let's see. We got another counterexample. This one doesn't make any sense, right? This is a huge number. In fact, this looks like the minimum for the int 256. Why did this fail? Does anybody know why the minimum for int 256 failed?
Minimum for int, you said?
Yeah, so if we do type int 256 dot min, we get this number right here.
Because uint takes half the values.
Yeah, so what's happening is when we cast when we basically try to cast it to a, when we get the absolute, when we do this, what happens is we're trying to convert this negative into a positive. But the issue is that, because of the way that negative numbers are represented, so we can look at type int 256.max. The way negative numbers are represented, the positive, you actually can't have a magnitude of this size on the positive. So we had one greater magnitude on the negative than we're able to reach on the positive. And this is because 0 has to belong to either a positive or a negative number, right? And so just, by ways that, the two's complement works, just, by the way that negative numbers are stored in, or signified in bits, 0 has to go to the positive numbers. And so when we try to get convert this to a magnitude for the int 256 type, it doesn't actually work because there is no positive magnitude that fits within that. And so you could read this function for like days, and you could be like, you could never find that. I would never think of that, right? Like that would absolutely, I would never find that. But we just ran this fuzzing test and we uncovered that, right? So hopefully that you're starting to see the value of running things like this. And in 5 minutes, I uncovered 3 different issues with this function that could have easily been missed by manual analysis. Probably the first 2, likely would have been uncovered by manual analysis. They have a percentage chance of going missed, but they could also take more time to uncover. But now we've just completely, there's no doubt about it. What we've done is we've completely filled up this volume for that function. So you could have had technically 100% code coverage for that function and missed all 3 of those edge cases. But now we've completely filled out the cube for that function. So what can we do? Let's just vm.assume, which will basically take that particular case and throw it out. So we'll say if the, maybe the minimum int 256 that's not likely to come up in the context of where we're using this in the system. So we're like, all right, well, we'll just throw that edge case out. Besides that, are we good with this contract? I mean, there can't be anything else. It must not saved. Min. And we're good. We have verified this with 300 different generalized sort of randomized runs. And if I want to run it for more runs, these are like individual different tests that Foundry is basically creating for us with randomized inputs. So if we go to this, let's say if I want to do 10,000 runs, we can run 10,000 runs. We can say, okay, now I have, some confidence in this function that, it actually bounds magnitude and it does what we expect it to do. So that is, from a basic level, this is what fuzzing can provide in terms of value. So before we move on and see what a large application of fuzzing could be in a way more complex code base, do you guys have any questions based on that?
So would you say that you would fuzz test each function?
Yeah, definitely. When we are scoping out functions that are a good candidate for fuzzing, anything that's like math related, especially like that bound magnitude function, that was actually a function in some updates that GMX was shipping to the V2 codebase, and all 3 of those bugs existed, right? And we found some of those by manual analysis, we found some of those by fuzzing, but functions like that deal with math or any sort of formulas, we always love to fuzz those, especially if they're, anything complex. Something that's really helpful is to differential fuzz test things. So for example, if, let me go back to the whiteboard. If there's a function that is like, for example, like convert string to bytes, and it uses some, convoluted method to do this. Well, usually there's like an open Zeppelin convert string function that it can be compared against. You can set up a fuzz test and be like, hey, we're gonna call this function with some inputs. If we call the open Zeppelin version with some inputs, do we get the same thing? That's another great way to apply fuzz testing to specific functions. And so, yeah, to answer your question directly, should every function be fuzz tested? I don't think every function needs to be or ought to be fuzz tested. I think the ones that are more like library math related type functions, those ones are really good candidates for fuzz testing. But then in terms of, like more general functions, like, maybe like create order, create position, those will have maybe not a particular fuzz test that is designed just for them. They might have a fuzzing harness and a fuzzing infrastructure set up to do some more path-dependent fuzzing, which is something we're going to look at in a few seconds. But does that answer your question?
Yes, thank you.
Okay, cool. Yeah, anything else before we move into the next section? All right, cool. So now we're going to see how we took this approach that the Poolshark team had, and we made it generalized. So I don't actually know what I was going to draw here, but we made it, if this is a vector through 3D space, then we made it fill up the entire space instead of just a single vector, instead of a single path. So
in hindsight, would you recommend them to use fuzzing instead of just super long tests?
Yes, this is absolutely superior. And what we actually did is we delivered the fuzzing infrastructure that I'm about to show you guys to them so that they can use this in the future. I do think there's still value to this, and there's better ways to do it and to adopt it. I think definitely integration tests, they become more valuable as you add more interesting things to them. So there's certainly value to this and having those discrete tests written out. But this, in terms of not only like protocol maintainability moving forward, and in terms of just covering as many edge cases as possible, I would much prefer this. If you could only choose one, I think this is the way to go, 100%. So we'll see here. So first of all, we'll go back to their limit pool contract here. We'll just minimize everything. You can see the three functions that I talked about. There's some other functions, these don't really matter. The main functionality here is mint, burn, and swap. That's really all there is to the protocol. So what we did is we took this limit pool and we built essentially a wrapper around it to be interfaced with by Echidna, which we're going to look at in a second. And so what we've built out here is a wrapper around the mint function that generalizes these inputs. So if I can, mint with an arbitrary amount of liquidity in an arbitrary direction that the pool is trading, with an arbitrary lower and an arbitrary upper. And not only do that, but stack these different mint, swaps, and burns in different orders with arbitrary values. We're going to cover the entire edge case space of this protocol. So what we're doing is, at an individual level, for burn, we took completely arbitrary values instead of what would happen in these tests over here. You're giving them very specific values and then doing computations yourself to verify the results. Now we said, okay, an arbitrary burn. Now, not only are we doing an arbitrary burn, we're saying, hey, what if you did an arbitrary mint, but you did an arbitrary mint and an arbitrary burn in an arbitrary order with an arbitrary number of them. So it could look like this. If I grab this, you could have a mint up here. There's a, it will automatically test out, what if we have a burn that happens before that mint? What if we have a burn that happens here? What if we have a burn here, any arbitrary order? And then of course, also you have swaps thrown in there as well. And so we're automatically testing every permutation of any arbitrary execution of any of these three functions. And so what does this look like when we actually go and run it, right? So we can get Echidna to start fuzzing this sort of wrapper contract and basically throwing all of those values into the system. So let's go back to, I think, limit POCs. And so Echidna is something you can install and run from the command line. We're going to fuzz this Echidna pool contract, and you can run multiple workers, which is basically saying like, hey, I want to do a lot of fuzzing really fast. I want to run a lot of this stuff in parallel. So here's what it looks like when we go ahead and start fuzzing based on this wrapper contract here. So it does some, obviously it's got to compile contracts first, and then we get this nice window here. So a lot of things are happening right now. We have assertions in the mint function, assertion in the swap function, and the burn function. These are the only three we really need to think about right now. So we can see a few things here. We can see calls per second. These are like, right now, those are individual like transaction calls that are happening. Like these are individual fuzzing test runs, right? And then we can see total calls. So as we've been talking, this has been tested 28,000 times. And what we're doing is we're testing even different orderings of what if I call mint, and then I call burn, and then I call swap, and then I call burn again, and then I call mint, or what if I call burn, and then I call swap, and all these different things with arbitrary values here. And so right now, you see all these things passing. Well, what are they passing, right? How do we define what it looks like to fail? So first of all, we'll see, an assertion like this, which is, for example, this one is ensuring that liquidity delta is incremented when undercutting. That means nothing. That has to do with the protocol specifically. We don't have to worry about what that means. But this is a post condition. So after our mint, we expect something to happen here. But not only just here can we write assertions. If I grep the entire code base for some assertions, we can see there's tons of assertions that have been made throughout the code base. So let's have a look at this one right here. Assert liquidity global underflows. So we've got this throughout the code base. Now this is just something that we can assert at any time to make sure, okay, when this thing happens, when the pool.liquidityglobal gets the amount subtracted from it, let's assert right here and make sure that this should never underflow, right? Of course, we never want the liquidity global to underflow. So what we've done is now we're able to verify across all of these different, we're up to 90,000, almost 100,000 runs at this point. I know with that degree of confidence that the liquidity global will never underflow. And you can do this for, any arbitrary, invariance for a protocol. So this is one of our invariants that we basically assigned to this protocol. Hey, whenever I'm removing liquidity from global, yeah, it should never underflow, revert, or anything like that. And now we have, proven that to a certain degree of confidence. So what we did with the pool sharks team, we like to do with every team is let's, ask them, what are your invariants? And then we'll collect a list. right? So let's say obviously this thing, pretty much every time there is subtraction, there should never be underflow. That's an easy one right out of the gate. If you ever see an unchecked block, so, a block that's unchecked and presumably allows for overflow to actually happen and not revert, unchecked blocks are obviously, that should never be happening. And then of course it just takes, protocol specific things. So these are things that will be more, specific to the protocol that you notice throughout the audit is like, hey, it would be really bad if this happened. Well, you can turn that into invariant and then you can make sure that that doesn't happen. So as we've been talking, 150,000 runs have happened. I'm gonna stop this thing and we're gonna see one really cool feature of Echidna. So we can see this little corpus directory here, and we've got some things here like coverage, reproducers. One reason I really like Echidna is when I quit this, we can see saving corpus. So now we've got all these different coverage reports. So what I can do is we can go and let me actually open one of these. We'll have a look and we'll see what does this mean. So there's a HTML version here. Okay, cool. So if I find the Echidna pool contract, here we are. These are our Echidna pool contract. I can see what lines of code were hit. If I see did a revert ever happen on this line, we'll get a little R. And then what lines weren't hit. Like this line, it looks like this for whatever reason wasn't hit. So, maybe there's something to look into there. And you can go and look at the entire code base like this and see how good are we, how accurately are we filling out this cube, right? I mean, this is, this is straight up code coverage, but this is very powerful code coverage because as soon as I know that a line here has been hit, I know it's been hit with arbitrary values in an arbitrary ordering of calls. So we're covering all of the edge case space for every line that we're covering here. And so this is basically a way to go and manually fill out that cube and check, okay, how much of this cube are we filling? And, get all of that covered. So then even beyond that, there's this reproducers directory. And there's nothing in there right now, but what will be here is if I ever do fail a invariant, it will automatically save the exact call order and the exact parameters that resulted in that invariant failing. So automatically built in is this idea of taking POCs. So right here, how we came up with POCs and manually wrote them, and then they fixed the issue and then, put the POC as a part of their thing. Automatically, these reproducers will get rerun whenever you start a new fuzzing session. So it will remember every time an counterexample arises. So let's see what that looks like. Let's go ahead and manually cause one of these to fail. So for example, assert liquidity global underflows. You might wonder why we emit something right before this assertion. We're going to see in just a second. So I'm going to just assert false. So let's say that we found that this assertion failed. Let's go ahead and run Echidna. Okay, bunch of stuff going on here. And we can see stuff really moving around. So we've got an error. We failed a counterexample. And we can see right here, things are shrinking. You can see things, okay, they shrunk it down. So what we saw happening there with, all of the, all that stuff moving around is we first found a counterexample, and then it sort of focused in on that and it tried to find the simplest counterexample. What's the simplest call sequence that I can do? And it's still, even zeroing in and making it even simpler. Simplest call sequence that gives a counterexample. So it's automatically doing that for you. And what we can see here, if we follow these, what these are events. And so we can look at, okay, there's, you know, a panic, a transfer, we can see approvals are happening, events are getting emitted. And it looks like, so I can scroll down here, go down and down and down, and we can see liquidity global underflow. So this is the event that gets emitted right before the failure. And so that's why we are emitting events right before we revert. And that's just kind of at least how we debug these counterexamples. We use events because they get basically logged out with this. And so let's have a look at those reproducers. So at the moment, reproducers, this is an empty directory. If I go ahead and quit out of this, you can see saving reproducers. Now I have reproducers. This is all of the details for what is the simplest counterexample that came up. And then now if I run this again, we'll see immediately it will have that, because it just remembers it and it will automatically rerun that at the beginning of the fuzzing session. And so there it is with that counterexample immediately. And so now, once you give a team something like this, you can give them all of the reproducers, and you can give them the, you know, the echidna test harness here. And now they have this sort of like continuous coverage for all of these invariants. And so if they change something in the future, they make a fix, they can go and verify that, okay, we didn't introduce anything new that broke any one of these many invariants. And what this ends up looking like, if we go to, I don't think this one is, we're able to give us all these different invariants here. So you can see we have a run count listed for all of these different things that were tested. Now this is for a very specific reason. You can never say, with fuzzing at least, you can never say that beyond a shadow of a doubt, this thing always holds, right? But we can say that, well, we ran it 50 million times with 50 million different runs of generalized inputs, and we couldn't find a counterexample to this. So this is really a statement of the strength of the verification that was done. Now, if you want to talk about, you know, proving beyond a shadow of a doubt, you can talk about formal verification and turning things into a mathematical formula and running them through a prover and legitimately verifying them. But with fuzzing, this is, we're just pretty sure, we're 50 million runs sure that this thing didn't receive a counterexample. Okay. So let's see. Yeah, and so hopefully at this point you can see that there's a lot more ways to find bugs and vulnerabilities than just reading the code base. In fact, it's a lot more powerful to build out these harnesses like we did for pool sharks than it is to spend that time doing manual analysis. So that harness probably took us, a few days to build up. But if we had spent that few days doing manual analysis, yeah, maybe we would have uncovered, one or two interesting critical vulnerabilities. Instead, we built the harness, and the harness helped us uncover 10 critical vulnerabilities just by, running that thing and debugging counterexamples. Okay, so what does this mean for your guys' perpetual protocol? It means, basically, obviously, unit tests are always a good idea for individual functions. You want to verify that each atomic piece behaves in isolation. And then you want to try some integration tests. These will just be basic, user interactions, obviously like opening a position, things like this. Nothing too interesting with the path dependent testing. But in the future, you definitely do want to have a few integration tests that test like, hey, what happens if user X does this, and then user Y does this following that? Does that have an effect, or do they fail because of the validation or things like this? And then in the future, what we can do is we can start implementing fuzzing tests, and you might already want to go ahead and maybe have some like computation heavy functions that ought to be fuzz tested, and you might want to implement some of those. But that's basically everything to say on testing. Do you guys have any questions on any of that stuff?
Looks like a very powerful tool. I haven't seen similar thing for Web 2.
Maybe something about fuzzing is powerful. Echidna is powerful as well. Is there something you should still be kind of wary about that they will miss, or is there like situations that like you showed us for code coverage, like 100% doesn't mean that you caught all the cases? Is there something like that for Echidna too?
Yeah, it's definitely the limitations. Like Echidna is extremely powerful. It's so powerful that I would say the limitations are, first of all, the number of times that you run it, and then the power of your test harness. So you can, like, Echidna is this big force of just randomness, and whatever you give it, it will fully, test that out. But it depends on the funnel that you give it, right? Like the harness that you give it is essentially how you're channeling Echidna's ability to just send randomized call data. You're channeling that into the system. And so there are 2 points in which your test harness is, adding limitation to the quality of verification that you're able to produce. First of all, how generalized are you making it, right? Like we saw in for example, our bound magnitude fuzzing test, we didn't fuzz, arbitrary minimum and maximums. Maybe that would be something interesting to fuzz. Is there an edge case that comes up if the maximum is 10 and the minimum is 0, or if the maximum is, the maximum uint or something like this, right? That is one such constraint, right? Like our literal harness didn't allow for certain things to be fuzzed. So we were missing, a blind spot there. Now, second of all, your verification is only as good as your invariance. So you saw we had, dozens of assertions made in the code base. Some of them were a lot more powerful than others, and some of them were a lot more critical than others. But it really depends on what you're asserting, because I could just assert something very basic that holds and run that for 100 million runs with the greatest test harness that allows all of the randomness to get through. And what you've proven is like, yeah, okay, this basic thing holds. It would be a lot more valuable to prove something that's non-obvious if it holds or not, but it's something that's very critical to the code base. And then, of course, the more invariants, pretty much the better, right? And the more runs that you're able to verify those invariants on, the better as well. So yeah, I would say 2 things are the limitations of your harness and then the quality of your invariants. All right, fantastic. So we've just finished the security basics section. So congratulations on getting through the very first section of this course. I hope that was valuable for you, and I hope that you've got a basis for what do well-designed smart contracts look like, what do well-tested smart contracts look like, and hopefully you have an idea of how we can protect from external calls and reentrancy and everything like this, all the basic sort of big security concerns that we have when we're designing smart contracts. So now it's time to move on to our advanced DeFi introduction. So we're going to introduce the idea of perpetuals, and then we're going to talk about, what does mission 1 look like? What do you have to do for mission 1? And we're going to go from there. So enjoy the introduction to perpetuals. All right, perfect. So first mission here is, of course, the introduction to perpetuals. So some of you might already be, really pretty familiar with perpetuals. Some of you might not be, but I'm at least 80% sure that none of you have built your own perpetuals DeFi protocol. So unless somebody has, then this should be a first for you guys on that front. So basically, we've got, with every mission, we'll have, the motivation for, why we're doing this written up here. And so obviously, this is going to serve you well to be very well versed in perpetuals, have a deep understanding. And like I said, throughout the 4 weeks, we're going to continue to build on this idea, build on your protocol that you're going to be creating. And in this first mission with your partner, you're going to be building a few of the basic pieces of functionality for this Perpetuals protocol. And so with each mission, you're going to have, goal and deliverables. And I guess we should add a sort of like completion date, just to be clear. And this will be completed by next Monday, which is the 25th. And of course, if it turns out that this ends up being way too much to get done in a single week, we can adjust as necessary. If it's a little bit less, then we'll throw in some extra side quests to make up for that. So next Monday, the 25th. And I guess that should really be the 25th, to be specific, the 25th before our session on the 25th, which is 1 p.m. EST. Okay, and then of course, if you're finding that it's a little bit too much work, then definitely reach out. Feel free to DM me about anything in regards to the course. So there's a completion date, and the basically deliverables for this first mission is going to be essentially 50% of the basic functionality of a decentralized Perpetuals protocol. Now, if that sounds a little bit daunting, it should a little bit, but it shouldn't seem like it's anything absolutely crazy. So it doesn't have to be like a GMX v2, which has over 10,000 lines of SOC. I went ahead and I implemented this first mission myself over the weekend, and mine ended up being, I think, literally around like 200 lines. So it really, as long as you're being, smart with the way that you're using libraries and existing opens up on contracts and things like this, then you'll be able to do it, quite reasonably without, 1,000 lines of solidity or anything like this. So for this first mission, we're going to have, first of all, protocol name. This is the most important part. You guys will come up with a protocol name, and we'll get you guys set up with team directories so that you have just an area to chat with your partner. And yeah, you guys can decide on a protocol name, and then we will have the smart contracts. So you might choose to have several smart contracts with your design, and I'm purposely leaving this whole idea of what the design should be and how particularly it should be implemented. I'm leaving that open-ended because this is going to be very much for you guys to sort of, first of all, ideate, come up with your own design, see where the pros and cons lie. And this is that part of beginning to understand, exactly when I look at a smart contract system, seeing, okay, why was this designed that way? Or, this was probably a poor design decision on their part. And this will start getting you guys, that initial sort of, code smell sense. So we're going to have the following functionalities. Liquidity providers can deposit and withdraw liquidity, and we will cover what all of this means in just a second. And then you're going to need a way to get real-time price of the asset being traded. Traders are going to be able to open a perpetual position for Bitcoin with a given size and collateral. Traders can increase the size of a perpetual position. Traders can increase the collateral of a perpetual position. Traders cannot utilize more than a configured percentage of the deposited liquidity. We'll get into why this is important. And then similarly, liquidity providers cannot withdraw liquidity that is reserved for positions. So if none of that makes sense, that's perfectly fine. We'll come to an understanding of all of these things in just a second. And then you'll have just a README that gives a high level of how does the system that you designed work, how does a user interact with it from a smart contract point of view, what actors are involved, is there a keeper, what is the admin tasked with, what responsibilities do they have, and then what are the known issues, what are the known risks, and then if you have any mathematical formulas, there shouldn't be anything really complex, but any type of formula that's used, that should be documented in the README as well. So in terms of delivery, before we start to discuss the details or anything like this, what you'll do is you'll just create a GitHub repo. You will add your partner to it, and you guys can just commit to this repo and add me to the repo as well. Commit to the repo throughout the week, and then basically just have these functionalities with this README committed in that repo, and that is basically the quote unquote submission. And then we will see exactly what the next steps are with what you've created in the next mission introduction, which is on next Monday. So is everything clear on what the deliverables are and how exactly you're going to achieve that? Do you have any questions based on that?
So how are we going to evaluate the mission success? Basically, are you just going to look at the repos or how?
Yeah, so you, at this point, you're just going to have access to just your repo, and you're not going to be able to see other folks' implementations just yet. And the evaluation of how good the implementation was, how well it was designed, you guys will see in coming weeks how that is going to be done. So that's going to be a little bit of a surprise. But in terms of just getting them in for this first mission, just having all this implemented in a repo is sufficient. And then the actual evaluation we will get to, and that will actually be a future mission. So does that answer your question?
Yeah, perfectly fine. Thanks.
Okay, great. All right, so if there are no other questions on the timeline or the deliverables or anything like this, we will go ahead and get into the details. We're going to do just a high-level overview of Perpetuals, and then of course answer any outstanding questions. I'm sure there will be a decent amount of questions just based on the introduction, and then of course if there of course things will come up as you're implementing this. I'm going to we're specifically not telling you everything that there is to consider. There's a few things here that are a little bit tricky to figure out when you actually go to implement this, that you're just going to have to consider for yourself, and we're intentionally leaving that out. That's for you guys to sort of bounce ideas off of each other and go and have a look at other perpetual implementations and see how this might be solved. But of course the office hours are here, and we have our first office hours tomorrow for you guys to come and get feedback on your approach or ask questions that you have and things like that. So without further ado, let's just get started by giving a brief introduction for what perpetuals are. And I know we've got a financial analyst in the call, so he can let me know how to do it. But so perpetuals are essentially, just to really simplify them, they're just a way for a trader to be able to bet on the price of a certain index token without actually buying the token, while enabling the trader to employ leverage. So what does that mean? That means that I can take a certain amount of collateral. So let's say if I just want to use 10 DAI of collateral, and I want to use this collateral to borrow from, let's say the protocol is here. I want to borrow $50 of value. I want to borrow $50, and I want to long Bitcoin. So what I'm going to do is I'm going to take those $50 and I'm going to buy Bitcoin. So this will translate to 0.00, I don't even know, some amount of Bitcoin. So what I've done here is I'm staking down this collateral, saying this is the collateral that backs my position. And now based on the amount of collateral that I've put down, the protocol is crediting me with $50 of which I used to buy Bitcoin. So if the price of Bitcoin goes up, and let's say Bitcoin, this amount of Bitcoin, it's originally worth $50 because that's what I bought it for. Now if the price of Bitcoin rises, maybe this amount of Bitcoin becomes worth $60. Now what I can do is I can close this contract. I can close this position. I can say, okay, cool. I borrowed $50 from you and I bought Bitcoin, and the price of Bitcoin rose, and now this Bitcoin is worth $60. So how about I completely close this out, I sell the Bitcoin, get the $60, I give you, the protocol, back $50 plus, maybe some fees, but we're going to ignore those for now. And then I have $10 left over. So minus 50, we're going to have $10 remaining. So with these $10, that's all mine, right? So I just get to take the $10, that's profit for me. And then of course, I closed out my position, so I also reclaim my collateral that I put down. And so I get the 10 DAI, and I walk away with basically $20, right? So what happened is I opened this position, the price of Bitcoin went up, and I made $10. And I never actually had to put down $50 to buy that Bitcoin. In fact, I only had to put down $10, but I was able to command $50 worth of Bitcoin. So what I was able to do here is have leverage. I had 50 divided by 10 equals 5. I had 5x leverage on my collateral. So this is really at a high level. This is everything there is to know just about, what is a perpetual position in general. And of course, why is it called perpetual? Is because I can have this thing open for a perpetual amount of time. So if I want to, let's just start a new trade here. If I want to put down that 10 DAI, and then the protocol gives me $50 of credit for that, and I go and buy, if I go and buy that same amount of Bitcoin, 0001, I don't know if that number is accurate at all, but something like that, I can just keep this nominal amount of Bitcoin for any amount of time, right? This is why it's perpetual, right? I choose when I want to close the position. So the price of Bitcoin can go up, it can go down, and as long as my collateral is sufficient to keep the position open, then I can keep the position open. I can close it whenever I want to. So that brings up a question. When is my collateral not sufficient to keep this position open? Well, let's say the price of Bitcoin goes down, right? What happens if I take this $50, I put it into this amount of Bitcoin, and then the price of Bitcoin goes down such that my collateral is now worth $41. So Bitcoin went down almost 20%. So now, from the protocol's point of view, if I close my position right now, I have realized a loss of negative $9. So what does the protocol need to do to recoup this $9 that was lost? Well, they need to take that from my collateral. So they need to take 9 DAI of my collateral. Now the effective leverage of this position right now, I have effectively 1 DAI of collateral after the P&L, which is this profit or loss, which is what this is. After this P&L is accounted for, I have 1 DAI remaining. So my effective leverage right now is the amount of, the value of what I borrowed, which is $50, divided by the value of my collateral, which is $1. The value of my collateral after the P&L is accounted for. So over here my leverage was 5x, $50 divided by $10. Over here my leverage is 50x. It's a lot more leverage. And so what the protocol will do is they'll define, almost an arbitrary amount of leverage where they're saying, okay, this leverage is too much leverage. We need to close your position. So let's say that amount of leverage is 20x. They're saying, if you give us $1, the maximum amount of leverage that we're going to allow you to be credited with is $20. Now, I'm over this threshold. So what happens when you go over this 20x threshold is the protocol needs to liquidate you. They need to automatically close out position. So what we do is they will, ideally the position won't even get to 50x leverage. It will be closed sooner, but let's just assume that we are able to get to that point. What's going to happen is we're going to close out this position. It's going to, basically force close your position for you. We're going to settle this $9 in losses. The protocol is going to collect that 9 DAI, and then there's going to be, more often than not, a liquidation fee that comes with that. So in this case, the liquidation fee might be 1 DAI, for example. So then that additional 1 DAI is going to go to the protocol as well. And so what I'm left with as a user after all of this is 0. So basically, I had this perpetual position open. I kept it open as long as I wanted until I was in so much loss that the amount of collateral that I had was not sufficient, and then they force closed my position for me, and they took an extra fee of 1 DAI. If they didn't take that extra fee, then I'd be left with 1 DAI after all of this. But they took that extra fee, and so my position is closed. The protocol remains solvent. There's no bad debt, which is basically what's called when if I'm able to basically open a position and I don't have enough collateral to cover my losses, then that would be considered like an insolvent liquidation. Now, we have a few examples and stuff that we can go through to understand, how's the P&L calculated and stuff like this, which will be useful for when you're going and implementing some of these things. But do you have any questions based on this initial stuff, or is this is everybody, is this all basic stuff for you guys?
No,
it's basic, but I think it's clear.
Okay, great.
Yeah, I agree. This is new stuff for me, but it's very clear.
Okay, that's awesome to hear. Yeah, I don't want to be going over just boring stuff that you guys already know. So that's good. Yeah, and this is what a lot of DeFi protocols look like, right? Is it some financial instrument like this? This is what Perpetuals looks like. Some of them are like we just audited an options protocol, or something like this. So a lot of protocols in the space are like this, just understanding the basic financial instrument and then going and understanding how that gets translated into smart contract code.
Can I ask a question really quick?
Yeah, absolutely.
So this threshold, like the 20x and stuff like that, is that when, because I noticed in some of them, I've read over some code over some different type of DeFi protocols or whatever, but they would say something like there's a 80% or a 70% threshold. Is this similar to what that means?
Yeah. So this is a different way of looking at basically the same thing. So if we're talking about, of course, you have Aave, which is a lending protocol, and they have a health factor, right? And the health factor is this is taking this same idea out of specifically Perpetuals. Throughout a lot of DeFi protocols, there's this idea of having collateral and then having some sort of borrowed amount. And there are many ways to orchestrate this, right? This is just one way to visualize it, and one way to logically think about it is you have some amount of leverage. Now another way to think about it is having some sort of health factor. So when we talk about like a 80% threshold or something like this, I'm assuming that those protocols are basically saying that if your borrowed amount is 80% of your collateral, so e.g. if I have borrowed, let's say if I have borrowed $8, but I have $10 of collateral, then this is an 80% sort of borrow rate. And this makes sense for some protocols, like a margin protocol or something like this. When you're borrowing things on margin, they're actually giving you those tokens. And so this 80% is a lot more conservative than what you're able to do with perpetuals. But this is basically what they're saying. They're saying, borrow this 8, then this is the maximum we're going to give you. So we're not going to allow you to straight up borrow 10. So for every collateral token you put down, you're not going to be able to borrow all of that. You're not going to be able to have 1. That's a utilization rate of 100%. So that's where we hear about, all of these different protocols that are over collateralized. When you're over collateralized, the denominator here, which is your collateral, is greater than the numerator, which is your borrowed amount. And the reason things have to be over collateralized when we talk about things like Aave is because all of these are actual tokens on chain that have to be settled in a way that smart contracts can literally enforce, and it will always be solvent, or else you get issues with the protocol doesn't work if you can easily become insolvent. So the only way I can guarantee that I'm able to give somebody 8 tokens and let them walk away with 8 tokens is if they put like 10 tokens into the protocol. And so then I have the choice at any given time. There's a safe window or barrier or buffer where if the price of their collateral drops, there's some liquidation event or something like this, I'll still have a good sense of confidence that I'm going to be able to liquidate them in time. I'm going to be able to get that liquidation transaction through in time to where I'm always going to be able to seize $8 of whatever their collateral is in order to cover the $8 that they borrowed, because they're not going to be giving me the $8 back. They're just going to get liquidated and we're going to take their $8. So this is, I think, what the 80% would be referring to in whatever protocol that is. I'm guessing it's a borrow lending protocol or something like this. But does that answer your question? Or you have any other questions based on that?
No, thank you. That makes sense. Thank you.
Okay, cool. And to add to that, the reason that we're able to go like 20x, which is like way more, like fundamentally, here we had to be over collateralized. The denominator had to be bigger. Here, the denominator is smaller. And the reason for that is we're not actually giving people these tokens, right? This is all sort of like virtually happening. Like there's no actual transfer of tokens under the hood here. We're just crediting people with these $50 size positions. We're not actually going and like literally buying the Bitcoin here. We're just tracking the price of Bitcoin. We're saying, okay, if this person if they did have this amount of Bitcoin, what would that amount of Bitcoin be worth currently? And then what we're saying is, okay, take what that's worth currently, compare it to the amount that they originally put into it, and we can figure out their P&L. And so this is a good transition to talk about, how is the P&L calculated? So we can go here and let's have a look. First, let's talk about directions. So we'll go to a new area. So there's long and there's short. These are the two different types of positions that you can open. When I am long, I am basically betting that price go up. Price of what? Price of the index token or the index asset. It can be anything. It doesn't have to be necessarily a token. In our case, it will be a token. So the index asset is just a thing that people are betting on. When you're long, you're betting that number go up. When you're short, you're betting that number go down. And that's really all it is. Now let's walk through just some basic scenarios to see how each of these long and shorts behave. So we've got a scenario for longs laid out here, and we've got a scenario for short. So the current price of ETH is $5,000. So the index asset is ETH, and it's worth $5,000. Should be worth $5,000 anytime now. One day you're gonna wake up and it's gonna be $5,000. Could be tomorrow. So it's $5,000, and what Bob, our trader, does is he comes and he opens a long. Now this is going to be important to just have over here the max allowed leverage. Max leverage is 15x before you get liquidated. That's just something we'll put up there on the side for now. Bob opens a long position with $1,000 of USDC as collateral and $10,000 of size. That is basically dollar value borrowed from the protocol to buy ETH. So what happens here is he's got a collateral amount, which is basically 1,000 USDC, which is hopefully also worth $1,000. And he's got a position size in dollars of $10,000. So if we translate this back to how we were drawing this out earlier, what this looks like is the protocol is here. Bob puts $1,000 of USDC down as collateral, like this. That's his collateral, and he borrows from the protocol $10,000 of size. We're going to refer to it as. So he borrows the $10,000, and then he buys ETH. This is what a long is I borrow that amount of money, and I buy Ether. So the current price of ETH is $5,000. We're going to ignore slippage or price impact or any of those ideas, and you can ignore those when you're using oracles. So this is going to turn into 2 ETH, right? So $10,000 divided by $5,000 gives you 2 ETH. So this is the size of his position in tokens. His original size is $10,000. The size in tokens is 2 ETH. So let's add that. Okay, let's see what happens next. Okay, so we can compute his leverage. So L equals $10,000 divided by $1,000. So his leverage is equal to 10x. So this is a quote-unquote healthy position. It's below the max leverage of 15x. So there's no need to liquidate him at this point in time. Okay, so now the price of Ether moves. We're going to see what happens. So now ETH goes to $6,000. So it increased by 20% from where we previously were at 5,000. So now what we do is we can go ahead and we'll copy these things and we'll go through each of them. So the collateral is still, provided that USDC hasn't depegged or anything like this, his collateral is still worth $1,000. His size, this is his original cost, like the amount that he borrowed from the protocol is still $10,000. He's still just borrowed that $10,000, that remains the same. The size in tokens also remains the same. We're going to add one more thing here, which is the value of the position. So the value of his position originally here is 2 ETH multiplied by the price of ETH. So the value of the position when he first opened it was $10,000. That's how much his 2 Ether in his position was worth. Now he still has that 2 Ether, but 2 Ether is not the same amount of dollars. Now the value of his position is $12,000. It's this 2 ETH times the current price of ETH. So we can calculate his P&L in the following way. So P&L is basically how much money did you make or how much money did you lose. So Bob is long, so his P&L is going to be positive. He's in a profit because the price of ETH went up. So the way we're going to calculate this is current value minus basically the cost, or you could say the borrowed amount, really his size, right? So what this is if we add numbers to this, the current value we just computed is $12,000 minus the borrowed amount, which is his size, which is $10,000. So I borrowed $10,000, it turned into $12,000, and I made a profit of $2,000. So that's his P&L. So at this point, Bob can choose to close his position. And when he closes his position, he'll return this $10,000. He'll sell his ETH, virtually. He never actually received this ETH. It's just being sort of internally tracked and credited towards him. Of course, it's up to your implementation, but definitely you don't want to actually be transferring tokens. So what they're going to do is they're going to pay back the $10,000 virtually, and essentially he gets to walk away with $2,000, all said and done. That's his profit. So if he chooses to close his position at this time, again, he doesn't have to. He can close it at any time. He'll get his collateral back, so he'll get his $1,000 of USDC, and then he'll get $2,000 back in, probably, it would get paid out in USDC or, however the protocol is implemented. But he'll get that profit back. And notice that his leverage is the same. It is fundamentally the amount that was borrowed divided by the value of the collateral. Now if USDC depegged and the value of the collateral goes down, then his leverage will increase. Or if he's in loss and there are losses that need to be paid out from the collateral, then this denominator will decrease and his leverage will go up. So let's have a look at that scenario, what it looks like when there are losses. But before we look at losses or anything like this, does this scenario thus far make sense? Are there any questions based on that?
Looks great to me.
All right, awesome. So we'll go ahead and we're just gonna erase this so we can continue. Bob does not choose to close his position. He's greedy. So even though he's on paper made $2,000 of profit that he could realize if he closed his position, instead he's going to leave his position open because he's still bullish on ETH. He thinks that Ether is going to go to 20K. So of course what happens is Ether does not go to 20K. Instead, ETH falls to 4750. So he swung all the way back down to below even the original price that he got in at, that he opened his position at. So what we'll do, copy this, all of these. Now his collateral is the same, provided that USDC is still worth $1. His size is the same. This is still the same amount that he borrowed from the protocol. Size in tokens, still the same, 2 Ether. But the value is no longer $12,000. In fact, it's no longer $10,000. It's now $9,500. So on each of his 2 ETH, he lost $250 each relative to what he bought in at. So what we're going to do is we calculate the current value minus the amount borrowed, and now he's sitting at negative $500. That's his P&L. So he's lost $500. Now what we need to do is factor in this loss into this denominator. So this becomes $10,000 divided by $500. His leverage is now 20x when you factor in the losses that need to come out of his collateral. So at this point, he has gone over this max leverage threshold. And so what's going to happen is he's going to be liquidated. And so what will happen is he pays back this $500 in losses, and he will just get back what is remaining out of his collateral. So he'll get $1,000 minus $500 minus whatever liquidation fee there is. So we'll assume that the liquidation fee is just 0 for our purchases here, and he's just going to get $500 of USDC that he originally put in. He'll get that back. Usually the liquidation fee will be, some X percentage of the collateral or the borrowed amount or something like this. Now it's also worth noting that when you're in profit, depending on the protocol design decision, the profit might be included in this as well. So when he's in $2,000 of profit, depending on the protocol, they could say that, okay, well, you're in profit, so if we did have to liquidate the value of your position, that $2,000 would go to cover the collateral, so you would be in fact $3,000 in this denominator. And that's sort of, I mean this is open to implementation, so you can kind of decide exactly how you want the protocol to behave when it comes to these things. Now, one thing that's interesting when you do add this feature is that if I'm able to have this, this P&L count as collateral, well, there's not actually any tokens backing this P&L. And so what it enables somebody to do is to have a position that actually has zero collateral, zero actual collateral. And as long as they're in profit, then they can't be liquidated. And so that might be fine. This is actually the case for GMX v2. You can have positions that have no collateral as long as you put some collateral in to start, and then you get into profit, and then you remove your collateral. It's possible to have this, but it's a risk that needs to be at least thought of. So that is, some sort of implementation detail. Like there's no specific EIP for this is how you implement perpetuals. Things like this can differ protocol to protocol. But are there any questions on this liquidation case or anything like that?
Yeah, I have a question about the last thing you spoke about. So GMX is one of those where you can count the P&L towards the denominator in the leverage. Is there any examples of protocols that does not do that, basically keeping the leverage based on the initial collateral instead of and only counting it, I guess, when there's a loss?
Yeah, I believe PeriFi is one such protocol. I don't think their code is public just yet, so unfortunately, yeah, there's no actual code to look at, but that is one such protocol. That is the only one that I know of, but it is, it's a design decision. It can work either way. So yeah, it just has to be thought of in terms of if you do have zero collateral in a position, you've got to be careful, because if the price of the index token swings and all of a sudden that $2,000 of profit quickly becomes only $100 of profit or maybe even a loss, then you're going to have an increased risk of having positions go quickly insolvent in that there's no collateral to actually back those losses. And so the protocol then has to take on those losses themselves. So it's really just a matter of, can we have, keepers that are going to be responsive enough? Are we going to be able to get these transactions through in time? And have we configured the leverage constraints such that there's a sufficient buffer between when a protocol has profits that can back, any fees or anything like this, and between them being actually insolvent. So yeah, does that answer your question?
Yeah, absolutely.
All right, cool. Anything else that could be clarified on the liquidation case? Cool. So we've gone through all of that. Let's now have a look at shorts. So how are shorts longs?
Sorry, I guess I have one.
Yeah.
So if we're looking at the position when ETH went to a loss, so I'm guessing so now we're comparing a stablecoin and ETH, but is it so that basically the leverage can differ if either the price of ETH goes down, or I guess the other token as well, right? If it would be like ETH to BTC or something like that. So it can be quite complicated.
Yeah. So the collateral can be, it doesn't always have to be USD. It can also be like BTC, like you're saying, or it can be ETH. And you can even have, in a position that is long ETH or short ETH that is backed by ETH. And so if the price of ETH goes down, then the value of my collateral goes down because my collateral is in Ether. And then if the price of ETH goes down, obviously that affects my P&L if I'm betting on ETH itself. In terms of, valuing things, if you're looking at like ETH BTC, it's certainly possible. I think the most straightforward implementation is to value everything in dollar denominated, and then that way you can calculate the P&L, just very straightforward. Like, okay, when it was in, when you borrowed this dollar amount, and then now it's currently valued at this dollar amount. Did I understand your question?
Yeah. I'm basically just trying to think about how the prices can move, basically. But
yeah. So the price of your collateral token certainly affects things. It affects the amount of actual value that's backing your position, and then of course the value of the index token affects things. And those two tokens can be different. They can be the same. So, and I mean that definitely, it depends on whatever the protocol would choose to implement. But in the case of the vast majority of perpetual protocols, these can be, well, actually in a lot of protocols like PeriFi, I think the collateral has to be in USDC. But in GMX v2, the collateral can be in ETH as well, depending on the market. But that's getting more into the specifics of their implementation. All right, cool. So if that is clear, then we can move on to shorts. So we're going to start off with basically the same situation. ETH is at 5,000, max leverage 15x, and I'm going to go ahead and just copy this. And so we have our same trader Bob. He's going to put down $1,000 of USDC. Same size, $10,000. Same size in tokens. And the value when he first opens it, if you've got 2 Ether, the value is going to be $10,000. And so his P&L, we can make this a little bit bigger. Or I'll just zoom in. So his P&L for shorts is going to be a little bit different. So for shorts, we're betting that the price of the index token, ETH in this case, goes down. So instead of taking the current value of the position minus the borrowed amount, we're going to invert it. We're going to take the borrowed amount minus the current value. And so what this is saying currently is, okay, you borrowed $10,000. It's currently worth $10,000. Your P&L is $0. You're not in a loss. You're not in a profit. You just opened the position, and the price of ETH is at the same point when you entered. And then his leverage is still 10x because he's got $1,000 of USDC and he's borrowed $10,000 and his P&L is 0. So let's see what happens next. ETH moves down to $4,000. So we've got another 20% move in the opposite direction. So let's see what happens here. So collateral is the same. USD price has not moved. Size is the same. Size and tokens is the same. Value, $8,000. P&L is still the same formula, only the current value is $8,000. So we do $10,000, the borrowed amount, minus the current value, $8,000, $2,000 profit. So do you guys see how for shorts, when the current value of your position goes down, you actually profit? So we're betting on the price of the index token going down. And then the leverage is, of course, the same, unless you chose to factor in profit into leverage, in which case it would be something like 3.33x. But yes, so this is the profit case for shorts. The price went from 5,000 to 4,000. We made money. Now what happens if the price of a short goes to 5,250? So I could have closed my position. Bob could have closed his position right now. He could have realized that $2,000. He could have walked away with profit. But of course, Bob's greedy. And the price of ETH rises. So let's see what happens here. All right, same collateral, same size in tokens. Value, however, is now 10,500. 2 times the price of ETH equal to this. Now the current value of his position is 10,500. So his P&L is negative $500. So we take that negative 500, we factor that into the amount that's veritably there, able to back his position, and we now get 20x. So we're above the max leverage threshold. So what we do is we go and we force close his position for him, we liquidate him, we go ahead and take his $1,000 USDC collateral, we subtract his $500 of losses, we subtract a liquidation fee, which we'll say is just 0 for now, and we walk away with $500. So to be explicit, the protocol gets $500 of his collateral to cover the losses. They also get, whatever the liquidation fee. If the liquidation fee is 0, Bob gets $500 of his collateral back. So this is the same exact mechanics for liquidation as in the long case, just inverted in terms of if the price goes up a certain amount, they'll get liquidated. Does this all make sense in terms of shorts?
Yep, it does.
Cool. So this is perpetuals. That's the whole thing. That's, you can borrow a certain amount from the protocol, get a certain amount of size, and if the price of the index token changes, you either make money or you lose money. If you lose too much money, you're going to get liquidated. And that is essentially the long and the short of it.
Just one question. Is it possible to hedge a position in the short side? I mean, by depositing instead of USDC and shorting it, because if price of it decrease, we are making losses, and if we short it, we are making profit. So is it possible to do this kind of strategy by depositing it instead of USDC?
Absolutely, yeah. I mean, well, it depends on the protocol implementation, what they want to allow users to do. So, like, in terms of something like PeriFi, again, I think they only accept collateral as USDC, but in terms of GMX, you can, depending on what the market is, you can choose to, okay, I want to short ETH, but I want to have ETH as my collateral. And that way, if the price of ETH goes up, then the value of my collateral goes up, but the P&L in my position goes down, right? So yeah, that's an interesting strategy that people can use, again, depending on what the protocol implementation is. But yeah, that is something that could be supported.
Yeah, very interesting.
Okay, fantastic. So that is the mechanics from the trader point of view. So we know all about traders now. Traders are the actors who are opening these perpetual positions, and they're betting on the price of the index token. They profit when the price of the index token moves in the direction that they predict. So longs, when the price moves up, they profit, and longs, when the price goes down, it moves in the opposite direction, they lose money. And then inversely for shorts. And then traders must provide collateral for their position. The collateral is used to cover their losses in the event that the price moves in the opposite direction of what they predicted. So the next thing that we haven't really talked about is liquidity providers. So these are the people who enable all of this to happen. Where are the people getting this, size of dollars from? Well, remember, we have to borrow money from the protocol. So the liquidity providers essentially act as the protocol. So when a trader comes and they say, hey, I have this amount of collateral, I want to borrow this amount of size, the liquidity providers are the ones that are not literally giving you those tokens, but they have provided an amount of value that's backing the virtual loan that you're getting when you take this $10,000 of size. So why do we need this backing value? Well, when a trader is in loss, they have to pay this loss from somewhere. And where do they pay it from? They pay it from the collateral. But when a trader's in profit, they get money from somewhere. And that actually materializes into an amount of tokens that might be USDC, it might be Ether, some amount of tokens that get sent to their EOA after they close a trade. So where does that money come from? That money comes from the liquidity providers. So in these cases where Bob profited, he profited $2,000 here, he profited $2,000 here. If he chose to close his position at that point in time when he was in $2,000 of profit, the liquidity providers would be giving him that $2,000. So why on earth would you just provide liquidity to pay out these people when they profit, right? Well, you have to understand that when traders trade and they use a lot of leverage, so if I use 10x leverage, there's a good chance that I'm going to get liquidated. And when I get liquidated, those losses get paid to the LPs to, balance that out on top of a liquidation fee. And then, of course, there are other fees like opening fees, closing fees, borrowing fees, and things like this that we're not going to get into just yet. But basically, as an LP, when traders lose money, you make money. And even if traders don't lose any money and they don't make any money, you're still going to collect fees. And there are tons of different fees. But when traders make money, you are going to lose money because you're you're paying those profits out yourself. You're still going to collect fees no matter what. So the general idea and the thesis of being a liquidity provider for a perpetuals exchange is that people are going to suck at trading and they're going to use way too much leverage and they're going to get liquidated and they're going to make bad trades and they're going to lose money overall, which is actually a winning thesis on average. And then you add the fees on top of it and it's not a bad idea, depending on what your risk sort of appetite is. So that is the allure of becoming a liquidity provider and putting your funds up to be able to pay out these trades. And again, just to make it very clear, the money that liquidity providers put up is only necessary, it's only used when a trade is settled in profit. So there's no tokens being shifted around here, at least in a good implementation. There's no actual token transfers that are happening in terms of, crediting someone with $10,000. That is all happening virtually. And then when a trade is settled, that's when the money starts to move. So if you settle in a loss, then the trader's over here, you settle in a loss, then that loss comes out of their collateral and it goes to the LPs. Maybe the LPs are a different contract, maybe they're in the same contract, depends on whatever your implementation wants to be. And maybe this is, okay, I'm not gonna go into specific hints on implementation or anything like this, but if a trader's in a loss, they're sending money, they're sending tokens to the LP, they're sending their collateral tokens to the LP. If a trader closes a position at a profit, LP is sending tokens to the trader. So like we have here, liquidity providers take the opposite side of traders. They stand to profit when traders lose money or are liquidated. They also often collect fees. They provide the assets that are used to pay out profit. When a trader profits, they get tokens from the LPs. When a trader loses, they pay tokens to the LPs out of their positions collateral, which has been, collected and sent into the protocol when the trader initially opens their position. So just an important note here, for mission 1, you're not tasked with implementing any sort of fee logic or handling any type of closing a position or settling profits or losses, but it will be helpful to think about what this might look like. So before we go on, we're almost have covered everything here. Before we go on, are there any questions on liquidity providers? Okay, so let's just talk about open interest for a second. So open interest is just a measure of all of the open trades, all of the open positions that are, open on the exchange. So for example, if I have trader A, gotta figure out how to zoom in here. All right, let's say I have trader A, and they open a long and they borrow $50,000. Okay, maybe I have a trader B, and they open another long, $25,000. So this is also a long. And then let's say trader C, they open $60,000, but this is a short. Okay, so there's an amount of total amount that's borrowed or set aside for longs, then there's amount that's set aside for shorts. This is open interest. So there's 75 open interest. So what's the interest in longing that's open? 75,000. And then the quote unquote interest for shorting, 60,000. So open interest. And then the net aggregate open interest of the protocol as a whole is $135,000. And so this is just a way to measure, okay, what is the net aggregate amount that has been loaned out by the LPs virtually? What amount is being borrowed in general? And specifically for your implementation, so I'll give you a hint of something that I think will make your life a lot easier when you're implementing this. You will want to, first of all, measure the open interest, which is this aggregate USD amount that has been borrowed. And you're going to increment that by the size when each individual position is initially opened, and after they're opened, if a trader chooses to increase the size of their position, you're going to increment that as well. You're also going to track open interest in tokens. This is going to make calculating the net P&L of the entire protocol very easy. So why are we going to do this? Let's say this trader, let's say this is all for ETH. We're just going to talk about just supporting one index token at this point. So ETH is $5,000. This is 10 ETH. This is 5 ETH. And then this is, he's shorting, so this is 12 ETH. It's all the same size and tokens calculation. So the total open interest for longs in terms of tokens is 15 ETH. Now if I have these two numbers, what I can do is I can very quickly calculate the net P&L of longs, no matter what the price goes to. And I don't have to loop through all positions and check the P&L of each individual position, which, as we know, is a terrible way to design smart contracts. You want to avoid for loops as much as possible. We'll be talking about this tomorrow. What I can do is, if the price of ETH goes to $6,000, now all of a sudden, we can use the same exact formula for calculating P&L for longs, and we can say, okay, what was the current value of the position? Well, it's $6,000 times 15 ETH, which is $85,000, I think. 80? 90. All right, $90,000 minus 75,000 equals 15,000. This is the net profit of all of the longs that are open. And this is going to be very useful to be able to calculate for your protocol for determining how much can we afford to lend out, when does this market become insolvent or something like this, things that we're going to get into later on. So this is why you want to keep track of the open interest in tokens of each side. And you can do this for shorts as well. We'll just do it for shorts really quickly. So there's this 12 ETH. This is the net open interest for shorts. Now we have this price of $6,000. We're going to use the formula for shorts for P&L. So $75,000, the amount that we borrowed. Sorry, this is actually $60,000, the borrowed amount, and minus the current value of the position, which is 12 times 6. So negative 12,000. And so this is important for determining how much is the pool currently worth. So we add these two together. Traders in aggregate are only $3,000 in profit in general, if you sum these both. So when we talk about LPs, when they put money in, if LPs have provided a net amount of $100,000 worth of value, but traders are currently up $3,000, then the net value that belongs to LPs is not what they put in, it's $97,000. And it's very important that this is tracked in real time. What do I mean by this? I mean that whenever somebody deposits and withdraws, you need to be able to compute what is this net value. Because if you just rely on what is the amount that is currently actually sitting in the LP fund, then you're missing a crucial piece of the equation, which is, well, what traders are we pending having to pay out, and what traders are we pending have yet to receive their losses? And if we don't account for that, then you're going to end up with a situation where if this is the pool value and this is time, you end up with these stepwise jumps. Now, throughout your analysis of protocols, as you go on and move on to look at other things, stepwise jumps are almost always a bad idea. This is because of front running and back running. So if I see that a stepwise jump is about to be incurred, I can front run that. And I can deposit when the pool value is at this level, and then I can withdraw when the pool value is at this level. Risk-free profit. So what incurs these stepwise jumps? If you're not tracking it in real time, it is a trader closing their position. So if I close my position in a loss, the pool value for liquidity providers immediately goes up. That amount gets paid out to liquidity providers right in that instant. So what we need to do is we need to track it in real time. And whenever somebody deposits, we need to compute the current value of the pool. So instead of doing this, it would look something like this. Maybe it does this. It depends on the price of the tokens, whatever the tokens do. And, maybe it does something like that. And so now, at whatever point that you deposit withdraw, there's nothing sandwichable here in this smooth line. So that's why at any given instant, we need to be able to know what's the net value of the liquidity pool. So I know that's, maybe a little bit confusing at this point. You probably need to, get some time to think about this model and dig in and see exactly what that will look like in code. But there are any initial questions on that aspect? All right, cool. So yeah, once again, completely expect that this is not all going to be 100% straightforward to start out. You're going to have to think about perpetuals. You're going to have to think about how you want to lay this out and design this. But this is one key sort of design consideration that you're going to have to figure out how to solve this problem. Okay, so with that, we'll move to the final thing here, I promise, is liquidity reserves. So there's this idea of having a certain amount of collateral, and if you lose money on your trade, then if you go over this max leverage, you're going to get liquidated. And that's going to be in place to keep the system as a whole solvent when traders are in a loss. But what about when traders are in a huge amount of profit? What if a trader buys Doge and Doge goes up 50x? And there's literally not enough profit to pay out for that trader to get their profit, right? To actually realize that. So to address that partially, what there's needs to be implemented for several reasons is a reserve sort of validation. So what we need to do is we need to make sure that we're going to limit how much open interest traders are able to open, right? So if I've only got $10 in liquidity reserves, so liquidity providers have only given me $10, there's no way that I can allow a trader to open a position with $10,000 of open interest. Because then what's going to happen is if the price, let's say it's a long, if the price of whatever they're longing goes up even a little bit, well, they're probably going to make more than $10. But if I make more than $10, then where's the money going to come from, right? The transaction is probably going to revert because there's not enough tokens to send to you to pay that out. So that's an issue. So we need to limit, based off of the amount on the LP, limit the amount of open interest that can be opened. And so here are, a couple potential formulas that you could use to limit it. So you could just say the total open interest that we're going to allow to be open on the protocol is less than the deposited liquidity amount times some max utilization percentage. That works. That's a good validation. It is somewhat arbitrary and it's somewhat open to whatever configuration you want to add, whatever this particular formula is. So you could make up your own, or you could go with something like this, which is a little bit more advanced. It considers the differences between longs and shorts. So this one will take the short open interest plus the long open interest in tokens times the current index token price, and compare that to the deposited liquidity times the max utilization. What does any of that mean, and why is it split up like this? On a short, you can only ever make as much money as you borrowed. If we go and we revisit the equation for calculating the P&L of a short, then we know that it is the borrowed amount minus the current value. Well, the current value can't go negative, hopefully. I don't think crypto is that bad. So it can, at best, for a short, it can be 0. So you can get the borrowed amount minus 0. And that's the best case for a short. So for a short, you will never have to pay out the trader more than the borrowed amount. So the short open interest is the aggregate borrowed amount for shorts. So we know that that's the maximum we'll ever have to pay out for shorts. In the worst case, that's if the token literally goes to 0. For longs, the formula is flipped. So it's the current value, borrowed amount. Well, the current value can go as high as we want. You know, it can be infinite minus the borrowed amount. You know, technically a token can do an infinite x conceptually. So the way to basically say, okay, well, this is, you know, roughly it's going to track with the maximum amount that we're going to have to pay out to a long, you just get the current value of the position. And that's a decent indicator of, you know, how much reserves should be reserved to pay out all of these longs. And so that's a slightly more complex version of basically this formula, which is just validating that the aggregate open interest on the protocol is less than whatever we're deciding can be supported. And that amount that you decide that can be supported is somewhat arbitrary, and it's not perfect. So are there any questions just based off of liquidity reserves, this validation?
One question for the first mission. Should we implement any swap logic, or should we keep it simple?
Yeah, so definitely as simple as possible. So of course, going in line with, you know, keeping as little code as possible, just whatever is, let me find the notion, like really, it's only like half of the actual logic. There's really not too much. Like, this might seem like a decent amount, but actually I would say aim for 250 lines of solidity code for the contract. Yeah, aim for around that, and try to use pre-written libraries to your advantage. So I guess I'll just go ahead and say that you'll get a lot of advantage from looking into something like an ERC 4626 vault or something like this, and trying to see how that can make, you know, accounting for people depositing a lot more simple. Now, you can't just use a straight up ERC 4626 vault. There's got to be some modifications to it, because we have, you know, collateral that is also in the system. And I mean, you might be able to use a straight up ERC 4626 vault. It depends on if you're using multiple contracts and things like this. But yeah, a 4626 vault for depositors, people who are liquidity providers. That's one thing I would consider. That will save you a lot of lines of code. But yeah, nothing beyond this. There's no fees. There's no decreasing a position. There's no like paying out P&L to anybody. It's literally just, you know, people are able to deposit liquidity to back this, and then you're going to need some sort of a price feed to track the index token, and then a way to open positions. And then if you're, you know, smart about it, usually the function that can be used to open a position is the same function that can be used to increase the size and increase the collateral. And so that way you can get, you know, a lot of code reuse with that. And then just really what these end up looking like is really just a require statement, or, you know, an internal function that does some validation. But yeah, does that make sense?
Yes, completely. Thank you.
Okay, cool. And anything else on the mission, we can go in on that if there are any other questions.
Oh, sorry, could you repeat the ERCs you mentioned? I struggled to hear them properly.
Yeah. So
it's 4.2?
Yeah, so ERC 4626, that will probably be useful to you for handling depositors, people who are providing liquidity, and then that is basically a standard for handling people depositing into a shared vault and then sharing in the profits and revenues that go into that vault. So that is a standard that will likely help you for liquidity providers, because what liquidity providers are doing is they're providing their, their liquidity per se, the tokens, and then they're either losing money if they have to pay out traders or gaining money if they get profits from traders. And so there's a nice way to handle that.
And probably a follow-up question. Imagine you've heard only like the basic ERC20s, 711s, and so on. How would you look for such reusable ERCs? I've never heard this one which you mentioned.
Yeah, absolutely. So Open Zeppelin is a beast. They have, so I mean, you can even see right here, ERC 4626. They have an implementation of this ERC. Most ERCs that are worth anything have a reference implementation by Open Zeppelin. So they actually have a ton of stuff listed here of like, okay, here's ERC 4626, here's Vault. If you want like a ERC 1155, which is like a meta ERC 721 collections or something like this, they also have like, of course, governance stuff and things like this. But yeah, I think usually Open Zeppelin has, always I'm thinking of like, oh, has anybody made a function that's like to convert a string to a bytes 32 thing or whatever, and then you check Open Zeppelin and they have it. So yeah, I think a lot of interesting stuff like this can be found just like searching Open Zeppelin to see what they've got. But yeah, I'll also throw this page up here.
I started it the wrong way because I inherited from the interface of ERC 4626,
yep.
And I started to implement all the functionalities, and it was like 170 lines of code. So for sure, it's too long. So now I'm trying to inherit from ERC 4626
yep.
in order to override some functionalities, since the ERC 4626 only use one asset, and to add liquidity we need two assets, right?
Yeah, so actually you can choose whatever like collateral token you want people to provide, and that can just be the single asset that gets paid out.
Okay.
So for example, there's a number of things in the GMX v2 codebase that are absolutely not necessary for like a basic implementation of Perpetuals. So what we can do is we can choose, okay, I just want to pay people out in USDC, and then we'll only accept collateral in USDC or whatever collateral token you want to use, and that can be the only asset. And so that way there is no, like, you could pretty much conceivably just use ERC 4626 straight up, depending on how that works. Yeah.
Okay. And so a liquidity provider can provide only USDC, and in this case, he is like the counterparty of a long trader, right?
Yeah, exactly. So this just adds considerations for the leverage of a market. So what we have here is the reason GMX they have two different tokens is, there's one token that backs the longs and one token that backs the shorts, right? And so ideally the backing long token is somewhat correlated with the, if longs make money, then this should also go up. Now, since we're just building a really basic like implementation of Perpetuals, we can ignore this for now and just say that, okay, we're going to hope that our validation that we talked about is, strong enough such that there's a lot of buffer room, so that even if Ether does 2x, then we're still going to have enough reserves to pay out. And there is functionality that GMX has called ADL, which is like auto deleverage. to start to close out long positions that are in profit before it gets to insolvent case, because they can still have insolvency. And that could also be used to address this issue in our market when we're still using USDC, but that is not something we have to implement for this mission. But yeah, we can go and use just USDC to back even both longs and shorts, and it still works fine.
Okay, great. It will be easier that way. And one last question. How to choose an exchange rate? I mean, if someone deposits 100 USDC, how many shares he will get? Like if he get 1 shares, how to determine the first exchange rate for the first depositor, the first liquidity provider?
Excellent question. So first of all, the exchange rate in general should take into account what is the current P&L of traders. So, and then we'll talk about what this looks like specifically for the first deposit. But in general, the value of a market, so let's just say or the value of, the LP contract, whatever pool, we're basically saying the LP value is equal to the total deposits. So, what's the total amount that has been deposited minus the current P&L. So total P&L of traders. And so this is the LP value. Now, when we're determining how much somebody's deposit is worth, well, this is what ERC46. So let me just pull up the LP value is these total deposits minus total P&L of traders, right? And so this LP value, this is going to be used to convert an amount that I'm putting in into an amount of shares tokens. So we're going to have a look at, we've got the ERC4626 contract pulled up here. Now we can see anytime we mint, for example, we get assets, and then we go to underscore deposit. Underscore deposit just handles the actual, token transfers and minting and things like this. And we do this, actually, I want to look at deposit. Deposit is the one we want to look at here. So, and deposit and mint are, basically the same thing. You're just specifying this is the amount of assets I want to deposit versus this amount of shares I want to mint, and then they'll determine how much assets need to go to mint that many shares versus the opposite way here. But, so we're going to look at preview deposit, and this is going to convert to shares. So this is what we care about right here. So we convert to shares and we take the assets, so the amount that I am depositing. And then we find this function. Here we are. So it's a function of the total supply, and then you have to worry about decimal stuff, and the total assets in the vault. So the total assets in the vault currently in this implementation, in this generic implementation, this just reads the balance of the contract. If I can find the total assets function, it's just the balance of this. That will not work for us. Instead, we want the total assets, or the LP value. This is basically total assets. We have to factor in the total P&L of traders. And so really what you could do to have like a minimal example is you can inherit from ERC4626 and just override this function. And then they'll handle everything else for you, right? You just have to tell them the total assets is not the balance of this. It's, we'll track the total deposits and then subtract out the P&L of traders. And then for the first deposit, this will basically handle all of the logic for the first deposit and that exchange rate out of the box, following that exact conversion formula, following this, and just going off of what you define for the total assets, which would initially be 0, because there's 0 P&L, 0 deposited, and then it would be a 1-to-1 ratio. And then, it can change from there, depending on what the P&L of traders is. But does that make sense?
Yes, completely.
Okay, perfect.
Thank you so much.
Yeah, then I think, Nyan, does that partially answer some of your guys' questions? I think that I got the gist of your question is it feasible to just have a 1-to-1 ratio initially? Yeah, so that's exactly what would happen if you were to inherit from ERC 4626 here, is you would have total assets of 0 plus 1, and then total supply of basically 0. And then this would basically, so there's a decimal offset. We can talk about this if you guys are interested in going to that. That's the solution that they have for the first depositor inflation attack. But basically, yeah, you will end up with a 1-to-1 ratio.
And basically it will remain 1-to-1 before the first trade.
Yeah, so it will, unless there's any sort of, weird rounding manipulation, which this attempts to protect against with their decimal offset. Besides that, there's no way to get it off of 1-to-1 unless, if a trader, so I guess we could walk through an example. So let's say the total deposits, we'll have that here, and then we'll have the total P&L of traders will be right here. And so we're going to start off at 0, right? Nobody has yet deposited. And then let's say I come in and I deposit 100 USDC. And so 100 USDC goes in the vault, and then my shares of vault tokens goes to 100, right? So initially it's 1-to-1. So this means at this point, let's also put just the LP value, which is a function of these two things. The LP value here is technically 0. And the total P&L of traders, so here it's still 0, no trades are opened. Let's say what happens is a trader opens a long, and let's say that they profit. Let's say they profit $10, so the P&L of traders is actually 10. And actually, let me erase this, because here, of course, the LP value is 100 minus 0, right? So the LP value is 100 here. And by the way, if somebody were to come in and deposit, if we freeze time right here, and we say somebody comes in, they want to deposit plus 100 USDC, well, then they're going to get the total supply. So they're going to get, 100, what they're putting in, divided by the current value of the vault, 100, times the total supply, which is 100. I'm sorry all these things are 100, but basically what that will come out to is 100. This is the amount of shares of the vault token that they'll get out. And ERC 4626 will handle all of this accounting for you. But then, so basically if somebody comes in with 100 USDC, they'll get 100 shares out. But we're not doing that in our example. It's just like if we were to freeze time and that happens right there, that's what happens with that. So in our follow-up, there's now a total P&L for traders of 10. So the LP value, the LPs lose money when traders profit, right? So the LP value is now 90. And so now the exchange ratio has changed. If that same person with 100 tokens comes in and they deposit 100, so the value of what they're depositing divided by 90, the value of the LP pool, times the total supply, they do 100 divided by 90 times 100, they get 111 tokens. So they got more than I got when I deposited 100, because the LP value is literally worth less now, right? So we've technically, at this point, the people who are holding shares of LP value, they've already lost that money that is belonging to that trader, that trader will eventually claim when they close out their position. If you were going to implement this straight up yourself, this logic, it would be like if total supply equals 0, then you can just mint the however much they're giving you, essentially. And so that's the 1-to-1. So I put in 100, I got minted 100 shares, and then else we have this logic here where we go, you're going to mint, and then the amount of shares that you're going to mint is going to be their deposit value divided by, let's make this a little wider, divided by the value of LP value times the total supply. And that's like essentially more or less, of course you want to, worry about solidity division and, probably move this here, but that's essentially what that would look like if you were to just implement it yourself. But of course, open supplements solved all this. But yeah, in this way, so the key to this is that in real time, we are tracking the effect that P&L of traders has on the LP value. And so this way, at any given point, if somebody deposits, they're depositing at the current value of the LPs, taking into account whatever the P&L of traders is at that very moment. And similarly, if they withdraw, so you can't get any situations like this, where I know that somebody's about to take profit, so I can, deposit before and then withdraw after. Instead, it's this smooth, continuous line. But yeah, any follow-up questions based on that?
I have a question. So this is from the within the ERC 4626. You said we would need to override the deposit function and then change the functionality with that, right, to include this total P&L of traders, right?
Yeah, so the way that this is designed, you don't even have to touch any of the deposit logic specifically. What you can do is total assets function, because really the only thing that we're changing about the vault is what is the value inside of this vault. The basic implementation of 4626 says that the value inside of this vault is just straight up what are the tokens inside of this contract. The extra consideration that we have is, well, no, that is the amount that has been deposited by LPs, but we have to remember that some of that amount will belong to traders in the form of if they profit, we have to pay them out. And also on the flip side, if traders lose money, then we'll get extra money. So that's where we have to, like currently the 4626, so 4626 value is basically saying just straight up the value is the total deposits. All we are doing is converting and saying we're going to add in the total P&L of traders. And so we could just override total assets, and that will do that.
Okay, thank you.
I could go with another question. When does it make sense to use the max withdrawal? I don't remember exactly the name of the function, but to limit the withdrawal of the LPs in order to not withdraw shares, not shares, but value which is reserved for traders.
Yeah, 100%. So that's a big part of what this this validation is that we have written somewhere. Yeah, so this part at the end here, this liquidity reserves, this is exactly that. We want to make sure that, of course, if I see that a trader's in profit, I shouldn't be able to just, take all of the money that's in the contract. So first of all, I mean, obviously one thing that protects against this is the fact that that trader's profit is valued into the vault at any given time. So it's not like I can just withdraw that money. It's already been accounted for and being lost from the vault. But another validation that we want to add is on top of that, we want to make sure that if this is ever not true, so if the total open interest, so the total amount of trades, or however you want to define how much should be reserved, is less than the deposit liquidity times whatever configurable utilization percentage. If this is ever not true, then yeah, we need to not allow that withdrawal to happen, or we need to not allow a trader to open a trade which would set it over this threshold. And so, yeah, to do that, to implement that, you would, there's a few ways you could implement it, but when you're inheriting from ERC 4626, you're definitely going to have to override either these public mint or sorry, not mint, but the withdraw or redeem functions. Either both of those, or you could just go to the internal withdraw function, and then, so this is virtual, so it's meant to be overridden when necessary. And you can add like an extra validation that occurs after this, and basically just super up to it for the actual implementation. But yeah, does that answer your question?
Yep, perfectly.
All right, great. So we've just finished the introduction to Perpetuals. I hope that is starting to make sense. You're starting to understand what an advanced DeFi concept like Perpetuals looks like. And I hope that you're excited to be making your own Perpetuals protocol. Hopefully you've teamed up with somebody to go through the missions. I think certainly it will be helpful to have a partner to go through each of these missions with. So if you haven't yet, go ahead and go to the Solidity Lab Discord and go to the Gateway course directory, find the Pair Up channel, and post your time zone, the timeline you're looking to complete the course in, anything else about yourself, and go ahead and find a partner to complete mission number 1 with. So with that out of the way, now we're moving on to front-running attack vectors. So we're going to understand what front-running is, how it can be used to cause some attacks, and then we're going to look at sandwich attacks, which include front-running as basically the crux of how they come about. So enjoy the front-running attacks section. All right, we're going to start off by getting first a high-level understanding of the exact functionality that enables these front-running attacks, and then we're going to go and we're going to see how they can apply to code bases and see the different types of front-running attacks that can come up. So first of all, we're going to dive into the whiteboard here, and the very first thing we need to talk about here is the mempool. So let's imagine the mempool as literally a pool of just transactions. So let's say we have all these different circles here, and each circle here is a transaction. So we have a pool here. This is our mempool. Let me just write it out. So we've got our mempool here, and it has a few transactions sitting in it. So when I send a transaction to the network, it is basically going to, before it gets actually picked up and recorded into a block and finalized on the blockchain, and we know my transaction has been recorded, the state is final, it is going to be sent to sit in this mempool. And so this mempool is sort of just the aggregation of all of these transactions that are waiting to be recorded in a block, right? So when they do get recorded into a block, we're going to have all of these transactions that are sitting here. They're going to get formalized. A subset of them will be formalized into a block that then gets recorded. And they're going to get put into a block in a certain order, right? So let's say if this is transaction 1, this is transaction 2, this is, or let's make it even removed from numberings. If this is transaction A, this is transaction B, and this is transaction C. These 3 transactions could happen to get ordered in a block, like B could be the first transaction in a block, and then A can be the next transaction in a block, and C can be the final transaction in a block, if we have a block that only has 3 transactions in it. And so you could also have a different block ordering where you could have A, B, and then C. And you have all these different permutations of orderings of transactions within a block. And so if each of these transactions, if transaction B, transaction A, and transaction C interact with completely different systems and they don't even overlap and affect the execution of each other, they're completely disjoint, then the ordering is, arbitrary, right? So maybe this one is going on Uniswap and it's buying like some ether with some DAI. Perhaps this one is opening maybe you're opening a position on Aave, you're borrowing some DAI or something like this. And then maybe on this one, it is, let's say, doing like a reward auto compound for an optimizer vol, a urn vol, or something like this. So all of these things are completely unrelated. That would be fine. It doesn't matter what the ordering is. However, if both of these systems, both of these transactions here, let's say B and A interacted with the same exact smart contract system, then there might be a difference depending on if B comes first and A follows, or if A comes first and then B follows. There might be literally a difference in the outcome depending on the ordering of those transactions. And so at the most abstract level, what a front-running attack is, and it could even be considered like a back-running attack, which we'll see and we'll get into in a second, is just manipulating this ordering of transactions in order to be able to either grief one user, cause them to have some loss, or cause them to have their transaction revert or something like this. Just change the execution of their original transaction in a way that is not ideal for them. Or you can get a better outcome for yourself in some cases, where if I was to get my transaction recorded before somebody else's, it can benefit me. So that raises the question, how exactly can I get my transaction to be recorded before somebody else's, right? How do I get this A to be recorded before B in this sort of like scenario 2? If this is scenario 1 and I'm the person who sent transaction A, how do I get scenario 2 to happen, right? Well, so to understand exactly how we're able to do this, we have to sort of dive in and look a little bit closer at how the gas pricing and the incentivization for the nodes that are actually including this block works. So at a high level, the most important thing to know is just that I can increase the amount that I'm willing to spend on gas in order to get included higher up in the block. And so the way that our like gas calculations break down is, for each transaction, we're going to have a base fee, and then there's going to be a priority fee on top of that. And the priority fee is what's actually going to go to the validator and is going to be able to get adjusted to be able to get our transaction recorded higher in the block. And so we can see, if we go to the Etherscan gas tracker here, we can see that we have some gas estimation here, and you can see the base is 37 GWh, this is gigaway, and the base is the same for all of these estimated transaction speeds. So if I want my transaction to be recorded faster, or even recorded just higher up within an individual block, then we can increase the priority fee here. And we could basically see, for example, for Uniswap, V3 swap, which they're estimating, would expend around 180,000 gas. We can take our 40 GWh and we can convert our 40 GWh to this much whey. And then if we go ahead and do the computation of that 40 GWh times our 180,000 gas, then that's going to give us some E15 number. If we go ahead and divide that by 1E18, that's the number of actual ether that we're going to have to pay for this transaction. So as we increase this 40 GWh number, this gas price, which is the net of the base fee plus the priority fee, if we increase that, we're going to be paying more, and so we're going to get recorded earlier on. And so this, if ether is worth $2,000, I'm not sure what it's at right now, I don't check price, then this would be $14. And I think So Ether must be doing a little bit worse right now. So it's actually around $8 or $9 here. So of course, all I've got to do, I've got to up this priority fee, and then I can ensure that my transaction A can get recorded before the transaction B, because I can basically come and I can observe, okay, what is the priority? What is the priority fee of B? What is the base plus priority fee? How do I just beat that? And then as long as I beat that, then I can get recorded in the block before. So with all of this said, it is just important to note that on some networks like Arbitrum, which is a layer 2 and it has a sequencer, front running like this is not actually possible because there is no public mempool for, as the sequencer basically takes these transactions, you submit the transactions to the sequencer, and the sequencer will do its own ordering on a first come first serve basis, and there's no public mempool to be able to observe and check somebody's gas price and then one up them and get ordered before them based on that. The sequencer is basically doing a first come first serve ordering, and there's no mempool to check, so there is no real front running that can happen on a network like Arbitrum that has a sequencer. But on L1 mainnet ETH, of course, this is a very, very real thing, and it happens way more than you can imagine. Okay, so let's see how this concept can actually be used and applied to real smart contract systems, and what are the types of findings that you can actually uncover with this sort of attack vector. So I've got this finding stake 1 pulled up here, and this is from a system where users basically are holding a token that receives value from these like individual transactions that add value to the token. So before we read the finding, we can sort of just map out what the system looks like at a high level. Is basically, you can imagine it as there's one pool of value, and then users can basically stake their tokens to get a share of that value, and they can unstake to basically like collect their rewards and then unstake, get out of that pool of value. And so while you're staked in the system, you will get whatever value delta happens while over the course of your stake. What does that mean, right? If I stake when this has, let's say, to keep it simple, let's say I'm the first staker and I come in, I stake, and originally it's worth $0 in here, right? So let's say I'm the very first staker and there's no staking rewards that are to be distributed to the stakers. Then a few days pass, a few days go by, and now there is $100 in here. And so now what I can do is I can basically like claim my rewards. I'm the only staker, so this $100 just goes to me. Now, the important piece here is looking at how exactly the $100 accrued here. It's not a like second by second accrual of like, 1 cent per second or anything like this. It is a single transaction that will bring $100 of value, add $100 value to this pool. So if we were to graph out the value of this staking pool over time, if this is basically the money that's sitting in the pool, and then of course this is time, it does not look something like this. It looks actually something like this. We're at 0, we're at 0, we're at 0, we're at 0, and then all of a sudden at time 2, there's a transaction that auto adds $100. So say this is $100 value. There's a single transaction that in a single block adds $100 to the value. And so when we see a stepwise jump like this, this is a prime candidate for being able to come and front run, stake literally right before. You could even go in the same exact block and just get before this, and then I can unstake right after, and I'll still get the same rewards as if somebody had been, they've been an OG, they've been staking since t=0, and they continue to stake forever. I get the same exact rewards just by being somebody who came in, saw that there's a transaction to add $100 of value, get in there literally right before it, and then I can claim that $100 of value immediately and just unstake right after. And so exactly what this would look like in this front running scenario is if this is the transaction to add $100, so if this is the plus $100 transaction, and let's say A was my transaction to stake, I'm doing this like I'm the malicious front runner here. This is my staking transaction. Now, instead of this situation happening where $100 gets added first and then I stake, in which case I don't get to claim any piece of that $100, I want to reverse it. I want to get A before B. And so we stake first, and then immediately afterward, literally in the same block, they add $100 to the value. And then I'm immediately able to withdraw some of that, and I can unstake my stake. And so I never really had to stake for any real amount of time to be able to reap the rewards of that $100. And the $100, it really belongs to the people who have been staking for this entire period, right? And so if we read the finding here, it says there exists no fee or lockup period associated with staking to receive a portion of the rewards compounded during the really long name function. A malicious actor may simply buy GMX key and stake right before the really long name function to immediately accrue a portion of the collected rewards that were meant to be attributed to other stakers. The malicious actor can then immediately claim these rewards, unstake, and sell GMX key after the reward compound, therefore stealing rewards from other stakers. And so this is exactly what we've described here. Is there's literally there's no disincentive to be able to not do this, right? When I stake, there's literally no fee for staking, there's no fee for claiming, there's no fee for unstaking, there's no lockup period or anything like that. And so these stepwise jumps here can be essentially just the value can be fully extracted out of them that way. Okay, now we have a second front running related finding. This is a good medium finding. And the description is basically because order ID is a value chosen by the user, a bad actor can basically grief them by front running the user's transaction with their own transaction and using the same order ID. And this will cause the user's transaction to revert, and it could be particularly detrimental if the user had a time-sensitive order and they really needed to increase their collateral to avoid liquidation or something like this. And so if we actually look at the code here, basically the issue is just that if we call this create order function as a normal user, we're providing an order ID, right? And then that order ID will go on to be used in the construction of our order and later the execution of our order. But of course, if an order exists with that same order ID, then my order cannot be created. We can't like overwrite an order that has an existing order ID. That would be a much worse issue. But essentially what can happen here is in the mempool, I can observe somebody's transaction B, and I could see that they're using an order ID of 7. And I see they're using an order ID of 7. It's an important transaction for them. They need to increase their collateral amount or else they're going to get liquidated. Maybe I stand to benefit from them getting liquidated. And so I can observe all of their transaction data sitting there in the mempool, and I could say, well, why don't I submit a transaction A, that uses the same order ID of 7, and then we just need to have my transaction A get before their transaction B. And so I just up the gas priority fee, and then my transaction A gets recorded before theirs, and then ultimately mine will create the order ID, the order with the order ID of 7. They will then attempt to create an order with an ID of 7, and it will revert because of course my order already exists with an order ID of 7. And so they're not able to increase their collateral, and potentially they get liquidated because of that. And so the recommendation is, of course, to use some sort of a monotonically increasing nonce, or perhaps make the order ID a hash that includes the message.sender, so it's unique to the message sender. It can't just be something that you just observe and then copy. It's something that actually depends on who the message.sender is at the time of when you're constructing that order ID. And so this is a fantastic front-running attack by the OX Lanterns team in one of our Guardian Defender audit contests. Okay, so those are two great examples of different kinds of front-running attacks. You can see how front-running is really a class of attacks, and it can apply extremely differently depending on the use case, depending on the system, depending on what the attacker is even trying to achieve. And so let's talk a bit about how you can uncover these types of exploits, and what are the systems and the frameworks that you can use to uncover these exact same things in your own security reviews. So first of all, we need to be checking for stepwise changes in the balance of things that are shared. So often in basically almost any DeFi protocol, there's some sort of shared pool, right? And this is sort of just by way of the design of Solidity and the design of Ethereum, is it just makes sense to have a shared pool. You have a vault or something like this, and it just accrues value over time. Well, we accrue value to the vault, and then everybody just owns a piece of the vault, right? So we need to pay very close attention whenever there is a single transaction that adds value to something that is shared in a single instant, right? So we need to be paying attention to any kind of stepwise jump in the value of things like this. So that could be a stepwise jump in the worth of a token, the stepwise jump in the amount of assets that are sitting in a vault, or anything like this. And so whenever you're in a security review and you're looking at a protocol that has some sort of reward distribution mechanism, then pay very close attention to stepwise jumps. They can often be sort of sandwichable, where somebody deposits and then withdraws right after. Another kind of front-running attack, which is related to the kind of front-running attack we saw from the OX Lanterns team, is the kind where we change a specific variable, we change a piece of state right before another user's transaction, and that affects how their transaction is executed. It might affect the price that they get executed with. It might affect whether that transaction reverts or not. But in the end, it just causes a negative outcome for that user and or a positive outcome for the malicious actor. So when you're walking through the fundamental goals of a system, ask yourself, what variables could impact the execution of this transaction? So whether it's a user executing something, like they're creating an order, creating a position, or even doing a swap or anything like this, ask yourself, what variables can affect this? Great, now that we have a list of those variables, now how could somebody potentially front run to change those variables and negatively impact the user? And then also, if it's maybe a keeper or an admin making changes, you can also ask yourself the same question. What are the variables that would affect this? Or how would a user even benefit from this change happening if I sort of like front ran the owner's manipulation of a value, and then back ran it to maybe be able to arbitrage the difference in a select parameter that they're setting for the protocol, or something like this. So at a high level, when you're analyzing these select external calls that users or keepers can interact with, think to yourself, what variables can manipulate or benefit off of this action if I were to front run it or back run it, or both. All right, so that is everything you need to get up to speed on front running and exactly what these types of attacks actually look like in real code bases, and even a framework that you can use to uncover some of these vulnerabilities yourself. Now, in the next video, we're going to build off of this one. We're going to understand the infamous sandwich attack. We're going to see how these front-running attacks and these back-running attacks, which we didn't really talk about too much, can be combined to basically extract more value from people who are swapping on an AMM. So essentially, sandwich attacks are a special case of front running where it's particularly financially beneficial for the attacker to be able to front run a transaction. Well, why is that, you might ask? So first, to understand this, we'll start off by drawing a simple price curve from an AMM. So here we have something resembling an x times y equals k curve. And of course, if you're not familiar with this formula or this AMM curve in general, then you can go ahead and check out my video on the complete guide to AMMs and the Uniswap V2 constant product model, which is this x times y equals k formula. So if you have a little bit of context on AMMs, we'll go ahead and just give some basic high-level overview. We have token 0 on the x-axis here, and we have token 1 on the y-axis. And essentially, if the price is all the way over here, that means there are a lot of token 0. There's a huge supply of token 0. This is the amount of the supply, is this x value of token 0, and there's not a lot of token y. There's not a lot of token 1, which is the y-axis right here, right? However, if price happens to be over here on the curve, then of course, well, we've got a big y-axis value. We've got a lot of supply of token 1 and not a lot of supply of token 0. And so, of course, in this example, where we're over here, we have a huge supply of token 1, not a very big supply of token 0. Obviously, that means that the price of token 1 relative to token 0 should be relatively low. So token 1 should be cheap as it's an abundant supply. Token 0 should be, rare, precious. So the price of it in terms of token 1, something that is not rare, is very high. And so if we're talking about the price of token 0 in the context of this curve here, stuff that is more to the left, so as we move more along here and we go more up and to the left on this curve, this is a higher price for token 0. So the price for token 0 goes up as we go to the left. Now, how does all of this build into what a sandwich attack is? Well, we have to look at exactly what you're doing when you swap on this supply and price curve. So let's say that I want to swap X amount, let's say, well, let's put an actual number to it just to not get X confused with this formula here. Let's say I want to swap in 100 token 1, and I want to swap that for some amount of token 0. So I want to swap my 100 token 1, I want to turn that into token 0. So what I'm going to be doing, if we say, let's say that the current pool price sits on this curve at this particular point, what we're saying is, so we've got this amount of token 0. This is the supply of token 0 here, is this X value of this point. And then we have a supply of token Y right here, and that is the Y value of this point here. And so what I'm doing is I'm adding 100 token 1, I'm giving that to the pool, and then I'm taking out token 0. So what would happen is I am increasing this y-axis value, right? So I'm coming in and I'm adding more. I'm making this y-axis value go up because I'm providing more of this token 1. We're increasing the y-axis value. So what happens is this increases, and as this increases, the x value decreases by a corresponding amount. So the net result, if I just come and get rid of this here, the net result is that we move this dot, the dot which represents the actual price for the token 0 that I'm buying here, and consequently also the token 1 in this exchange rate, moves up here. So we just moved up and to the left on our price curve, so the price of token 0 just went up, right? So I removed token 0 from the supply of token 0 here is smaller, and I added token 1. The y-axis supply here is greater. So I directly took price from where it was right there and moved it up to where it is now. So now maybe you're starting to see how this might be able to be manipulated if somebody can front run your swap. So let's ask ourselves, what would happen if I say I want to swap at this price here? Let's say this is, let's just call this P0. Let's say this is P0 here. This is the price that I am willing to swap at. This is what I want to swap at. But somebody else comes, and before my swap gets executed, right, it's sitting in the mempool. This is what we talked about in the previous front running video. My transaction could be sitting in the mempool, waiting to get recorded in a block. And then somebody else can come and they can do this swap right before me, and they move price up here. So now instead of price being at P0, when my swap starts to get executed, now price is at P1. And so that is immediately bad for me because I thought I was going to get executed at price 0. But now I have to buy this at a higher price, which means that I'm going to have to put more token 1 in to get the same token 0 amount out, right? Because the price is higher. And my swap will subsequently move the price even higher after that. So after I'm done swapping now price will be up here. It will be at this P3 value right here. And so somebody got in right before me. They're able to get in at this P0. That's when they were able to buy, the price at which they were able to buy. And then I bought at price P1 and I pushed price up even higher to P3. And now, well, this person who bought all the way down at P0, well, they experienced some profit right away because not only did I just raise up the price, but they've still got their cost basis at P0. So what this person can do now is they can just sell their tokens immediately and just realize that little delta of profit. So now when they sell their tokens, they're going to bring price back down to some value. It might be slightly above or slightly below wherever price was when I initially bought, depending on how much amount they bought at price 0 and how much amount I ended up swapping. But essentially what was able to happen here is instead of me just getting my execution where I wanted it to at the original price, somebody forced me to buy at this price and push price up even higher. And then they were able to extract value from that by immediately selling the tokens that they bought right before me at a little bit lower price and experience that basically risk-free arbitrage, risk-free delta profit. And so the key here is really just the fact that when a person swaps one token for another, they move the price. If I can get directly before your swap, then I can have a lower cost basis and just wait for you to move the price even further and then sell at that higher price. And then that is the crux of this vulnerability. So you might be asking yourself, well, how do you even protect from this? How are we even able to swap on chain without just completely, just front running each other and having, a ton of value extraction just happen in every swap? So what I'm able to do to protect myself is I'm able to say, okay, well, I haven't set my transaction yet. This is what the price is right now. It's at this P sub 0, we'll call it. And I'm looking to make a swap at P0. But of course, if somebody completely front runs me and moves the price up to something much higher, then that's a bad deal for me, right? They're going to be extracting a ton of value from my swap. So I can say, well, look, here's the percentage of slippage that I'm willing to accept, right? I'm willing to go, maybe like 1%. Maybe I'll allow you to go 1% higher than this P0 price. So this would be, for example, 1.01 times P0. That's what this price would be. So you just say, okay, price is currently at P0. If somebody were to come and extract the maximum of that value that I'm allowing them to extract, I'll let them push the price up to 1.01 times wherever the current price is. So that's the slippage that I'm willing to accept. And now, as your transaction is sitting in the mempool waiting to get recorded, if somebody were to try to maliciously front run you and cause you to have to buy at some crazy price that's way up here or something like that, it's going to completely just revert, and the swap is not going to go through because we are invalidating this 1% margin for slippage. And of course, you still do want to have somewhat of a margin, because otherwise, if literally anybody does even a minuscule swap, then your swap is just not going to be able to go through. So what do some findings related to sandwich attacks and slippage protection look like in real smart contracts? Well, I've got a finding here pulled up from a Guardian Defender contest. This is from Team 3, which was actually just a solo team of Chinmay. Chinmay compiled a fantastic report here. Recommend that you go and give him a follow on Twitter, as he often puts out some great Web3 security related content. But he's got a great high finding here, which has to do with the slippage tolerance being extremely high. So we can go ahead and look at, we'll read the description, then we'll have a look at the actual code. So let's see, it says, when using a router to swap tokens, slippage tolerance provides a protection mechanism in case of flash moves in the market values. It is the user's responsibility to give a minimum amount of tokens he is ready to accept. In this protocol, the min amount has been hard-coded as 1, which means 99% plus slippage allowed in case of large amounts. So the user is, usually supposed to determine, this is the minimum amount of tokens I'm willing to accept out of this swap as a result of this swap. And that's really where we're defining our, percentage of whatever the current price is. And so this finding is basically saying that the configured slippage in the contracts that we'll see in just a second is essentially 99% plus. So what that's saying is somebody can come in and move the price all the way up here and beyond, and you'll still make the swap, which means a ton of value just got extracted from that swap, and they're going to be able to steal a lot of value from your swap, and you're going to end up getting pretty much, for the most part, wrecked. And this is exactly what Chinmay says here. This will make a user lose most of their dividend funds in this particular finding when the pool is imbalanced. And then, of course, the recommendation is to provide slippage tolerance as a parameter instead of forcing having basically a terrible 99% plus slippage margin. So we'll have a look here. And we just have very simple, just a function swap tokens for ETH, and we have the actual path, and then we'll do an approval, and then we'll do the actual swap. And the swap will basically have just any amount of ETH, and this is the minimum output amount parameter here, and we're configured just one way of Ether, which is essentially for all intents and purposes 0. So essentially you're saying I'll take even basically 0 amount out of this swap, which means effectively there is no slippage protection, which means exactly like Chinmay said, basically all the value of this swap could be extracted. All right, so now we understand what a sandwich attack is. We understand how to protect against it with slippage protection. We see, what a common finding related to sandwich attacks looks like, but how can we have a framework for uncovering similar attacks like this, and what do we need to think about when it comes to sandwich attacks to smart contracts? Well, first of all, we need to ask ourselves, are we auditing or building something that interacts with an AMM and does a swap, right? So if you have something that does a swap on UniV3 or any other AMM, then you need to be thinking about slippage protection. Now, looking at every single swap call, you should inspect the minimum output amount, whatever the particular slippage configuration is, and make sure that it's able to be configurable and something reasonable. Anything above, maybe 100 plus basis points is probably a little bit too much leeway. Of course, it depends on the amount that's being swapped, but that will be protocol specific. But there should be some way to set appropriate slippage controls during a swap. And on the other side, if you happen to be auditing an AMM itself, then of course you need to think, well, we need to expose appropriate slippage controls to the user. All right, so if a protocol happens to not have slippage controls, or maybe the slippage controls are not sophisticated enough, then those should be implemented. All right, now that is everything you need to know to get a really strong grasp of sandwich attacks. And last but not least, let's go ahead and let's have a look at the famous Jared from Subway. We've got his address pulled up here on Etherscan, and let's see how he's actually doing these sandwich attacks to uncover and extract value from transactions and other folks doing swaps. So we can see, first of all, tons and tons and tons of transactions just happening all the time. We can see even in the past 3 minutes, this whole page of transactions is filled up here. So we're going to have a look at 2 of these transactions that are back to back right here, and they're both from the exact same timestamp from 55 seconds ago. So let's have a look at the first transaction here. We can see there's a few things going on here with some more bespoke tokens and also interacting with wrapped ether. We can see that around 633, what is that, billion of this network spirituality was swapped, and then they received, some amount of wrapped ether. And then Jared from Subway sends in around, what is this, 85,596,730. So around 85 million of this Trinity token here. And Uniswap sends back 1.229 wrapped ETH or something like this. And this is the first transaction here in the sandwich. And then we're going to see, so somebody came in the middle and they have moved prices. And now we're going to have a look at exactly how Jared from Subway profited on the subsequent transaction. So in the subsequent transaction here, we could see that Jared from Subway sent in what looks like 4737 wrapped ether and received back this time 634 billion network spirituality. And so if we compare that back to this swap that happened here, from what happened, he put in 633 billion for this 0.49 amount of wrapped ether. Now he put 0.47 and received 634. So this was a pretty decent amount of slippage that Jared from Subway was able to extract between this, whatever this network spirituality token is. He essentially went from putting in 0.49 or putting in 633 billion of this token and then receiving 0.49 and then only putting in 0.47 and receiving 634 billion. And we can see a similar thing happened with this Trinity token as well. We can say that in was 85,596,000 and then out was 85,603,000. And we can see that also 1.229 was the out and 1.22 was the input. So essentially we can see for both the network spirituality and the Trinity token here, Jared from Subway was able to extract value from some swapper who happened to swap in between. And in the original transaction, he basically took this network spirituality and this Trinity, turned it into wrapped ether, and then on the subsequent transaction after, so the top slice of the sandwich, he took that wrapped ether, and he didn't even need all of it. He just turned a little bit less of that wrapped ether into more network spirituality and Trinity tokens. So basically ending up with more wrapped ether and more of these bespoke tokens than he had before. Of course, where did that value come from? It came from this person, and whatever their slippage configuration was, he extracted that delta of that value. All right, so that is absolutely everything you need to get a strong grasp on these sandwich attacks, and even a framework you can use to uncover these types of exploits in any smart contract system. And of course, now you understand why you must always set your slippage when you're performing a swap. All right, fantastic. So now we're ready to hop into the audit training section of part 1 here. So first of all, we're going to have a guest lecture from Patrick Collins. Patrick Collins is going to come and he's going to tell us how to write stellar finding reports, specifically on CodeHawks, but also this is going to apply to any type of reports, any type of findings that you uncover in any security review context. So this is going to be super beneficial for anything you do in security moving on from this course. So after that, we're going to go through a live audit session. So this was a live audit that I did with 6 security researchers auditing with me. So sort of following me as I go through my audit approach, asking me questions about my approach along the way, and just, you know, being there and figuring out the code base alongside with me, and then also discussing findings and ideas that we had for attack vectors as we went through the audit. And then after this live audit, we're going to go into student code walks. So you're going to see in this section what some of the perpetual protocol implementations actually looked like. So I would recommend that before watching this session that you actually have mission 1 completely implemented for yourself, because you don't want to spoil, you know, what an implementation might look like or something like this. I think that would diminish the effectiveness of mission 1 for you. So definitely have that completed before you watch the code walks, and you're going to get to see different approaches, different ways that people were thinking about designing the system, and then you're going to understand perhaps some interesting vulnerabilities that we uncover in real time as we're doing these code walks. And then after watching this, perhaps you'll want to go ahead and go into the community Discord for the course and post in the Gateway course chat and see if there's another team or another individual who's taking the course who would want to do a code walk with you or something like this. Personally, I think that code walks have been really beneficial for me coming to a deeper understanding of DeFi and having a deeper understanding of the code base that I'm giving a code walk for, but also being better as a reviewer, which ultimately translates to just being a good security auditor, right? So I think code walks are something that we're going to continue to drill in on and improve as a tool to improve security research as a skill. But in this student code walks session, you're going to get to see what code walks look like and how they can be conducted and how they can be used to improve your approach to security research. So with all of that out of the way, let's hand it off to Patrick Collins to get this audit training section started off.
What's going on, everybody? My name is Patrick Collins, and here is how to write a stellar finding report. So you might be asking, why do I even need to write good write-ups? Why is this important? Well, we're going to go over that in this video. We're going to talk about the different components of what makes a good write-up. We're going to do a live example, and then probably most importantly, we're going to learn how to actually learn from the best. So first off, why is writing a good write-up important? Well, we want to win over the judges in a competitive competition, of course. And ideally, we even want to be the selected report. Often on competitive audit platforms like CodeHawks, you actually get a boost in reward if you have the best write-up. But more importantly, the most important thing is you want to convince the protocol they need to fix the issue. If a protocol does not fix the issue and you reported it, it's your fault. So you need to be very convincing. Components of a good write-up. You need to have a clear root cause, a clear impact. You need to be succinct. And finally, like we said before, the burden of proof is on you. A proof of concept or a proof of code is preferred. You'll see POC be used a little bit interchangeably. They are a little bit different, but we will go over both of those. So to demonstrate this, we're actually going to be using a CodeHawks first flight. CodeHawks is a competitive auditing platform, a phenomenal place where you can earn money. You can compete with other security researchers to earn rewards by finding bugs in real code bases. There's tons of contests that you can sign up for to participate in. And additionally, we have this thing called first flight. These are more beginner-friendly competitive audits that are much less daunting. The code bases are much smaller, so they're perfect for you who's going out to learn. And at the end of these competitions, they are very quick. You will get very quick feedback on how well you did, so you can see where you need to improve. So the first flight that is going on at the time of recording is this thing called a password store. Very minimal, very small code base. I'm sure that Owen has taught you all the bugs that are in here. If we look at the code base, there's a ton of bugs in here. I don't want to give anything away right now, so I'm not going to report an actual bug in here. However, we are going to see one very obvious gas optimization or gas efficiency improvement. One gas efficiency improvement would be that this S owner variable right here, it's actually never changed, right? If we do a little quick search for it, it's never changed, so it should be immutable, right? Having it as a storage variable is a waste of gas, so we want to actually fix this in our code base. Another reason that we're going to use this as our finding, this as our example, because this is a very simple one, a very minimal one, right? And we can do it kind of very quickly. Now, normally in first flights, we don't allow gas submissions. However, for this demo, we'll pretend that we allow gas submissions. And let's try to write this gas submission up as if it was a low, a medium, or a high. How do we write a really good submissions? How do we tell the developers that, hey, you need to change this S owner variable to an immutable variable to save gas? So we're signed into Codeox here. We're gonna go ahead and hit submit finding. We're gonna scroll down and we get to the submission box. So the first thing we need to do is write a phenomenal title here. Now, when you're writing a title for your finding, you usually wanna do root cause plus impact. And that's how you want to title these so that it's very obvious what you're finding, what your issue is. So for this issue here, the root cause is the fact that we're not setting this variable to be immutable. So we want to say the root cause is what? The root cause is the fact that this S owner variable is not set to immutable. Or we could say that it's currently set as a storage variable. So to reference it, one thing we could do is we could say password store : S underscore owner being set as a storage variable. This is the root cause. And this is one way that we actually reference a variable or a function. We say the contract name, 2 colons, and then the function or variable name. So, and then we put these little backticks around it to let somebody know that this is actually code from the code base. Let me zoom in a little bit here. Password store S underscore owner being set to a storage variable. That is the root cause. And what is the impact? We could say wastes gas or causes extra gas or whatever you want. This is the impact. So we have the root cause and then we have the impact. Next, we want to select the severity. In the Codeox docs, we have how to evaluate a finding severity between high, medium, and low. This one, like we said, is a gas severity because it's just a waste of gas. There's actually no security vulnerability here, but let's pretend it's a low. But to really understand how to actually judge them, we would basically do a matrix of likelihood versus impact. The more impactful it is and the more likely it is, the higher severity is. The less likely and the less impactful, the lower severity. Good example of high impact is lots of funds could be drained. Medium impact would be some funds could be drained or paused. Low impact was there's no funds, but the state might be incorrect. The protocol might give a wrong output or something like that. High likelihood is something that's highly probable to happen. Basically, a hacker could directly call a function to extract money. Medium likelihood is maybe there's some very weird specific attack path. And then low likelihood is maybe it's unlikely to occur. Maybe some hard to change variable is set to, is set to something very unique on a very specific block. It can be a little bit subjective here, but we have some examples below if you want to learn more about the different severities. For this one, this would be a gas, but since there's no gas allowed in this, just for this demo, I'm going to say low risk. Next, we want to add relevant GitHub links. We want to add the actual exact links where this vulnerability occurs. If we go click view repo, we can go into the repo here. I'll hit SRC. We'll go to the actual line where this occurs. It looks like this right here is where the immutable variable isn't being set. So we'll hit the 3 dots, copy permalink, and we'll paste it in here. And then we'll add another link as well. And we'll add it down here because it could be set to immutable down here. And we'll copy permalink as well. Now, if I copy paste one of these links, it'll bring me directly to the line that was highlighted before, so that either a judge or a protocol knows right away, this is the line that they should be looking at. Now, we get to actually writing the finding. What are the components? Clear root cause, clear impact, succinct, and then the burden of proof is on us. What is going to be our summary here? Well, we're going to say we're going to do some markdown with backticks, password store, 2 semicolons, s_owner, variable is unable to be changed and therefore should be immutable to save gas. That's the summary right there. And what we could do is we can scroll up, we can preview this, and we can see those backticks actually highlighting. We can see that this is actually highlighted as well, and we can see what this looks like in markdown format. And that looks very nice. So we've given the summary here. What's next? The vulnerability details. What are the details here? Well, we actually want to point to the lines of code, or maybe make it more obvious, more clear to the protocol what's actually going on here. And so oftentimes what I like to do is maybe I'll even copy paste some code, do some 3 backticks. We'll say JavaScript or Solidity, paste it in here. And then I'll even maybe do like a little @ sign and point to this exact line so it's blatantly obvious where this is happening. And maybe I'll say something like, and I'm going to copy paste what I've already written. Maybe I'll say something like, if a variable never changes, then reading from storage is less gas efficient. And instead we should read from the bytecode. Using an immutable variable will enable the protocol to save gas on reading the password store, s_owner variable. Boom. Now we've been very succinct. We've pointed to the line where it actually occurs. Boom. Vulnerability details section complete. Now, impact. This is where you want to add what the exact impact is and then prove the impact with a proof of code or with a proof of concept. So for this one, I would say it wastes X gas. And this is probably the most important piece in your whole finding. Remember what I said before. The burden of proof relies on you. You need to prove to the protocol, and you need to prove to the judges why this is an issue, and ideally exactly how bad the issue is. Right? Now, of course, depending on time allotment, depending on how far you are in the audit, depending on the maturity of who you're working with, you can make this more or less verbose. I would argue you should always defer on the side of writing a proof of concept, a proof of code. So what a lot of people will do is in this section or in the vulnerability details section, they'll add a test that they actually wrote that can be dropped right into the test suite of the actual file, like dropped in the test suite here, where it'll prove exactly how much gas is wasted and how much gas could be saved if they changed it. Or if you were doing another vulnerability, you would prove exactly how bad it is, exactly where it is, etc. So you'd say the exact impact or as much impact as possible with proof of the impact, with proof of the vulnerability as well. Finally, you can add some tools used, like Slither, Foundry, whatever. And then you want to add your recommendations. And there's a couple different ways to do this. A very simple one would be to do set password store, s_owner to immutable. And then what's phenomenal is if you give a diff with the exact change. Of course, I might add something else about actually changing the name to I_owner, but that's beside the point. Now, if we do these 3 backticks, write diff, these 3 backticks down here, and we do a minus here and a plus here, we'll get some really nice syntax when we go to preview this. We scroll down, we see we get a red line for the line we want them to remove and a green line for what we want them to replace it with. Come back to write, scroll down, maybe I get rid of the minus. We'll just get the plus if we go back to preview, right? But we want that minus there. We want to say, hey, change that line with the new line that we're giving you. And this will give the protocol exactly what you want them to do so they know exactly how to fix this issue. And if I zoom out a little bit here, now we have a phenomenal write-up that has a good chance of being the selected report if this gets included as an actual issue. So we say root cause, impact, relevant links, succinct summary, clear vulnerability explanation, impact, and here's where we would write some test suite. Maybe we would say exactly how much gas it wastes, etc. Tools used, and a very succinct, clear recommendation for the change. Here's where you can learn even more and even quicker. What you can do is, let's say you want to know, hey, like, has somebody else come up with this before? How has somebody else done an issue like this before? What you can do is you come to a platform like Solidity, where you can actually search for and look up other findings, other reports that other massive teams, competitive auditors, etc., has reported. For example, let's say you wanted to find a high impact issue on reentrancy. Maybe you look up reenter. We'll do a search. We can actually see something up right from Cyphren. Actually, we can see a write-up from the Cyphren team, and we can get a good idea of what these look like, what a really good write-up looks like from these professional teams. And then finally, if you want to see a lot of really interesting findings on a code base where you can learn a lot very quickly, I highly recommend everybody check out the Beetle competition that went down on the CodeHawks platform a couple months ago. This was an Oracle-free perpetual lending protocol, so it's DeFi right off the bat. And if we go to the final report by hitting view final report here, we actually can see a whole lot of issues. And if we click contest summary, we see there were 26 highs, 15 mediums. Let me zoom in a little bit here. 26 highs, 15 mediums, 28 lows, and 110 gas/informational findings. So this is a place where you can see in a protocol a ton of attack vectors that you can learn from very quickly. And even if we just scroll down some of the top ones, we can see exactly what those attack vectors are. We see something about weird ERC20s. Tokens with less than 18 decimals allow for draining of funds. This is a very common attack vector. Lender contract can be drained via reentrancy. I'm sure Owen has gone over this. If not already, he will soon. Another reentrancy issue. There's a sandwich attack. This is a classic MEV attack. We have some wrong reward calculation. We have using fake tokens, more weird ERC20s, more MEV, a slippage issue with a Uniswap integration. This is a phenomenal code base, a phenomenal report that you can walk through, you can read to learn A, how to write phenomenal write-ups to potentially get selected, and then B, learn a ton about DeFi, a ton about common issues in Web3, and just level up your skills as a competitor. So with that all being said, highly recommend everybody sign up for CodeHawks. If you're a little bit nervous of these competitive audit platforms and you really want to get a win under your belt, definitely be sure to check out the first flights, where these are much easier competitions. These are much smaller code bases with bugs that we've specifically planted in them. And then, of course, when you're ready, when you're feeling strong, or even when you're not, and you just want to move to the next level, be sure to sign up for a CodeHawks competition where you can actually begin and actually start testing out your security researching chops. Like I said, my name is Patrick Collins, co-founder of Cyphren, CodeHawks, Web3 Education. And finally, we have a phenomenal security and auditing, DeFi and EVM curriculum coming out very soon. So be sure to head over to cyphren.io to learn more. And I'll see you next time.
What we'll do is we will find a contest, and we're going to find some code to audit. So let's see. Let's see what audits are going on right now.
You could try the $1 million one.
Yeah, I mean, let's do it.
I was joking actually, but
we'll do it. We'll do it next week. Maybe we'll make 200 grand.
That's really good news that there's a really big contest going on. Everyone's talking about that.
Yeah, 100%. Asymmetry, AFETH. That's an invitational. There's Maya DAO. Their cross-chain thing. I think that's what that is.
These days, CodeHawks as well. I have a few, and right. Usually they are competed in a few of them. They are a little bit more beginner friendly, except the Viper compiler one. That one is crazy, but
yeah.
Yeah.
I like CodeHawks.
Yeah, ditto ETH. The system mints pegged assets using an order book. Interesting. Using over collateralized staked ETH. What do you guys think about this one?
Why not?
All right, cool. let's check it out. Let's see what this looks like. 3,000 lines. All right, cool. So let's do this one. We'll do ditto. I'm gonna take a quick break. I'll be back in 2 minutes. Just go to the restroom, and then we'll get started. Okay, so I'm gonna use this as kind of like our notepad. And here's what I like to do before I even really go into the code base. So first of all, we'll lay out what are the goals, what are the things we want to be able to go in and achieve. And I have a place to just put notes, a place to put findings, and that will do it. Just a place to write stuff. Okay, so let me have a look. First of all, let's just see what this is. Contracts. Where's their README? Okay. Docs right here. Looks like there's these things of orders. Got a token. So we got staked ETH. There's known issues. Okay, let me read their docs. Let's see this. Decentralized pegged asset built on Ethereum. ERC20 tokens that track the price of a targeted asset. So it seems like it's a stable coin for not necessarily the US dollar or anything that you want it to be for. Okay, so ditto assets providing collateral in the form of staked ETH. Okay, so it's kind of like a DAI where it's an over collateralized stable coin, but it's just not necessarily tracking US dollars. Okay. Okay. I think that's everything. Okay, so goals. I want to start off by understanding how do I mint these pegged, I think they said ditto tokens or something. Ditto tokens, the pegged assets. One thing I'm interested in is how do I determine which asset I'm pegged to, like what I'm minting. Let's see, you know, always when there's some sort of collateral, how is like health factor involved? Do you get liquidated? I'm assuming yes. How does that work? Let's see what other interesting things. How do I mint ditto tokens? Yeah, is collateral always ETH? I think it is. So these are the questions that I'm going to ask that I want to get answered as we're looking. So what I'll do generally, after I've got my goals like this, I'll go ahead and set a timer. In this case, we're going to set it for, let's go for until the hour. So 55 minutes. That's what we'll set it for. So we got that going. And I'm going to attempt to tackle this. Usually when I'm auditing, try to close out of everything, including like Discord. Obviously we're gonna stay on Discord, but to avoid like, you know, getting distracted or anything like this. So let's find the code base again. I'm going to clone this. I'm going to pray that IntelliJ behaves and it's able to index this.
What could be out of the topic, but why IntelliJ?
Yeah, so you'll see, well, hopefully you'll see why I like IntelliJ if it works nicely. It's been acting up lately. So I like to use IntelliJ because of, like, let's say, oh God, are they using diamonds? Oh no. Like let's say, let's try and find a good, so that's like I can just click and it will go to like, okay, what's this error? Okay, well, that's not working, but command click is like, I really love this. And then also, like if I want to go back, I can just use a command bracket and stuff like this. So definitely, for me, it's just like a personal, I like to use it for navigation and things like this. Just kind of removes my, the friction that I feel when I'm, like if I wanted to see like, oh, where's this function? At least in VS Code, they also have command click, but it feels to me that it only works like 20% of the time or something. So you have to like command shift F and like find that instance or something like this. So it's really just the indexing that is why I choose it. So there's bad news. They're using diamonds, which is just really annoying. So we've got all these facets. So these facets are individual like contracts that are registered in the diamond. So the diamond contract, basically it's going to be like just delegate calling to the correct facet that belongs to whatever the message.sig is. So I'm going to try to ignore a lot of the diamond stuff and try to understand more of the interesting things. But of course, there's issues that could arise with the diamond stuff. So my first goal, let me find that MD. How do I mint Ditto tokens? All right. So let's see. There's a lot of stuff going on here. Let's see if they have, I know they have technical docs, so maybe they have a nice little guide. Using an order book, using over-collateralized staked ETH, system is a central limit order book, limit short order type, price, and an amount. Okay, this is weird. Okay, so I'm assuming they're doing this order book off chain. All right, so I'm gonna look for an order book. Got ask orders. Got to create ask, create bid, create forced bid, exit short. Interesting, exit's a short. So it looks like you can short stuff on here. Orders, so we've got cancel bid, cancel ask, so you can cancel your orders. Is this a, yes, this is a contract. Cancel a short. So it seems like I have, if I'm gonna write down some notes here. Seems like we've got bids, we've got asks, we've got shorts. Seems like all of these are within their definition of an order. Cancel order far from Oracle. Weird. O is order types, obviously. All right, owner stuff, short orders. So they've got an idea for limit orders that I think will get triggered at this price.
Can I ask you, when you code in Solidity versus coding in like any other like normal language,
Yep.
do your code style change? For example, something I've thought about is that Solidity needs to be that much clearer because it's very easy to make mistakes. Like, have you done any like mental changes?
Yeah, I mean, it's been a while since I've written anything else. So actually, like, I mean, yeah, I think certainly there are always like the style type stuff, like putting underscores for stuff like that. That obviously I only do in Solidity. That would be, you know, pretty like obtuse for like Python or something like that. I think, yeah, I mean, it always depends on like what you're making, right? So I think definitely with Solidity, the code is just there's not a lot of the code, right? Like generally in a Python application or something like this, you're going to have, you know, you could easily have 10,000 lines, 20,000 lines, 30,000 lines. Or, I mean, if you work at a company with a Python app or something, like I used to work at Klaviyo, which is like a email autoresponder. They had a Python application for their backend, and it was millions of lines of Python. That's never going to happen in a Solidity code base. So I think in terms of the amount of code, I think, yeah, generally, personally, I do a better job of documenting the code and stuff like this, probably just as a byproduct of the fact that there's not that much code comparatively to other languages. But in terms of style, I think Gas also puts an interesting consideration, because, you know, sometimes you might be doing something in Python and you're like, okay, I don't really care about hyper optimizing this. Like, first of all, we're writing Python. Second of all, I don't have to pay for gas. So maybe you hyper optimize, you over index on readability versus something that's just more efficient. So that's a difference. But yeah, does that answer your question?
Yeah.
Yeah, so let's see, and what I'm doing right now is I want to just quickly be able to just glance over all the code that they actually have and just see sort of like what we're dealing with. What are the high level features that we should try to get an understanding of. So short record facet, this is interesting. Increase collateral, decrease collateral, combine shorts, active shorts into one short. So I think another thing I want to add here is like, what are they shorting? I'm guessing the pegged assets. That's what I'm guessing. So that's interesting. Increasing collateral for the short. I'm guessing only valid short record. So obviously we're doing this for a short. Decrease collateral for short. We can combine shorts, which is just kind of gross, but we'll see. TWAP, a vault facet. Let's see what this is used for. Contract that owns all of the ETH and ERC20 tokens for the entire network. So it sounds like funds are actually going to end up in here and they'll just be moved around from other facets. Probably calling this so only valid asset. So it looks like anybody can call this withdraw ZETH. So what is this ZETH stuff? ZETH, carbon ZETH. Invalid ZETH. Interesting. What is ZETH? Okay, so I'm assuming, so it looks like anybody can call this withdraw asset function mint. All right, ERC escrowed. Here's another thing. ERC escrowed. What is it? So let's have a look at this. Okay, what is S? Really like the naming here. So let's find out what is S. IntelliJ is failing me. App storage. Let's find out what app storage is. Okay. There's a lot of stuff here. All right. So it looks like, holy crap. This is the storage for the entire application. So admin stuff like this, flagger ID counter, token ID counter. Okay. Okay, they're also, okay, so it looks like they're like pretty trying to hyper optimize this. This is probably going on mainnet. They're trying to pack these into, you know, certain storage slots. ZETH to Vault. Okay, so it seems like ZETH is a defined token address. I wonder if that's, maybe that is something in here in this tokens, maybe that's one of those. And then there's a vault that corresponds to it. And that's seemingly what you deposit into the vault. And then we're going, okay, so from, there's a number for a vault, and that corresponds to something like this. There's vault bridges. That's interesting. Then we've got a mapping of the account to the vault user type. All right, so there's a lot of stuff going on. So here's our order book. This is related to these. This is how these are stored. This is, we've got the bids, the asks, shorts, short records for whatever reason. So the difference between shorts and short records, this is just asset to, so for every asset there's an ID that goes to the actual order. Now here for every asset there is a mapping of the account to the ID to the short record. That's interesting. So it seems like this ID is on an account basis.
Yeah, this is almost like I would probably need to visualize it, I think, because there's so many like mappings everywhere. Especially that one is like a map inside a map inside a map.
Yeah, yeah. There's literally 1, 2, 3 here. What we should be seeing when we look at the short facet again, we should be seeing per asset, per account, and then per account has an ID. So let's see. Can I find that facet again? Short orders facet, short record facet. So I'm giving, let's look at increased collateral, for example. Asset, we've got the ID, and then I'm assuming they're using message.sender. So yeah, exactly. So let's have a look at this. All right, I guess this is in modifiers. So let me just pull this contract modifiers. We want to get this on the side. Okay. I'm looking for this. So the shorter is that message.sender. If it is canceled, then it's invalid. Okay. Cool. All right, so we've got an understanding here. So this modifiers contract, looks like everything inherits from this modifiers contract, which seems a little odd, as everything has app storage. So what's going on with that? Why does everything inherit from modifiers? And then, so I guess my question is I want to understand, how do we change storage? How does that happen? Where do the S stores and the S loads happen? So let's see. Let's just look at this create ask. So it creates ask order in market. Incoming ask created here instead of, yep, stack stuff. Okay, so we're creating an ask for an asset at a price, the unit price in ETH for ERC sold. So that's interesting. I wonder if this is like a limit, if you're setting a limit, and that's the price I want my limit to hit at. ERC amount, this is how much I am asking to be sold, or I'm selling. So ask is, I'm basically putting my ERC20 up for sale, so I'm assuming this asset. And then a bid would be, you know, I'm bidding to fill the other side of this in our order book. So ERC amount is market order. Okay, so there's something I'm noticing right away here is, you know, does this have a different meaning, market versus limit? And then, you know, can this give them? Because it seems like maybe the price literally means nothing if it's a market order, or maybe it's like a slippage type thing versus if it's not a market order, it's a limit order, then it would actually probably be the trigger price for the limit order. So that seems, could be a little bit inconsistent there, so that's just something I'm going to note. Order hint array. Array of hint ID for gas optimized sorted placement on market. Those collection of words don't really make sense to me. A hint ID, okay, so for sorted placement on market. So I assume we will come to see what that means. I'm going to ignore that for now.
Just a slight tingling of a red lamp, I guess, if you could gas optimize the sorted placement on market. I don't really know what that means, but could you also manipulate that, I guess? Would be one question.
Yeah, absolutely. Like, is this, especially because it seems like, right? I mean, it seems like anybody can call this function. So first of all, anyone can provide this. Like, it seems like they might be expecting the UI to be nice and provide the right thing. Anyone can provide this. What if they don't provide the right thing? So yeah, anybody can specify the ask that they want to create, but then this order hint array seems like it's something that's like just helping out their system. But of course, what if I just give the wrong thing? So, okay, so ETH is the price times the ERC amount. So it seems like the price here is denominated in ETH. So that's something I'm going to note. Seems price is denominated in ETH. So this isn't like the canonical USDC price or USD price. Otherwise, this would not be an Ether amount. It would be a USD amount. So we'll see if that's consistent throughout the system. The min ask. Okay, so they've got some validation there for min ask. Interesting. Just based on that, I'm just thinking max ask. We'll see later on if that's something that they should have. Okay, so ERC escrow, that's where we see this again. So if my ERC escrow is less than the ERC amount, insufficient ERC escrow. Okay, so I think I'm starting to get an idea of what you have to do is you have to escrow a certain amount of these ERC20 tokens before you can create an ask for them. So there seems to be like a two-step process here. I'm guessing that the vault allows you to escrow these things. Okay, so we've got ETH escrowed. Okay, here we go. So ERC escrowed. So if I deposit into the vault, then I deposit this asset, I deposit this amount, which is like really annoyingly optimized for a uint 104. Like, come on, guys. This is why we need layer 2 as well. So deposit asset, burn from. So, okay, so immediately I now know that this asset, this is not like wrapped ETH or something like this. I don't think it is, because like you're not going to want to, like if they approve you for wrapped ETH, you don't want to burn that wrapped ETH. This has got to be one of their assets. So let's have a look at this. Only diamond. Okay. Not equals diamond. That's right. That's right. So the, yeah, I'm just thinking about storage collision. Okay, so yeah, so all of this, since this is a diamond contract, all of these facets, they will be technically being the address this during execution of any of these facets is the diamond contract, since the diamond just delegate calls to all of those different facets. So they have the permission to mint and burn whatever this asset is. I don't really know what this asset is supposed to be. Like you can create, this is the thing that you can create asks for, the market. So it seems like the asset is a market asset. So let me just go back to the vault here again. Deposit asset, deposit ERC20 token into the market system. So this is like a market asset. That's what it seems like. So they burn from, so somehow you get that asset. That remains to be seen. So how do you get market assets?
Is the SZ ETH, is it pegged to the ETH, and that is what you can withdraw?
Yeah, so Z ETH, let's see, deposit Z ETH into market system. So let's see, Z ETH, and then an amount, which is obviously a uint 88. If Z ETH is the carbon, okay, so there's a vault for that, that's specifically for that. Else there's like a mapping, and then so that's your vault. Okay, so this is interesting. Okay, here we go. Here's a key detail. Okay, so here let me just have a look at this vault user mapping. Okay, so it's from the vault to the account to some type here. So when you deposit Z ETH, your vault balance of the message sender, your ETH escrowed, gets implemented, or gets incremented. And we burn your Z ETH. Let's see where this is used.
And was there one for ERC escrowed or as well, or was it ETH escrowed?
Yeah, so there's ETH escrowed here, and then ERC escrowed here. Let me see, I can zoom in a bit. Okay, cool. So we want to understand what's this ETH escrowed. Create bid. Interesting. So, aha. So the ETH escrowed matters for the bids. So when we're creating a bid, we need to make sure the ETH escrowed is less than the ETH amount that is being asked for. So let's see. Yeah, right, because I'm going to be buying this thing. If this bid gets filled, the money is going to come from the amount that I have escrowed. So, follow-up question. Here's like, I guess we'll start another potential issues. I think this might be something that might get done. We'll see. Situation. I create a bid. At this time, I have enough ETH escrowed. Time passes. I remove escrowed ETH. My bid gets filled. Where did the ETH come from? So that's something we'll look at. Okay, so the ETH escrowed matters for the bid. And then the ERC escrowed matters for the ask. Okay, so then the question just becomes, when I withdraw Z ETH, for example, we get the right vault. If amount greater than, obviously you don't have enough. That seems like they don't have any protection on that. Oh, okay, hold on. Yeah, I mean, this looks like it might be an issue. So what I'm thinking is this ETH escrowed, it gets decremented. We only validate it when we first create this bid. So we'll hop here. We validate it here. And I'm guessing the bid doesn't, for example, if it's a limit, like not a market order, it will stick around. It won't get filled immediately in this transaction. So let's see. So we set all this stuff on the bid. Okay, so yeah, you can have market or a limit. Oh, they're actually doing matching at the smart contract level, which is surprising. Oh, man. So they must be sorting these asks. I'm actually expecting to see something like a loop somewhere. Okay, here it is. Here's the loop. Okay, so I think what they're doing is they're going to be iterating through the asks, and they're going to, yeah, almost kind of do like a, kind of like how Uniswap has like a, you know, price limit or something like this. They're going to swap up to something like your price. Oh man.
I'm immediately thinking that, I mean, for loops are already like kind of scary for DDoSes.
Yeah.
Like wild true loops, and this seems awfully nested as well. Like, yeah, I'm smelling a lot like a lot of code smell here.
Yeah, no, that's a fantastic intuition. I think there is exactly an issue just like that with this. So while true, let me just confirm they're getting the lowest sell, and they're going sell by sell. So let's just draw this out so we can visualize it. So I think they do have an issue here. Let me find where. Okay, right here. So here's what they're doing. Need to be able to zoom in. Okay. So they have, let's make this a little bit bigger. They're trying to do an order book, which is better done off-chain, at least from what I've seen thus far. So when we have an order book, we've got bids, and we've got asks. and we're trying to just match these. And so with an ask, like let's just look at, a bunch of like limit asks. So there's a bunch of asks. Let's say price goes down here. So the asks up here are at a higher price. And I suppose I'm going to represent asks like this, like little bricks or something. And each ask has a certain amount of like size or quote unquote liquidity. So let's say this ask has a liquidity of 10 ETH or something like this. This ask has, something like 5 ETH. And these are all at different prices. So let's say this is, we're just going to totally make up prices. We're going to say this is at a price of $5. This one's at 4. And at 3, there might be increasing liquidity, people who are looking to get filled. Maybe there's like 15 here. And let's say this is where the current market price is at like 2.5 or something like this. Now, if I come through with a bid, what they're doing is they're saying like, okay, let's say I have a bid, it's a market bid to, let's say I want to buy 20. Like that's how much I want to buy. And we'll see if they have like a price limit or something like this. See what that looks like. But it looks like what they're doing is they're going through in this while loop, they're saying, okay, here's the first lowest ask. This is the best one that any bidder, any market bidder, they want to get filled at the lowest price, right? So we're going to start here at the lowest ask. We're going to get you filled there. So we match these guys up, right? So now this guy gets 15 from this, and he gives the asker their $3 per 15. And so the bidder, they're not fully filled from that. They filled 15, so they're partially filled, but they still have 5 left over. So they get 15 filled, and you have 5. Now this guy, he's fully filled. So in our while loop, we go to the next one. This is the next lowest. And they literally have a function, get lowest sell. So and this is inside of the while loop. So we do this over and over again. And then, so this guy's 5. So perfect. We'll match these guys up. And then now this guy's completely filled. This guy's completely filled. And voila, that's, I think, pretty much what they're doing. Now, the issue that we just pointed out is, okay, well, this is done in a loop, and there's like a lot of stuff in here. And there's even like internal functions, there's memory getting allocated. This seems expensive. So what I could do as an attacker is, let's say this is what our asks look like. What if I create a bunch of different asks, and it's like, so this is really, you've got like a ton of zeros here, right? Because if it's ether, there's like 18 zeros to say, hey, I've got 10 ether here. Bunch of zeros, right? So these are actually like veritable amounts of ether. ... What if I just put 1? A singular way. Now I'll have to check. I think they do have some sort of minimum deposit check, maybe, or minimum ask. They might not. They actually might not, and this could be a really big issue. But what if I just create a ton of these? And they could all be at like, pretty much the same price. This means now if I come through and then maybe there's a real ask here with like 20 ETH with the appropriate amount of zeros. All of these are all trivial amounts. These are essentially worthless. So if I come through with a bid, let's say I have 1 market bid and I want to buy something. I want to buy, maybe even just 5. We've got to go, and in this while loop, we've got to loop over this. We've got to loop over this. we gotta look over this. We go here, and then what happens here? We run out of gas. And so we can never fill this. And basically the entire exchange just gets completely, basically DOS. Like you can't really fill anything unless you're going to fill it in these really small increments. So let's see if that's possible. So the question we need to ask to see if that's possible is we go to create, we need to go to the ask facet, right? Creating asks. Okay, look at this. So they've thought of this, and they've got this minimum ask ETH. So let's see here. Okay, they get the app storage. Okay, so it seems like they're allowing some arbitrary thing that will get set in the mapping. But that is basically going to require that, hey, if you're going to do this, you can still do it. You can still do this. You just have to put like a minimum amount of value into each one of these such that, you can still technically pull this attack off. It's just going to cost you a significant amount of capital. So that still might be like a veritable issue, even with this minimum. So maybe, even like a warning to say like, hey, you better keep an eye on manipulation because it might actually end up being profitable if I had some sort of strategy. I don't know, even with the shorts that they have on here, can I like allocate a certain amount of funds to basically shut down the order book somehow? Yeah, that's just a question that, yeah, it's a knob for sure.
So I'm thinking like worst case scenario, like there's an attack vector utilizing this, but even in the best case scenario, so to speak, would it really manage to do all of the matches? Like, I mean, it can still like fail under load, right? Like it can just be a lot of asks and bids and
yeah. Let's have a look at this. As painful as it looks, let's just try to have a quick understanding. No cells left after a partial fill. Yeah, there's just so many edge cases. This is really just not something you want to see implemented in Solidity. This is something that, is probably like most protocols that try to implement like an order book. They do it off chain, and then you would just have the settlements happen on chain that a keeper is able to, make the settlements. And there are ways to make that trustless. So,
and also like having this order book on chain, I mean, front running issues, right?
Yeah, it's another great thing to consider. So yeah, definitely if I saw somebody was about to get filled, maybe you can front run them and you can eat up the liquidity that they're about to use, and then you cause them to have to get a match with somebody up here. And then now all of a sudden they're getting a way worse price because I ate up all the good liquidity. So let's see. Like if the incoming bid is at a greater price than the lowest price, then it seems like we actually do it. Else, it seems like we add bid, so it's almost like we stash it. We match the incoming bid. What does this do? Match incoming bid, asset, match total. So match total let's look at this. Of course, it's a struct. So this just carries the information about, okay, how much was filled, you know, throughout all of these iterations, throughout all of these different matches. Rates queried. Save gas when matching. Interesting. So a lot of stuff going on there. And of course, another huge function. The short was matched. And they're doing all this stuff.
So something that me and EVDoc realize as well is when you have a function like this, it becomes really difficult to unit test it properly.
Yeah.
It can fail in a bunch of different places.
Yeah, 100%, especially like when you have like these functions within each other, like this is just a part of another huge function. Okay, so, and then this is interesting, ETH escrowed. So this part is really the interesting thing to me. So the app storage, the vault user of the incoming bid. So we're changing both the ETH escrowed and the ERC escrowed. Okay, so in a bid, we've deposited ZETH, and they're going to basically subtract, okay, how much was filled in ETH, basically how much of my Ether, so on this side, this is, I'm providing Ether and I'm asking for 20 ERC tokens. They're providing ERC 20 tokens and they're asking for Ether. So with this, the bidder, they are paying ETH from their escrowed account, and then they're receiving ERC 20 tokens, which is, you know, what they got from the bid. They're receiving that into their escrowed account. So it looks like they're never actually transferring tokens. They're just like, this is actually pretty interesting. So everything in the vault, like literally when I open a bid or an ask, all of those tokens go to the vault. That's what it seems like. And then they actually never leave the vault. Even when my bid or ask gets filled, the only thing that changes is my ETH escrowed and my ERC20 escrowed. So that's interesting. And I mean, I think that's pretty good. I mean, it minimizes the like external interactions that we have to make and things like this. It might even make things easier to, you know, if you wanted to support tokens with callbacks or things like this, you might not have to worry about that. So I'm going to ignore all of this logic because it seems a little bit more deep than what we need to understand at this point, but I think this was important to see. So let's go back, and that will just happen every time at the end of a bid match algo round. So this is interesting. All right, so that's all we're going to look at for the bid match algo. We don't want to get too much into a hole. Okay, so I think, I mean, I pretty much understand, like you're just going to get matched if your price is, you know, something that could be fillable with the lowest thing. If it's not fillable, it seems like they just create another bid for you that I suppose will sit as sort of like a limit or something like this. So that's the bid side of things. So that is, I guess we've looked into bids. So I guess the biggest question I still want to ask is, how do I mint these Ditto tokens, these pegged assets? What's up with this? I think we want to look at It's almost as if they lied to us. This is not what I was expecting from this protocol. I was expecting something like DAI, where you just put down collateral and you mint some sort of stable coin. But I don't see that. So I think it might be helpful just to quickly look at their documentation again. So after having a quick look at the code, usually it's nice to go and look back, and then now we can understand things at a deeper level. Okay, so it's a decentralized pegged asset issuance protocol built on Ethereum. So let's see, where pegged assets are ERC20 tokens that track the price. Okay, this clicks now. This makes sense. So the pegged assets that they're talking about, this is when let's go to the vault. This is when they like deposit asset. This asset, which is their little mock token, this is what they're talking about. So I still have to answer the question of, okay, how does this stuff get created? And it looks like this Ditto contract is how that happens, but that makes sense. Pegged assets are ERC20 tokens that track the price of a targeted asset. Users can mint these Ditto assets by providing collateral in the form of staked ETH. This enables users to get price exposure to pegged asset. Users will be able to deposit staked ETH onto the Ditto ETH exchange to enter a long or a short position against particular pegged assets. You can earn yield in the form of ZETH, which will come from the staked ETH. It will also be loaned staked ETH from the long trader. This additional collateral earns them staking rewards. You can create, manage, and speculate on pegged tokens that can represent any financial instrument in the world. Okay, so there's a bit going on here. So you have these synthetic assets that you deposit into the vault, and then you can essentially trade them on their order book that they've created. And those trades will just get settled, and they'll basically just manipulate the storage of the escrowed amounts for your account. So that is making sense. I'm interested about the creation of these assets. So I think we want to look at Ditto. Okay, so obviously only the diamond can call it. We're minting. So what is this? Where do we use this? Is there any Ditto dots? Yield facet. Okay, this seems like it's something else. Maybe a reward token. Ditto match reward. Oh, maybe this is this ZETH? Is that what it's supposed to be? Let's see. Let's see, what is tokens? Okay, it's a DAO token. Okay, so we can ignore that. It's not too interesting. So it looks like the asset. This is meant to be used for ZETH. I don't see a ZETH.sol. I don't see that. So maybe that's just a use case of those. Stablecoin for USD backed by ZETH. Interesting. Yeah, via asset.sol. Okay. So I'm assuming they'll have a price. So maybe like a mapping where you're able to get the price for whatever the asset is. So that should come up when we're creating bids and asks. let's see, anything about a price here. Price is the price that you provide. That's also kind of like, you know, yeah, it also seems like this, the price that I give actually, this might be, this could be good actually. Here's an idea I just had. So when I'm creating an ask, they have this validation that there's the minimum ETH here. Now this is based on this ETH, like it's computed right here. The price, however, is user defined. And so let's say, you know, this could be my limit price or something like this. And there's no validation that the price is like a reasonable thing from what I can see. So what if my price is literally one way, and then no, that would just make this thing smaller. We want this thing to be bigger. So what if I make the price a huge number? I think this will actually work. So let's see. So we potentially turned a medium into a high with this. Maybe even a critical, depending on what the argument is. So they have validation to make sure that you can't just, you know, do these one-way things. But the validation is based on the price that I arbitrarily provide. So what if I say I want to open an ask, and it's a limit ask. And the ask is that when the price goes to something incredibly high, so, you know, something that it doesn't even have to make sense. It could just be a really large number. That's my limit for my ask or something like this. Now, multiply that by the ERC amount. Well, I'll just put one way. And so these multiplied together, this might actually get around this minimum ask ETH. But I'm getting away with only having to put down one way, and that one way is what will get subtracted from my thing when I create this ask. So of course they're going to run the cell match algo, and then of course the price for my ask is going to be greater than whatever the highest bid is, of course. And so what will happen is it will get, you know, left over as a bid, since they can't match it. So I can do this a ton of times, right? And then I can just effectively do the same thing again and again and again. And now I've gotten away with only putting down one way for a ton of asks. Now, the only limitation here is that these are now all at some ridiculous price. So there's going to be all the reasonable asks down here, which are at a reasonable price. You know, maybe they're at like $20 or whatever. These are the ones that are going to get filled first. So it's not as high impact as you might think, but that's interesting that the validation is dependent on a user-defined input. And so, yeah, when this is computed, it's just kind of arbitrarily based on the price that's given. And so, yeah, I think a stronger validation would just be on the straight up. Yeah, I don't know. So that's something to note. But okay, so our 55 minutes are up. I think this code base definitely ended up being a little bit more involved than I thought it was going to be. They've got a lot of stuff going on, a lot of different features. But do you guys have anything that we should look into before we wrap it up on this code base?
No, it was really interesting following your thought process.
Great, yeah, and I think what we'll do is next week we have another session like this. Hopefully we'll have more time. What we can do is we can pick up with the same code base, so we can go a little bit deeper and find some more interesting things. Right now we were just trying to get a grasp on what this code base was doing, like what's all the code. There's a lot of different facets here. So next week we'll try to dig in and find some more interesting stuff. But yeah, that's really just like even the first couple of days usually during an audit, I'll spend probably not even looking to find issues like as aggressively as we were today, but just trying to understand all the different stuff that's going on as fast as I possibly can. And I'll usually spend a lot of time talking to my the fellow auditors who are working on it with me, trying to get what they understand about the system. Usually they've done a good amount of research and they can get me up to speed really fast as well. So yeah, that's just the approach I like to take, and then we've got these goals that we can finish up next time. So what we've got here is basically just a breakdown of the only two roles, the two people who are basically involved in a code walk. First of all, we have the walker, the person who is basically walking through the code base. You just explain the code base throughout the code walk. First, we'll just start with a quick introduction of the code base, of the design, of the concept. Of course, for you guys are all working on Perpetuals protocols, so we're all familiar with the concept of what it is, and then maybe any noteworthy design decisions that were made that should be called out at the beginning. That might be something that you talk about. That would just be brief, probably 2 or 3 minutes. And then the walker will basically continue to explain areas of the code base that the reviewer will basically ask to see. So as a reviewer, you're guiding the walker through sort of basically a live audit, a live interactive audit of the code base. And so walking through the pertinent functions line by line, while of course we don't need to completely focus in on the most trivial aspects unless we want to double click in on that. But basically just walking through what is this function doing and things like that. You'll see exactly what that looks like. So yeah, like we said here, and we're just gonna describe, okay, maybe that might be a little unexpected. Why did we decide to design it that way? Things like this, or just answering any questions that the reviewer has. And so the goal of the walker is just to effectively communicate the code-based design, how important functions work, and explains why certain design decisions were made. And of course, why is it useful to be a walker? Why is it useful to even do this? Well, first of all, as a walker, we're going to get better to effectively communicate code, which is increasingly important if you go and you want to work at an audit firm or something like this. The ability to communicate what certain code bases are doing, and they might even have similar things where if you're auditing as a group, which is something that sometimes we do at Guardian, they might have things that are similar to this. And of course, ability to defend design decisions. This is something that will just help you as a developer in general. The ability to critically think through design decisions and then have a proper defense or just reasoning for, okay, this is why we decided to go with this. Of course, it will potentially help you understand your own code base at a deeper level. You're going to get a different aspect of a reviewer asking questions and prodding, and you're going to basically be able to perhaps understand the concept of perpetuals deeper through the questions that they ask and the things that they point out. And then of course you're just going to get feedback on the design of your system. Maybe they point out a few edge cases that you need to handle and things like this, and you're going to basically just see okay, that's interesting, this is the point of view that the reviewer had that maybe I didn't think about that thing, or something like this. And so basically you're getting a free audit as a walker. And you might even choose to point out, hey, this is an area where I'm actually unsure of. What are your thoughts on this? Or how would you, improve this or something like this? Or how would you handle this edge case? So that is essentially the role of the walker. And then, of course, the role of the reviewer is to guide the walker after the walker has finished their high-level introduction, and then we'll basically, now we're asking like, okay, I would like to see, could you help me understand how somebody opens a position? How does that work? And then the walker will go and walk through the logic for that. And then as the walker is walking, the reviewer may, ask, why did you decide to design it that way? Point out maybe, what if you did it this way? Why did you decide not to do it this way? Did you consider that, or something like this? Ask if, have you handled, somebody overriding a position or something like this? And then maybe you do spot like a potential bug or vulnerability or stuff like this. Maybe that's something that you would point out as well. And then generally just ask further questions to understand the code base. That's the main goal, is to understand the walker's code base, and then to provide some valuable comments or suggestions that may help improve the code, whether that be design or bugs or edge case handling, or anything like that that might be worth considering. And then, of course, why is it useful to be a reviewer? Well, it's actually pretty straightforward. Being a reviewer is essentially being a live auditor. So you're sort of doing an interactive audit. And this is basically going to allow you to hone your ability to ask the right questions when you're going into an audit. And it's going to make you a lot more efficient. It's going to almost be a forcing function to make you a lot more efficient at understanding code base very quickly, because we're only going to do this for, like 15, 20-minute periods. Your goal is to understand the code base, understand how it functions within that very short time frame. And this is something that's going to exponentially help you as an auditor. If you can get to understand a code base very quickly and understand the questions that you need to ask of the code to do that, this is going to be a huge asset too. And then even if you're not a reviewer, you're somebody who's just watching this exchange and you're watching how the reviewer is asking questions and navigating the code base, you are probably going to be able to glean a good amount of, knowledge just based on, how is this reviewer approaching this? Oh, I wouldn't have thought of that question, or I wouldn't have thought of that edge case, or things like this. So you'll be able to learn just from even watching the reviewer and improve as a reviewer yourself. And of course, if you improve as a reviewer, this is going to be pretty much exactly mappable to improving as an auditor in general. We're just sort of, taking the amorphousness of sitting down and reading a code base and taking that into a live and interactive situation. And so this is something that I think is, just doing a number of these in the past has given me a really good boost in, being able to understand code bases and ask the right questions. So what we're going to do now is we're going to actually do one of these, but
Sounds good.
all right, cool. So let's go ahead and let's pick an order. So we'll go ahead and first we'll have, how about EVDoc and Kenny, how about you guys go first? You can, I don't know, whichever one of you wants to do the code walk, and then I'll be the reviewer just to show folks for the first time, like, what it would look like to be a reviewer.
Yeah, sounds good. EVDoc, do you want to do it from your branch, or do you want me to do it?
I can do it from my branch, the one in my code editor or in GitHub.
Yeah, I think code editor is good. And yeah, I know, so you guys might have merge conflicts and stuff going on, so that's fine. Definitely, like, don't worry if, stuff isn't even, like, half implemented and stuff like this. Definitely don't worry about any of that.
Okay, so let's go to my code editor.
Yeah, absolutely. So just go ahead and share your screen, and then you can get started off. We'll do, like, a brief just overview of the design and the approach that you guys took, and then we can dive right into just walking through some interesting bits of the code, and I'll kind of try and ask some interesting questions and see if we can find some interesting stuff. And then as we're going, folks, feel free to drop any questions that you have for EVDoc in the chat, and then I'll go ahead and ask those and stuff like this if you guys have anything that you guys want to see in the code walk.
Are we allowed to help each other, or is it better that only one does it?
Yeah, I think if there's like something that, you know, maybe somebody else implemented, yeah, totally fine for the other person to jump in and take over that part.
Yeah, I think me and Lividoc has done different parts, but we try to get as much understanding as possible. But yeah, Reda, just ask or if you need any assistance.
Okay, so let's go. I'll share my screen. Okay, great.
All right, cool. So what we'll do is we'll just start off. You could just give, you know, maybe just a high level overview of maybe the external functions you chose to have, and then, you know, maybe some design decisions, and then we can go from there.
Okay, so let's start with the main functions: the deposit collateral, withdraw collateral, deposit and withdraw. So deposit collateral and withdraw collateral are external functions for users, traders, to deposit collateral in order to be able to open a position. Nothing special about it. So after that, we have the deposit and withdraw function. These two functions are using the ERC 4626 built-in functions, the deposit and withdraw. We just update the total liquidity deposited, this storage variable, and we call the deposit and withdraw from ERC 4626. So we've made a decision regarding the leverage in order to, because of precision loss due to truncation. So by doing this, we've got much better precision, because, for example, if a trader opens positions with a leverage of 20.9, it will be truncated to 20. So in order to avoid this kind of issue, we decided to multiply this leverage by 10,000. And we've made some changes accordingly in the calculate leverage function. Here is the calculate leverage, calculate user leverage. So in order to get the right leverage, we multiply the collateral by the decimals delta. Decimals delta is 18 minus 6. 18 is the decimals of BTC and 6 of USDC. And then the formula is this one. So after adjusting the price feed by this decimal precision, we can compute the user leverage, and we check if it is greater than the max leverage. So here is the formula, and this is design. This is to avoid the precision loss in the leverage.
Yeah, what's the decimals of the underscore size? Like when you guys store sizes, what's the precision or units for size?
There is no decimals for size. Like if you want to open a position on WBTC, one WBTC, you just enter 1, and it will multiply 1 by the WBTC price here, the price from the price feed, and it will be divided by the user collateral in order to get the user leverage.
Okay, got it. So if I wanted to open a position with a size of half a Bitcoin, that wouldn't be something that we could do?
you're right. A trader cannot open a size of half Bitcoin. So, yep, you're right. It should be 1, 2, 3, 4, or 5.
Yeah, that might be something to consider. Like maybe adding, I like your idea of adding like a adjusted for the price feed. That's actually something that I did as well, as add like an adjustment factor for the price feed so that, you know, avoiding precision loss and having stuff like this is easy. So that's great. I think, yeah, it would be good to be able to support like, you know, fractions of a Bitcoin size or something like this as well.
Yes, we will implement it. We didn't thought about it, but it's a great idea, of course.
Cool. And then, so I guess I'm interested in, so when you're depositing liquidity, you're going over that a little bit earlier. So I saw there's like deposit collateral functions and then like deposit actual liquidity, like ERC4626 functions. I was interested, how do you differentiate the like collateral balance that people deposit into the contract versus balance that was deposited by LPers, so that when LPers withdraw, they can't withdraw collateral from other users?
Yep. In ERC4626, the total assets function is used. So we override this function, and first thing we subtract the PNL, and regarding the collateral, I think it was in the update liquidity function. Let me check it.
Yep.
Because we don't use the USDC balance of this contract, we are trying to keep track of the variables.
Yeah, the total liquidity deposited.
Total liquidity deposited to make it simple.
That makes sense. Yep. Yeah, and then I guess, okay, I was interested in when we're now opening a position, how does that get stored and tracked?
So we have this open position.
You passed it by. It's a create position.
Create position. Okay, so first thing we check that the leverage is not greater than the max leverage, and we check that the user, so the trader, doesn't have any open position, because we only allow users to have one position. And then we compute a nonce in order to get the position ID. Here we don't care about any collision, since a liquidator will liquidate a user and not a position ID. So two users can have the same position ID. And then we create the struct position. And there is the position ID, the size, collateral of the user, and the total value computed with the size and the current price from the price feed. The owner is message.sender, and Boolean to know if it's a long order or a short order. After that, we update open interest in order to keep track of open interest, and then we update liquidity, and this is one of the invariants. Short open interest plus long open interest in tokens times the current price should be less than the updated liquidity times the decimals delta. So this is the invariant to make sure that we always have enough liquidity. And after that, we update some mappings in here.
Yeah, and I see the position object has a position ID attribute, and then it's also stored in the mapping from position ID to that position. What made you decide? Was there like a necessity for putting the position ID on the position object?
This is a great question.
Yeah, I think, I mean, it was basically a way to be able to track all of the positions. So I think there are many functions where we rely on the position ID. So at the moment, we're incrementing it by the nonce. So there's the global nonce that's being incremented every time we do a position. And then that will help us point to which position it is. And from that, you can get all of the, I think you can get all of the information about the position. Or maybe I didn't answer your question.
Yeah. So I see we've got, so first of all, there's this feature where it looks like one user can have multiple position IDs, right? So we've got like a set where we add that position ID to. Then we have the mapping where we can go from the position ID to the position info. But I think, is it always true that we will access the position through the positions mapping?
I think we've done this we've done this because we were thinking that maybe a user should be able to open multiple positions, but we decided to keep it simple. But in fact, it could be a good thing if a user can open several positions. But at the moment, a user cannot open several positions; he can open only one.
Yep.
Yeah, I think if you go to if you go up to the mappings, it will be a bit clearer. So at the moment, we have a uint 256 to position. That is basically position ID to position, and then we have an address, which is the user address. So we are able to see how many positions a user has, and we're using an enumerable set so that we can access certain values. So these are the ways that we track first all of the positions, and also all of the positions that a user can have. And yeah, for a moment it's just one position, and maybe we're gonna keep it that way and use maybe like position delta or something that could make sense.
Yeah, so the way, it seems the only way to access the position data is through this mapping, right? That's where the position data is stored.
Yes.
And so you have to have the position ID to read the position data, right? And that's the only way to access the data. Presumably we always know what the position ID is, because that's how we're able to access it in the first place. So I think you might be able to remove that position ID attribute on the position object, since we'll always have it, right? Because that's how we access that data in the first place.
I'm not sure I follow. Are you talking about the create position?
Yeah, so if we look at just the position struct, so like the definition of position, yeah, so the first attribute there is the position ID, but we'll always like have the position ID, because in fact the only way to access this data is through the position ID. So I think just like an optimization for the amount of storage slots they have to use would be we can just remove that.
I got you. Yeah, it's definitely redundant if we do it this way.
Yeah, I think definitely I like the design of having this mapping where that's like the source of truth, and then if we have like an enumerable set for the users so that they can have multiple positions. Maybe in the future we want to support multiple index tokens, in which case this would be really valuable, and that's a good way to go. But all right, that is basically the 20 minutes. So great job, EVDoc. Great job,
Thank you.
Kenny. thank you guys for sharing the code. I think you guys have a lot of great designs in there, and I think that you guys are gonna have fun. I mean, I think you guys already had a head start on implementing Mission 2, but so Mission 2 should be pretty easy for you guys. But yeah, great stuff.
Thank you.
All right. So let's see. Does anybody want to volunteer to go next? All right. All right, and definitely, I mean, you guys don't have to feel, pressure. It's not like a super prepared thing or anything like that. But Paul, do you want to go next and do, I guess, since Dimo's not here, do the code walk?
Yes, of course. Of course.
All right, cool. So let me know if you're able to share your screen, and then we can get things started. You just give a quick, brief overview of, maybe the overall important external functions that you have, and then what we'll do is we'll hop in. And does anybody want to try to be a reviewer for this one? Otherwise, I can go again if nobody wants to.
Everyone can see? Hello?
Yes.
Yep.
Yes?
Yeah, it looks perfect. Yeah, it's big enough to see, so that's great. All right, cool. So before we get started, does anybody want to be a reviewer for this one? Or anybody want to try it out? Anyone want to try live auditing?
Okay. I want to show you first one. Yes. You can see the library?
Yeah, I can see it.
I can't see anything on my end. Sorry, I can't see anything on my end for some reason. But
okay, hold on. Let's see. Well, we'll give it a second poll before we get started. So I think if you leave and join, that might do it. Otherwise, we'll have to make poll reshare. So maybe try that. All right, and it sounds like I'll be the reviewer again, unless anybody wants to do
No. Okay. Sorry. Didn't listen you, Owen. Follow the contract.
Yeah. So I think could you try sharing your screen again?
Again. Okay. What now? Now it's right?
Okay, yeah, I can see it.
Okay, perfect.
Other folks can see it.
Okay, now. This library I create for take the price from Ethereum and use it. Okay, that one have this function for conversion the USDC or day amount and for the value the Ethereum, and this one is also for convert rate and take the Ethereum amount and the return value in the and that one is the contract. The perpetual guardian is RC 4626, and I get the struct position, and this one is position summary, and this I create this constant variable. This is max leverage, and this one is utilization percentage. And I put the library here for can take the price value from Oracle Chainlink, and and I create this constructor, and that one put information from the RC20 token, and this one is the day, and also I put the price feed for take the price from Ethereum and USDC. And also I create a function add liquidity for to deposit to Perpetual Guardian. Or the liquidity providers can deposit to as Perpetual Guardian, and also remove liquidity for people liquidity providers can withdraw the money. And also I create token position, and the traders need to put the size, collateral, and if it's long or it's true, or it's short. And this one have this. I create this variable because it's I need for take the Ethereum value, and also I create the this variable position for create the struct the new position from trader, and the trader can put this information and put here. And for example, the trader one put size is divided from current Ethereum price.
Yeah, and similarly
yes.
to the last code base we looked at, what are the decimals and the units of size? Is it just like 1 for 1 USDC or something like this?
Yes, no, I started working with this today, but I didn't finish, and I stay here in this branch.
Yeah. Okay, yeah. So similarly to be able to support like fractions of a USD value. Yeah.
Okay. And yes, and the next one have the check position health for the protocol half of security when the trader create this position have the health sufficiently for create this position. Okay. And when after they finish the function, the function of data position summary and to information, and that's information.
Yep. Yeah, that updates the open interest and stuff like that.
Sorry, wait a minute.
Yeah, so this update position summary function that updates like the aggregate size and stuff like this.
Okay, and that function it's here, and this function aggregate and size in DAI and in Ethereum, and also if it's long, put and here, if it's in short, put and here, and because after I create these variables. Before I create these variables, total long position and total short position.
Yep.
For put this information.
Okay. Yeah, that makes sense. Yep.
Okay. And also create a function get position, and it's necessary put address owner for know the position from him or her, and also it's possible increase position collateral, and it's important have a current Ethereum price for know what is the price at that moment, the amount and to deposit of new collateral.
Yeah,
and also
one small note is we should just be careful to use safe transfer from whenever, even though it might be DAI and DAI is always compliant. If we wanted to switch that token out to something like USDT or something like this, then we want to use safe transfer from, or if the transfer failed for whatever reason or something like this. Yeah.
okay. And after I have again this this function for know if held or not the position, and put the true position, the new collateral, and
Yep.
and also traders collateral, and also positions from a message sender the equals position.
Okay, I see. So in contrast to the code base we just looked at, you guys are tracking the amount of collateral that traders have versus Kenny and EVDoc were tracking the amount of deposits that were made. And so I assume when you're returning how much assets somebody can withdraw when they're withdrawing as an LPer, I assume you guys are accounting for subtracting out that collateral amount versus Kenny and EVDoc were basically saying this is the total deposits and they didn't have to subtract out. So I guess, do you guys have like a total assets function or something like this that you overrode in this contract?
But, and do you want to say, for example, they used collateral from
right here, total assets.
One trader or total assets?
Yeah, exactly, total assets right here. Let's see.
Okay. Total assets, it's here, and I create this function, and this variable is for get traders PNL. It's here, this function, and I create from no, it's from RC4626. If not, I use super total assets for delayed from contract RC4626, and for I can use this function and put this logic. That logic put the calculation, the total assets from liquidity providers and traders, less traders PNL, and less traders collateral.
Okay, very nice. Yeah, so we can see there's really multiple ways to attack the same thing, right? So previously we saw a completely different approach where they didn't rely on the total assets of ERC4626, which is basically the balance of this actual contract. But now we have, a different way where you can do that. And then, just different ways of doing the same accounting. So very cool.
Okay, thank you. And after I have this function, this function is the get traders PNL and check position held. And this one put the position, the true position, and current Ethereum price for if the position from user is held or not. And also have a calculation position PNL, and this one the people is the necessary put the position and current Ethereum price, and
yep,
and have this logic for calculate the calculate position PNL.
Yeah, just a quick note on. So I see on lines like 202 and 203, we're casting this value as an integer. So it's a uint 256, and then we're casting it to an int 256. The only, I think it's probably a minor issue because I don't know how achievable this might be, but there is a case where this position.eth amount times the current ETH price, that could be a resulting uint 256 that is actually too large to fit into the range of values that the int 256 can support. And so in that case, you would have a overflow, and it would silently overflow, so it wouldn't revert like, like if we try to subtract 1 from 0 with, solidity 8 and up, we have just automatic panic reverts. But this casting to an int, it could potentially silently overflow and then cause like some nonsense number to be the value that is returned as that int. And so one thing that I might add here is to use like a safe cast library, which would basically revert instead of, if it were to overflow, it would revert instead of silently overflowing. So that's just one small thing. I don't know if that would be technically achievable with the position.eth amount times current ETH price, but it depends on, the index token and the price of the index token. It might be able to get that high, but that's just a minor thing.
Okay, and for possible fixed, is better use the library SafeMath, no?
Yeah, so OpenZeppelin has a safe cast library.
Okay.
And so,
yes.
Yeah, they have like safecast.2int, 2int, 256,
okay.
Whatever you need, whatever integer. And then that will basically, it will revert if it was going to overflow, and that will protect you. Yeah.
Okay. Thank you, Owen. And after have this function for get the value and get icon from Rails. And yes, I know your feedback it's necessary some change because maybe another asset have different decimals, and I want to ask about this because it's possible, for example, put here, for example, address asset, and no, it's here. I think it's better. And here, for example, amount. Yes. And for example, this one is price fit. Yes, it's the same as price fit or asset. And for example, change the logic. It's possible, for example, take the decimals if, for example, not this logic, but for example, if put this one price fit decimals, for example, because like that's it. It's okay.
Yeah. So what you had before was 1 ether. So
yes, this is the logic, but I wanna tell you, for example, if have another asset, like a Bitcoin, Bitcoin have another decimals. If not remember, but it is 8 decimals, and for have the different logic for calculate the price with a nice decimals, and take the another logic, yes, but for take the decimals, I think so. It's nice if put like this one place fit point decimals.
Yeah, 100%. Yeah, I think this is actually a good opportunity to basically hash this out. So actually, I think it's really important that you brought this up. So I'm going to share my screen, and I'll share basically how I think about this and how I think the cleanest way to handle these decimals is. So I'll go ahead and share my screen really quick just to cover this. All right, we're going here. Okay, so what Paul is pointing out here is that let's say we want to get the price of a token, right? We know Chainlink gives us prices. We'll say always with 8 decimals. They have some that have a different amount of decimals, but most of them are 8 decimals, right? So this is the price that we get back from the feed. Now, we also in our systems we have some sort of representation. All right, we have some sort of representation of like what is $1, right? What is 1 USD? And that's sort of, I mean, depending on how you're tracking positions, they have some sort of what is the size of this position in dollars, or we have to represent dollars somehow in the system. And you get to determine how many decimals are dollars, right? How many decimals do they have? So some systems, they might have no decimals, and then so literally you can have 1 way equals $1, right? That would be if I chose to have 0 decimals. I could choose to have 18 decimals, which would be 1E18 equals $1. I could choose to have 30 decimals, and then my representation 1E30 would equal $1, right? So these are all just different representations of how many decimals do I want $1 to have in my system. Well, if we want to really easily convert a dollar value to a, let's say your index token is Ether, or just anything that has 18 decimals. So we want to convert USD to a token amount. And let's specify 18 decimals. So I actually think this is one of the harder parts of mission 1, is handling these decimals and trying to get this in a wieldy way and still being able to support enough precision. So if I have 0 decimals for my USD representation, well, this might be kind of hard, or we're going to really easily run into precision loss issues where, like, first of all, how do I represent 50 cents, right? I can't do it, right? That will just get rounded off. Now, if I have 18 decimals of precision, well, that's good. I can definitely represent 50 cents. 50 cents is just 5E17, right? That's 50 cents. $0.5. But then let's go ahead and let's convert this, try to convert 5E17 to like a token amount. We've got to do a little bit of, shifting around. So if let's take $1, we have 1E18, 1 USD. I want to get this to a token amount. So if I want to just divide by the price, so the price is some 8 decimal thing, I'm going to get a 10 decimal thing. Well, that's not 18 decimals. We need something that has 18 decimals, right? So then you've got to come over here and you've got to multiply by, for example, 1E8 or something like this. Now you could do this, and you could like think through this and come up with a good multiplier for each sort of each numerator here when you do this calculation. That's one thing, one approach. I prefer to take the higher order of saying like, okay, 1 USD has 30 decimals of precision. And then what we're going to do is I'm going to make the price for each token such that when I take a 30 decimal USD value, so 1E30, and I divide it by the price, the decimals of the price are such that I will always end up, so we're going to say X decimals, they're such that I'll always end up with the amount of decimals that I need. For example, if the index token is Ether, then we need to get to 1E18 decimals for our thing. So how many decimals do we want a price to have? Well, we want our price to have 12 decimals. So then that way it can be really nice. I can just say basically, you know, size divided by oracle.getPrice or getIndex price. Boom, you immediately, without even thinking about the decimals, you just get the index token amount. And it's got the right decimals and everything. So how do we get the prices to always be this nice thing, right? What you could do is in your Oracle contract, you can have a, you know, like a token price multiplier. And this is like a mapping, right? So we can have, this could be from token address to unit 56, right? And then this will basically just get multiplied with the price feed from Chainlink. So we'll just token price multiplier. And for Ether, we'll just set this thing to 4. And so we'll always end up with 12 decimals. For Ether, maybe for, so wrap Bitcoin, I think Bitcoin has 8 decimals. So for Bitcoin, we have this equation, but we want to get down to 8 decimals when we get that resulting token amount. So if we copy this, we want to get this to 1E8. So 1E30 divided by 22, something with 22 decimals will give you a wrap Bitcoin token amount. So what we'll do is we want 8 times 14. So for Bitcoin, we want 14 in this mapping right here. So 8 plus 14 equals 22. And it should technically get plus. So this is a way to kind of hide all of the token decimals complexity, hide it away in the Oracle contract, and that way for every token that you can query from the Oracle, it will automatically give you the decimals that you want. Right? If you're doing this for your collateral token or index token, you know, USDC has different decimals than Ether or something like this. So that's just one approach, but that's a core problem in Mission 1 that you guys had to sort of wrestle with. But yeah, any follow-up questions on that? Does that sort of resonate with folks?
Yep, I have one question. It's very interesting because we talk about it with Kenny today. We were expecting Oracle to return a Bitcoin price of 8 decimals. In fact, we get 18 decimals, and we checked in Etherscan at the address of the Bitcoin USD price feed, and it's 8 decimals, but we got 18 decimals, and we don't understand why.
Yeah, so you might be getting the Bitcoin ETH decimal feed. So I think all of their, so if we go to Chainlink feeds, we should have just a list of them. So let's see one that's denominated in Ether. So they've got, you know, a lot of, like these Ether feeds, they have, let's see if we can, they have a lot more decimals.
I think so. When if put in Google price feed, Chainlink have the website from where can put the rotate the address.
What feed were you guys using?
I'm double checking right now, but I think it's Bitcoin USD price feed. Here is the address. I will paste it on the chat.
Cool.
We are using this one.
So let's go to Etherscan. What network is this on? Let's see, maybe DBank will help me find that. There might be some dust in it or something.
That one should be the Sepolia network. I have it for mainnet here.
Yeah.
Oh yeah, sorry, it's the Sepolia one.
This is the mainnet BTC used address.
Okay, cool. Let's see. Let's check it out. Okay, so we'll see what the decimals, where we have decimals for this.
Third one, yeah.
Okay, so we've got 8. And then let's see what's the latest. Yeah, so this should be, so if we do, yeah, so that should be, that looks like 8 decimals, right?
Yes. But when testing on mainnet, we got 18 decimals.
That is interesting. Using this address.
Yes, this address.
And you're calling. Oh, were you calling latest round? Is that what you're calling?
Let me check here.
I assume you're calling latest round data, and you're getting the answer.
Yes.
Okay, so let's see. Yeah, that should be.
Hey man, I actually saw what you did. Rajita, I think, didn't you just multiply it with a decimal adjustment with 10?
Oh, is that what it's doing in there? Is where
Yeah, maybe, because if you go to the oracle.sol, there's a decimal adjustment.
Yeah, that might be, yeah, and I mean, that just goes to show, like, the, you know, all the overhead with dealing with decimals that we have to do. So yeah, that might be it.
Yeah.
But yeah, okay, that makes sense. All right, any follow-up questions on this sort of logic?
No, thank you, Owen.
Yeah, absolutely. Okay, sorry, Paul. I didn't mean to take over your walk here. So yeah, I think we were looking a bit at the conversion stuff, and you pointed out, yeah, this decimal stuff. So I think, yeah, what that would look like for you guys is probably adding a mapping in this price converter, and you know, maybe turning this into a contract that has state, and then allowing a mapping in here, and then in the get price function, I see you guys are basically doing a similar thing, where we're returning answer times 1 with a bunch of zeros up there on line 12. I think what we'll do, yeah, instead of returning 1 with a bunch of zeros like that, we could return the multiplier that comes from the mapping, and then that way we'll be able to sort of dynamically turn our USD values into token amounts.
Okay, thank you.
But yeah, I think, so that makes sense for the price converter. I guess I was interested, when we increase a position, how does that get stored in the contract? How do we store positions?
Sorry?
Yeah, how do I open a position with this?
Open
contract?
position, yes.
Yeah.
I can hear you, Owen.
I'm not saying anything. Can you hear me now?
Yes. Yes.
Okay, cool. Yeah, you can go ahead and I think I'm still. Yeah, I'll stop. I gotta stop sharing my screen. But yeah, you can go ahead and just walk through this open position function.
Okay. The open position. The people put the size and the collateral, and when put this one, save of the stroke of position, and say and after and check the position held and send the day. They is the token using for the collateral. Put the among collateral and the position new and update the position summaries.
Yep. And I see. So similarly, like we saw, different ways to achieve the same thing. You guys are tracking the average ETH price, which also works. It's a different way of storing the same information compared to how we saw earlier. It was being tracked in a different way. We're storing the size and stuff like this. So yeah, that makes sense. That all looks good to me. So I think, yeah, if you want to touch on anything before we wrap up this code walk, feel free to do that. Otherwise, I think it was great.
It's okay, Owen.
All right, awesome. So fantastic job, Paul. Thanks for going ahead and doing that. Great stuff. I think you guys showed us like a different way to achieve the same sort of stuff, like with accounting and things like that. So it just goes to show like there's no one right way to build this kind of system, right? So there's a lot of different ways to achieve that. So great job, Paul. Thanks for doing that.
Thank you.
All right, cool. So, all right, we're down to our last one. So Nyan and Trisha, are you guys good to code walk? And which one of you would want to do it?
Yeah, I'll do it.
All right, fantastic.
Can you?
Yeah, let's see. Yeah, I can see it. That's perfect. Thank you.
Yeah. So we have implemented two different contracts for trader and liquidity vault easier during testing. So let's go with the liquidity vault first. So okay, let's start with trader first. Yeah. In the trader contract, we have implemented open position, increase position size, decrease position size, close position, and total open interest currently, and haven't implemented the profit and loss. We will be adding it. So in the first trader contract, these are the variables used for positions and position type. So functions are starting from here. For depositing collateral, these the trader to deposit the contract will similarly collateral function, and here in position. Yeah, so this allows the trader to open both trading position, and actually I have considered a part where a trader can have multiple positions, like for different tokens, obviously. So that's why I have collateral mapping also.
Yep.
Let me check. If in case we implement different index tokens in the future, it will be easier to like which position this like different collateral can be used. That's why if a trader is if trader is depositing $10,000 of collateral and he wants to have $1,000 of collateral for long position for Bitcoin and short position for, let's say, a wax token. So he can implement it without adding the different collaterals at a time, or he can use the collateral as if he wants.
Okay, very cool.
So, yeah. So I have also considered the condition or minimum position size, but haven't given the amount. Like, I haven't considered a minimum position. Like, we can change it anytime, or not a fixed, not a constant age minimum. So from here, as when you mentioned to implement the sizing tokens part, so we have edited it and changed everything accordingly. So it calculates the sizing tokens based on the current price, like whatever the index price is at that time, and it ensures the trader has enough collateral for the position also. Given this,
Great.
and it detects used collateral and updates the total interest for this one.
Okay, one quick question I have based on this is, if I choose to open a position, and so let's say I open, position with a size of 10, collateral of 5 or whatever, and it's a long, then if I open another position, will I overwrite the old position in the positions mapping?
No. You will have the different, no, you will not overwrite. You will get the different portion or the different collateral size, and
I think you're cutting out a little bit.
Okay, so no, you cannot override. You will get the new position if you are applying for the new long or short position.
Okay, yeah. So the positions mapping is that there's just one positions mapping for every position.
Yeah.
And
I think.
Yeah, it's keyed on like the address of the trader.
Yeah, so I think I have to have different charts here.
Yeah, and we might also add, I think, maybe a requirement that the trader doesn't already have a long position or a short position, because then otherwise we would just be like putting a new position there.
But what if trader wants to have a long or Bitcoin and again long position for it?
Yeah, if they want to have that, that's great. But they need to they'd be overwriting the old position that's in the positions mapping, right? On line 98.
Okay. Yeah, understood. But so we have to implement like if a current position is open, so they can't change position again. Even if it's different open.
Yeah.
Are you saying that?
You could tackle it a few different ways. Like if you wanted to, instead of keying off of like just the address of the message.sender, you could have like a position ID that is like the check hash of the message.sender and a position ID that is just monotonically increasing, or it could be, it could also include islong, it could also include the index token, and that way it could be like unique for type of position.
Okay, yeah, that's interesting. I'll check it out.
But yeah, I'll say one thing that I really like that you added in this function at the beginning is this require statement that the size is greater than a minimum position size. I don't know if any other code bases consider this, but yeah, I think definitely it's a good idea to just disallow like really small positions, things that don't even really make sense, like one way of size. I think those things, yeah, they should just be not allowed. So I like your intuition to add that.
Thank you. Shall I proceed?
Yeah, absolutely, yeah.
Yeah, so for the increased position size, it calculates the additional size in index tokens and ensures the trader has the required collateral, also an open position here. Like without open position, he or she can't increase the efficiency. And it updates the trader's position and also the total open interest, given the additional amount like has been added after.
Yep.
Yeah. So for the this has been added recently. So function decrease position size. Actually, we are using the storage here for positions, and it calculates the profit or loss based on the current price and also the position's entry price. And for entry, like for current price, we are using gate price from the price feed, and not the block timestamp. Like I was checking, like for some DeFi protocols have implemented block timestamps. I so to get the current at what time the trader has opened the position. But we are using at what instant the trader opens the position. So based on this, we have calculated profit and loss if like to adjust the collateral amount ultimately. Change the total open interest based on the profit and loss in percentage. And if the person wants to close the position, we have added this extra function in between the trading if the person wants to close the position. So
Okay, great. And I assume like
and
when the P&L like handling is added, when I close my position, you'll force me to pay out all my P&L. If I've like lost a ton of money on my position, I'll have to pay that out from my collateral.
Yeah,
it makes sense. Cool.
And this function is extra because I needed it for the contract. And this is a liquidity vault contract. It's purely based on the ERC 466. And we have implemented deposit and withdrawal. If the person is depositing, he should get the shares in back. And it is like we have used the previous deposit from the ERC 4626. Similarly for the withdrawal function, and this was missed during the last mission one, and that's why we added this time.
Great.
If liquidity providers can't withdraw, they can't withdraw their liquidity. That's why.
Yeah, it makes sense. Yeah, the open interest divided by the total assets minus, of course, what we're about to withdraw. Yep.
And this is like to get the total assets function. It's implemented from the ERC 466. It's just overriding.
Yeah, and I like how in contrast to the first two code bases we looked at, this one has the liquidity vault as its own separate contract, and so that removes some of the complexity associated with having the collateral stored in the same contract as the contract that LPs are basically depositing into. And so the total assets is actually really simple. It's just the balance of whatever's in this contract. And so I think that's a great way to handle this. The only thing that you'll have to be sure to account for is when you do add in the P&L logic, we just want to be sure that that total assets function accounts for the P&L that's pending in the trader.sol contract as well.
Yes, sure.
But yeah, I think that's great. And then in the liquidity vault.sol, is that inheriting from ERC 4626?
Yes.
Okay, great.
And also, actually, I need total open interest and maximum utilization percentage in this contract. So instead of importing whole trader contract, so we are using the interface.
Yeah. I would say the only thing you might have to look into is the ERC 4626 contract has some public functions that people can call on it to deposit and withdraw. And like they have I think they have deposit, withdraw, but they also have mint and redeem. And so these functions will still be,
Yes.
yes, people will still be able to call those and get around some of the logic that you've specified here. So I think you might have to override those and, you know, sort of disable them.
Yeah, I saw those functions like I can remove this one and just use the deposit instead of transfer form, and preview deposit will remain the same. I mean, but I can change that one, transfer form.
Yeah, and I mean, I think these two functions here are fine. I think they're great to have just the minimum logic, exactly what we need with that extra require statement for the withdraw. I think we just need to make sure that those other functions, so currently I'll be able to call mint and redeem on this contract, but we don't want people to be able to call those because they're coming from the abstract ERC4626 function or contract. So I just want to like override and disable those so that nobody can call those.
Understood.
But yeah, I think this looks great. And then, so I think we've pretty much covered everything except for maybe the price feed contract. Could we just have a quick look at that one?
Yeah. Yeah, it's like we are only the Bitcoin price as of now.
Yeah.
Like many, like as in other people have integrated conversion rate and stuff, but like I have used it differently, like not using as a library directly implement functions here, but directly like as you mentioned this decimal part, I'm returning directly from the contract logic here.
Yeah. Yeah, and I think having this price feed as a contract instead of the library, I think that's fine as well, especially if, you know, we do want to add like a mapping for multipliers for prices or anything like that, or if you do want to add support for multiple tokens, then you can have a mapping that holds the price feed address for each token address. So yeah, I think having it as a contract, that seems perfectly acceptable as well.
Yeah, sure.
All right, awesome. So any other areas that you want to touch on?
No, not right now.
Yeah, I think we pretty much covered everything. So awesome, looks great. I think you guys have a really nice design where, you know, we've separated the liquidity vault and the trader contract. I think that will end up probably being cleaner as we continue to add stuff, but we'll have to see. I think definitely if we're going for like the minimum number of code lines, putting them in the same contract, that that would give you the minimum number of code lines. But I think in terms of complexity and avoiding bugs, I think you guys will really appreciate having those separated. So great job, and thank you for taking the time to go and walk through that.
Thank you.
All right, fantastic, guys. So great initial code walks. I think those were honestly, you know, better than I could have asked for getting like the first code walk. So thank you guys for trying that out. What do you guys think about code walks? What's the general consensus?
I think it's really nice. One thing that it certainly does is that you have to explicitly explain your thought processes. And I think one of the things that you easily fall into when you're writing a code base is that you get very blindsided by your own code. Like you have a lot of assumption, you write them down, and you have a way of thinking, of course, like every developer. And now when you have to walk through the code and you get questions, then you have to reflect upon it on a higher level. So I think it's good.
Yeah, 100%. I totally agree. Like, there's a reason like developers can't audit their own code. It's just kind of like a mental block. You know, you have the assumptions, like you said. So and yeah, hopefully it was useful or interesting to be able to look at other people's implementations. Maybe you guys see stuff that you want to steal and implement for yourselves, or things you want to fix based on what you've seen other folks do. So hope that was useful. And then of course, if you guys have any questions on mission 2 or anything like that you guys want to cover, we can go over that. Otherwise, that's pretty much everything for today.
Yeah, I really enjoyed the code walks. One of the things that I'm gonna take with me from Paul's code base was that I saw that you guys added protocol invariant in a modifier. I thought that was really interesting, so I'm gonna experiment a bit with that. And the other code base that we just saw now, it was really clean to just divide them up and to just have the liquidity vault, and then you have the perpetual protocol, and we have the Oracle as well. So that was really good to keep it clean and smaller.
Yeah, definitely agree. Yeah, fantastic all around. Every single code base is, I think it's really interesting how there's none of them are exactly the same. All of them have slightly different approaches, and they're all great in their own right. So fantastic job, guys. All right, fantastic. So we just finished the audit training, and I think you've officially made it more than halfway. We're about probably 2/3 of the way through part 1 at this point. So first of all, congratulations and big respect for making it this far. By now you should have mission number 1 completed, and hopefully you've got a really strong grasp on this idea of perpetuals. And now we're going to be moving into a mission number 2 for perpetual. So definitely you should have mission number 1 completed at this point before you move on to perps part 2. So now we're going to dive deeper. We're going to see exactly how the decrease logic works, how liquidation logic works, and we're going to add in some more complex stuff like borrowing fees, opening fees, liquidation fees, and things like this. So now our protocol starts to get a little bit more complex, and you're going to start to see how easy it is to write new bugs and stuff as we start adding new features in. So I hope that you enjoy Perps Part 2. We're going to deep dive on perpetuals yet again, so enjoy the lecture. All right, you guys might have seen when perps is up here. Of course, the motivation of mission 2 is that we've got a baseline groundwork set for what our perps protocol is, and now we want to add to it. We want to get it over the line. The community is asking when. They want number to go up, and they want your perpetuals protocol to be launched. So with mission 2, we are just basically adding the missing baseline functionality to the protocol and getting it ready for launch. So of course this one will be next Monday, same time before our next session on Monday. So you have all week to do this. And the goals for this one, of course, these are the only functions that you should really have at this point is a way to get the real-time price of the asset being traded. You might also have a way to get the real-time price of whatever collateral token you're using. Traders can open a perpetual position for Bitcoin. They have a specific size and collateral. Traders can increase the size of a perpetual position. Traders can increase the collateral of their position. They cannot utilize more than the configured percentage of the deposited liquidity. And then liquidity providers can't remove liquidity that is reserved. That's only thing that was basically outlined for week 1. So nothing like liquidations, not even the ability to decrease the size of your position, no types of fees or anything like that just yet. So now with mission 2, what we're going to be adding is the ability for traders to decrease the size of their position. And when they do that, they'll realize a proportional amount of their P&L. Traders can decrease the collateral of their position. Individuals can be now liquidated with a liquidate function that anybody can call. There will be a liquidator fee that's taken from the position's remaining collateral upon liquidation with the liquidate function, and it's going to be given to the person who calls the liquidate function. So this will incentivize people to call that function and liquidate positions that should be liquidated. and it is up to you whether the liquidator fee is a percentage of the position's remaining collateral after they pay out their losses and fees and stuff like this, or if it's, a percentage of the position's size. So you should just have a reasoning for what you decide to do in terms of that and have that documented in the README. Traders can never modify their position such that it would make the position liquidatable. This can lead to an Euler finance type scenario where a trader is able to basically remove all of the collateral from their position and then consequently liquidate themselves and also receive a liquidation fee, which is somewhat similar to what happened to Euler finance. We can go into more detail on that at a later date if you guys would like, but traders should not be able to make their position liquidatable. Traders are now charged a borrowing fee, which accrues as a function of their position size and the length of time that the position is open. The borrowing fee will go to the LPers, and this is basically their incentive for providing liquidity on top of getting paid out when traders lose money. And then traders are charged a position fee from their collateral whenever they change the size of their position. This is the position fee is a percentage of the position size delta. And what I'll do is we'll say this one is optional / bonus. Since, it seems like last week was a bit more than we were aiming for. So I think, making this one just if you guys have time or you want to implement this one, then you can go ahead and implement the position fee. So one thing that you might have already noticed is there's a lot of different edge cases and gotchas, and as you add these things, there's going to be exponentially more. So these would be things that you just want to start to try to think about the different edge cases and how each of these affects all the other features of the protocol. And then we've got some, basically a full rundown of, okay, what does it look like when we're decreasing a position? Some examples: decreasing a position when somebody's in profit, decreasing a position when somebody's in loss. You can see exactly what happens there. Decreasing collateral should be fairly straightforward. Let me talk a little bit more about, what makes a position liquidatable, when should liquidation occur, what occurs during liquidation, how exactly that process looks, how do liquidations happen, things like this. And then we have a bit on the fees. So these are the position fees. This is optional / bonus. Everything described here with some examples for position fees. And then we've got borrowing fees here, which are, they have a few considerations in terms of, especially decimals and things like this. And then, of course, liquidation fees. This is really just the liquidator fee. And of course, that should be documented in the README. So all of this should be sufficient to go over and understand exactly what we're adding here. But on a high level, do you have any questions based on things that are being added in Mission 2?
Anything about adding orders, or or is it? Is that part of the features as well?
Yeah, absolutely. So this is sort of like a up to your discretion. So in for example, the GMX system, they have orders, right? So I can create an order and then it will get executed by a keeper. Now we don't actually need to do this for our basic system. If you did do it, that's completely fine. That is, a great thing to have in terms of, avoiding MEV and things like this. The reason GMX needs it is because they have this idea of price impact. And this is basically saying that, if trader A opens 100K long, they're going to get impacted X dollars on their execution price. And it's dependent on what the current balance of the market is. So now all of a sudden, if I front run that person and I change the balance in the market, I can make them get impacted worse, and I can even sample attack them, and I can get positively impacted afterwards and sort of extract value from their trade. So this is why GMX has the sort of like two-step order execution layer that they do. It's not entirely necessary for our system, but it's, you know, a good thing to have nonetheless. So you could definitely have an implementation where traders, there is no creation of orders. There's just a, you know, increase position function, and then, you know, that takes like the size delta, the collateral delta, you know, is long, things like this. And traders could immediately open their position with this function, or, you know, increase the size of their position with this function. And then there is no real idea of orders. It's just transactions to call this increase position function, and their position gets immediately increased. So that's like the most simple bare bones approach. But then, you know, of course, yeah, you can have this design of people create orders, and then orders do that, and they get executed by a keeper or something like this. So, I mean, I think both make sense. The order mechanism is definitely, it takes, you know, more of a cautious approach, and it's definitely better if you're building a more complex protocol. So yeah, with the order paradigm, you would similarly, oops, what is this? I'm guessing you would have an increase order right now. Basically, all this is doing is you're adding a decrease order, which will mirror whatever increase order does. And then there will still be, you know, I think even if you have orders, if you don't have orders, you're still going to have a liquidate function no matter what, which should just be callable by any address that could liquidate somebody in a single transaction. So yeah, there are any questions based on, you know, orders and stuff like that? Or I guess does that answer your question they had based on orders? Yeah, so really just adapting these new things to whatever your design has been thus far. Okay, cool. And then of course, you know, we can go more in depth on, you know, borrowing fees or any particular area in office hours, and that can be recorded and shared with everybody if need be. So any final questions on mission 2 or anything like that?
Yeah, one quick question, please. So if we decrease an order, in fact, it's like we are closing part of the order. So we are realizing a loss or a profit, right?
Yeah, exactly. Yeah. So when we're decreasing, so a position might be in profit or loss, like you said. So for example, if I decrease my position by 50% of its size, I should realize 50% of whatever the outstanding, you know, pending profit or loss is. So if I was in $10 of profit, I decrease my position by 50% of the size, I should immediately in that transaction get paid out 5 USDC, or half of my P&L, and then the remaining 5, you know, profit should remain as pending profit for my position.
Okay, clear. And the profit is added to the collateral, is it right?
Yeah, so losses are deducted from the collateral. Profit, when you realize profit, it should get paid out directly to the trader. So there should be a transfer when there is profit. It should get transferred to the address of the trader. But when there's loss, it should just be deducted from the collateral of the trader's position. Does that make sense?
Yes, thank you.
And why is it that way? Does it have to do with how much leverage the trader has?
Yeah, so I'm assuming you're asking why is it, are you asking why is it so like 50% that gets realized?
Yeah, so I guess one of the things we thought about was to add the profits to the collateral and then also deduct the losses from the collateral. Is there a problem of doing it? Like having both interact with the collateral variable, and then, you know, if they want to withdraw, they will just withdraw the collateral, which is everything.
Yeah, they definitely, you could do that. It's a design decision. I think we're just going to specify for our design that traders, when they're in profit, they get paid out that profit instead of it first going to their collateral and then them having to, either make a second separate transaction to claim that collateral, or maybe in the same transaction doing some jujitsu to decrease the collateral, calculating a certain amount that you would want to decrease it, knowing that the profit would be added to the collateral or something like this. So yeah, you definitely could do it both ways, but in terms of our protocols, we're just going to enforce the design decision to pay out the trader. Yeah.
All right, got it.
I like the jujitsu part.
Yeah. Hopefully, we try to avoid jujitsu as much as possible in Solidity, because normally that's where interesting bugs are. If you ever see jujitsu happening in the code, pay very close attention.
I guess that's the quote of the day.
Yeah, that's a great one. So we covered a bit on decreasing position. We can do more on that if you guys have any particular questions there.
Can you?
Yeah.
Can you please, with decreasing? Let me see. Yes. Can you please go over that? Is it okay to? Yes. Can you go over that a little bit? I'm sorry, please.
Yeah, absolutely. Let's do just a full overview here. So, okay, cool. So we have a few examples here that we can walk through, but let's just walk through what we've got here. So similarly to increasing the size of a position, when we're like opening our position, traders have the ability to decrease the size of their position, right? So this is how, a few things happen. So here are the important things that happen when I decrease size. Let's just make this a little bit. So first of all, we'll just straight up, decrease the size of my position. So what does that mean? When we have a position, we have some notion storing, how many tokens are in this position, right? Virtual tokens. And then what's my cost basis? What's the cost basis? Right, so if I have a position, so for example, I could have a position that has, let's say, two Bitcoin, as this is my size. Well, that's great, but to calculate P&L, I need to understand what's my average price for those 2 Bitcoin, right? Because I could have bought those 2 Bitcoin at a cost of $50,000 each, right? And then Bitcoin is at, I don't even know what it's at. Let's say it's at 20,000. Hopefully things get better. Then my cost basis, so if this is a long, for example, we're going to be able to use this to say, okay, well, I'm negative 30,000 per Bitcoin on here. So this is a crucial piece of information, is this is the price that I entered at, and this is the current market price. So we have the ability to track the current market price through the Oracle, the price feed, however you're handling that. But with this current, this 50,000 here, this is tracking, okay, what's our entry price, right? And you could track this a number of ways. You could track it by just having a position size in USD. It could be, just average price. You could store that. And we saw a few different implementations of this today. But basically, there's just some way to be able to get this information of what did I buy these 2 Bitcoin at virtually, right? So this is important for decreasing, because what we're going to do when we decrease is we're going to allow somebody to decrease this number, the size of tokens that are in their position, and we're going to have them realize a corresponding share of the negative or positive P&L that they have outstanding. So what does that mean? That means that, for example, if I have a position with 2 Bitcoin in size, and then let's say I want to decrease by 1 Bitcoin, so I want to basically cut my position size in half. Well, let's say, first of all, let's say I was in a loss, right? So let's say my cost basis, let's use this example from up here. My cost basis is $50,000 per Bitcoin. So I've opened this position way back in 2021 when Bitcoin was $50,000. And now BTC is $20,000. So then, of course, from this information, we know that we're able to calculate P&L. And, you know, we've already got logic for this. This is basically, so we're going to specify that this is a long. Longs are, I find them the easier case to think about. So our P&L is going to be, of course, what the current value is of our position. So we're going to do $20,000 times 2 Bitcoin minus what we paid to get into the position. So $50,000 times 2 Bitcoin. And this is going to give us a net P&L of negative $60,000. So we're $60,000 in loss. Now, when we decrease our position, the main goal of decreasing the position is to make this number go down, our size go down. So we're going to take our size from 2 Bitcoin to 1 Bitcoin. But I can't just let somebody do that, decrease their size like that without, you know, them doing something about this huge loss over here, right? So if I just let you decrease your size without adjusting anything else or accounting for P&L at all, well, then you can just change your P&L magically without having to, you know, pay the consequences. So if I just let you decrease your size like that, you could make the equation look like this. And then magically, now you're only $30,000 in a loss. Where did that P&L go, right? It just vanished and I didn't have to pay for anything. And, you know, I'm basically just cheating the system. So when we allow somebody to go from 2 Bitcoin to 1 Bitcoin, we have to account for the fact that, hey, your P&L in this P&L calculation is going to go down as a result of your size in tokens here going down. So what has to happen in this transition here is the trader has to pay for this $30,000 decrease that's going to happen in their P&L when I decrease by 50%. So what this basically ends up, you know, looking like is upon decrease, traders pay a fraction, a ratio of their P&L. So P&L times the size delta, so how much I'm decreasing by, divided by the position size. And so for our explicit scenario, what this looks like is our P&L is negative 60,000 times the size delta, which is 1 Bitcoin, divided by the position size, which is 2 Bitcoin, equals 50% of negative 60,000. So we go to negative 30,000. This is the P&L that traders have to pay, right? Or traders have to, quote unquote, realize. We have to actually bring this into real world assets. And so what they've got to do is they've got to be able to pay, they've got to come up with $30,000 of value here. So we're going to take this from their collateral. So when traders lose money, we subtract this from their collateral. So that means, you know, let's say this trader has, you know, for the sake of the example, we'll say they had $100,000 of USDC as collateral. That's what they had originally. Well, when we decrease the size of our position, we're going to take this $30,000 loss and we're going to apply it to the collateral. So then the trader goes to $70,000 USDC of collateral, and the 30,000 of loss is transferred to the LPs. So for your guys' implementation, what that looks like is you're going to take this 30,000 USDC and you're going to transfer it to the liquidity vault contract, and that will automatically be shared by the LPs. So does this start to make sense? Or do you have questions following up on this?
Yes, 100%. That does. Quick question. For instance, since they started this trade back in 2021, what if their collateral? So that's the reason why probably we would have to have a collateral function to be able to increase the collateral, right? If, say, for instance, they didn't have enough collateral, would that even be a scenario?
Yeah, exactly. No, that's a great question, and it leads to the next big feature for. Of course, we have a corresponding way to decrease collateral if they want to pull collateral out, but admittedly, this functionality is not too complicated nor important. Liquidation. So just like you said, what if, there's the question, what if they don't have enough collateral, right? So what if they owe everybody $30,000, but they don't have it, right? So that's a state that we desperately want to avoid. We want to avoid positions ever getting into that state, because when that happens, like, there's nothing we can do, right? If they don't have enough collateral in their position, well, there's no real incentive for them to add more collateral. They'd have to, make a transaction on their own to do that. That's not very trustless. So at that point, the protocol is basically out of luck. So our goal is to, quote unquote, liquidate them before it can ever get to that scenario. So what does that look like? We might see a position getting to the point where it's like, it's pretty close, like they're in a lot of losses. So a position might start out with a size of $10,000. So that's the total amount of size that was like put into this position. And then, well, actually, let's copy the same example we've been going with. So the size of this position initially was $100,000, right? We bought two Bitcoin at $50,000 each. So that was our original size, $100,000. Now, I said that collateral was 100,000 of USDC. So when they initially opened this position, their leverage was 1x, right? $100,000 divided by $100,000. Now, what's happened is they've lost, their net loss is $60,000 on their whole position. So we can take their whole P&L. Now, fast forward 2 years later to today, the P&L is negative $60,000. So we know that that's going to have to be removed from the collateral. So let's adjust our leverage formula to collateral minus P&L, since we know that that's going to have to, well, technically it's plus P&L, and then a negative P&L will get added to the collateral. So what this looks like is we still have that $100,000. That's just our cost basis. That's the size that we initially opened the position with. That doesn't change. Our collateral, there's still 100,000 USDC sitting there. We haven't, decreased the position or anything like this just yet. Minus this $60,000 of pending P&L. So this is 100,000 divided by 40,000, which is, I think, 2.5x leverage. So our leverage has gone up. So for the amount of collateral that we have here, we're, quote unquote, trading with $100,000 of value. So depending on the system, we might say that's acceptable. You still have $40,000 of USDC to support, if you continue to lose even more money, there's still that barrier of, hey, we still have this amount of money from you to cover any more losses. Now, what if the losses continue? What if this person goes down to, minus $99,000, right? And you end up with 100,000 divided by 1,000. Well, that's 100x leverage. That's pretty risky, right? If they lose just a little bit more, then there's literally just not going to be enough collateral to pay for their losses. So what we'll say is, hey, I want to define a max leverage, which is, we could say like, hey, 20x. As soon as your position gets to 20x, we are going to liquidate you. And that's basically us saying, we're going to close your trade for you at the losses that you're at right now, because I know that at this point in time, you can still cover your losses. There's still some collateral left to be able to cover that. But we don't want to allow you to go any further, because if you go further, it increases the chance that you're not going to be able to cover that. So what that might look like is if this person gets to 5,000, for example, as soon as this person gets to $95,000 in losses, that's the point at which they're in 20x. And that's the point where they get liquidated. And that just looks like a force decrease, right? So we just decrease your position for you. And, it's exactly like the math that we did here. You could probably have an internal function that is just used between the liquidate and the decrease position function. There's just a little bit slightly different logic, but most of it can be reused. So really it's just allowing a position to be force decreased. And we're just, saying, hey, like cut your losses and here's any remaining collateral back that you had that's left over. We're going to take all of the collateral that you had, that were reserved for losses for your position, and we're going to give those to the LPs. So yeah, does that make sense?
Yes, thank you.
Okay, cool. So that's liquidation, and that's pretty much everything that we talked about here. Now fees. So position fees, we're gonna ignore these for now. Those are kind of optional or bonus for this mission. We don't have to worry about those too much. And they're actually not too complicated. But the borrowing fees are probably the most interesting thing to touch on here. So borrowing fees are a way to basically, another way to generate yield for the LPs. Because the LPs are basically lending out the money that they're providing as, quote unquote liquidity for people to be opening these perpetual positions. And so anytime when I open a position, so let's say I open that $100,000 USD size position, then I'm reserving X amount of like LP deposits. And this is based on the validation that you guys added, right? The utilization percent. We know that when I open this position, that means that there's some amount of LP deposits that now are not able to be withdrawn. Like they literally can't withdraw them because of the require statements or the validation that you guys added. And that's kind of the notion of this amount of money of the LP's money being reserved. So we're going to charge an interest rate on having that open, because otherwise what people would be able to do is they would just open a ton of positions and open a ton of open interest, open a ton of size, and they just reserve all the LP's money. And then they're just going to be stuck, right? And then of course they're exposed to the market risk of, whether or not the index token goes up or down. But they could also just hedge, and they could open a long and they could open a short. And so that way they could be delta neutral. If the market price goes up, they make money on their long, they lose money on their short. If the market price goes down, they lose money on their long and they make money on their short. So we don't want to allow people to just risk-free take up open interest size, reserve all this liquidity for no risk and no charge. We want to charge them a borrowing fee. So this is kind of like the interest that you pay for renting this liquidity from the liquidity providers. So a borrowing fee is something that depends on the amount of time that a position has been open, right? So if I have a position open for a week, I'm going to pay borrowing fees for that time period of a week. If I have a position open for a year, well, I've been quote unquote borrowing those funds for that entire year, so I'm going to pay borrowing fees for the course of the year. And of course, if I'm reserving a huge amount of LP deposits, I have a position with $1 million of size, I'm going to pay a lot more borrowing fees than somebody who opened a position with maybe like $50 of size. So borrowing fees are a function, they're a function of time and position size, and of course borrowing rate. So I've got a really simple formula here just to calculate the borrowing fees. So it could be literally as simple as borrowing fees equals the position size. So the size of the position times the seconds since position updated. So the period since you last paid your borrowing fees, multiplied by the borrowing per share per second. So if we look at the units for this thing, we have a size times a time, or we'll say seconds, size times seconds, times this thing that is, we'll do this, we'll make it a bit simpler. So size times seconds divided by this thing that is per share per second. So times per share per second. So divided by a size times a second, right? Or we could think of it like this. So the borrowing per share per second is a 1 divided by size times seconds thing. And so what we're ending up here is, you know, this thing cancels with this thing, and we'll just end up with a dollar value at the end of it. So what we'll do is we'll multiply this by $1 when we actually translate this into code, depending on whatever your dollar representation is. So let's break this example into, you know, an actual usable formula. So we want to have a borrowing rate that actually gives us something that makes sense, right? So we'll define a rate of borrowing as, you know, something that's reasonable as 10% of your position per year. So if I open a position for a year, then I'm going to owe 10% of that position size as borrowing fees. So how do we do that? So we've got the borrowing rate as basically our knob to turn up the borrowing fees or turn them down, and we can configure them how we want. So let's say I want to find the borrowing rate where it equals 10% of your position per year. Let's find that borrowing rate, and then we'll use that. So we can do some simple algebra and basically calculate that if I want the position size divided by 10, that's what I want the borrowing fees to be, right? We can just make this, use this formula. So if borrowing fees equals the position size times the seconds position has existed times the borrowing rate, which is a borrowing per size per second rate, we're going to use this function. And I want the borrowing fees, I want them to equal my position size divided by 10. That's what I want. And we want to solve for borrowing rate per size per second. And we want this to be over the course of a year. So we know in a normal year without a leap year, which we're going to just conveniently ignore, we have this many seconds. So then we can basically take this to, what we'll do is we will divide each side here by position size. So we'll get 1/10 here. And then we will divide each side by the number of seconds in a year, the number of seconds in a year with an extra 0. This is what we'll get for our borrowing per size per second. This borrowing per size per second gives us 10% of your position per year is what you expend. So, of course, there's some more decimal trickiness with solidity, right? We don't know how the hell to represent this in solidity without it just rounding down to 0, right? So instead, you might come up with, some sort of decimal solution to do this. And this will probably be centered around what your USD implementation is. So how do you represent USD in terms of decimals? Earlier, we were talking about what if I choose to have 18 decimals for USD, or 30 decimals for dollars? Well, if I have 0 decimals for dollars, we're going to have a bit of trouble calculating the borrowing fees. So we definitely want to have some decimals to work with here. So we can actually convert this into a usable thing if we divide by however many decimals our dollars implementation has. And so in my example, we say $1, a USD amount has 30 decimals of precision. Yours might have 18, it might have whatever. If it has 30, this is what this would look like. You do borrowing fees equals, of course, the position size. And note that the position size, at least how we're thinking about it here, this is a USD variable. This is a USD amount. So this is in 30 decimals of precision right here, times the seconds position has existed, times that rate. So what we've done here is we have multiplied 1E30 by this borrowing per size per second. And this is how we're achieving this 1 over this thing effect. So what this looks like is 1E30 divided by, or I suppose you could say times, the borrowing per size per second. And then what we're doing is we're just dividing all of this by 1E30 afterwards. So we're doing all of our multiplication first, and then notice the units. This is 1E30. This is just a seconds. This thing is also 1E30. We're basically multiplying by $1, a USD here. So we divide by 1E30 afterwards. So the units we end up with after all of this is a USD unit, because we had USD, that's position size, times seconds, times 1 USD as sort of like a unit vector. And then we had this 1 divided by USD times seconds here. So this, let's see, can I cross stuff off? Here's what we'll do. This cancels with this. This cancels with this. And we're just left with the USD amount. That's the resulting borrowing fees. These are in USD terms. And so the entire reason we had to, multiply by 1e30 here and then divide afterwards is because there's no way to easily represent this in Solidity without rounding down. So what we did is we put this thing into basically 1e30 terms. So if I grab this, actually I want to grab this with the extra 0. If we do 1e30 times this thing, or I'm sorry, 1e30 divided by this thing, we get something that's 1e21. Now we've just found a way to apply this factor to anything in Solidity. We can multiply something by this 3.17 whatever e21 value, and then we can divide this by 1e30 afterwards. So for example, if I want to say I have a position of $10,000 of size, so this is a dollar amount, so this is times 1e30, and let's say this was open over a period of 60 seconds, a single minute, some high frequency trading. So it was open for a single minute. I'm going to multiply that by this. This is our representation of this borrowing rate per second. I'm going to divide this whole thing by 1e30 because I multiplied here by 1e30 to be able to start to use this. Then we're dividing by 1e30 to get it back to this 1.9, this is a fraction of a cent or something, is what you would pay over 1 minute for borrowing fees. Now, of course, if I wanted to do this for a whole year, so let's grab the seconds in a year. Let's grab this really quickly. The amount of seconds in a year, we get 1,000. We get 1e33, that's 1,000. That's exactly 10% of our position here. And again, that's exactly what we defined this rate to be, is over the course of a year, we want it to be 10% of our position. So I know the math on this gets a little bit involved with some algebra and then some decimals nonsense, but hopefully this, if you rewatch it back when you actually go to implement this, hopefully these sort of decimal logics start to make sense. But any follow-up questions based on that?
Well, thank you for that. Thank you.
Okay, cool. Yeah, so that is everything on the borrowing fees. All right, so we have just introduced mission number 2, and now we've gone into some more advanced concepts surrounding perpetuals. I hope that's starting to make sense. If not, I think working through mission 2 and hopefully being able to talk to your partner or other folks who are taking the course will be super, super helpful. So do not hesitate at this point to reach out in the Discord channel and the Gateway course Discord directory and talk to other folks who are also working on this. Try to bounce ideas off of them. And then, of course, if you're not already paired up, I would definitely recommend that you go ahead and attempt to pair up with somebody and work on mission number 2 with. And then, of course, now we are moving on to EVM mastery. So now we're going to go into an EVM intro and a memory guide. And by this point, after the EVM intro and the memory guide, I would recommend going to side quest number 1 and completing side quest number 1. That's everything about memory. We're actually going to go and we have a number of questions related to the Solidity Safe Transfer Lib library. We're going to break that down. We're going to understand how it works. And then in the Yul Masterclass, you're going to get the answers to side quest number 1. So make sure you have that completed before you watch the Yul Masterclass. And then we're going to go and finish things off with a Calldata Masterclass. And then you have officially completed part 1. So you'll be halfway through this course. I think hopefully looking back, if you look back from where you are now, from when you started, hopefully you have a ton of new knowledge around DeFi and Web3 security. And I think going into part 2, that's just going to continue to deepen and deepen. So without further ado, enjoy the EVM intro. All right, great. So in this guide, we're going to cover all the different types of areas where data can be stored in the EVM. And then once we get an idea of the high level layout of all of these different areas in the EVM, then we're going to dive in and see how these areas can actually be utilized during a transaction execution and how the EVM actually works with each of them. All right, so let's get started. First of all, there are actually 6 different places where data can be stored. And this is, of course, most commonly the stack, memory, call data, and storage. But also, you can store things in code, obviously, that is at any particular address. And then also logs, which is a write-only way to emit events and log stuff. So in this guide, we're really going to drill down and focus on the first 4 here. We're going to get a very solid understanding of the stack, memory, call data, and storage. Okay, so first of all, let's dive into the stack. Now, I'm sure many of you watching this video are already well aware of what a stack is and exactly how it functions, but for those of you who don't, a stack is a very simple data structure where you can just take items. Let's say I have this item here, and I can push it onto the stack. Let's say this is my stack. It's just a little cup here. So then we put that item into the stack. There it goes. It's in the stack now. So this item's now in the stack. And then what we can do is we push another item. So we take another item and we push that item now onto the stack. And so now this item comes here, we grab it, and now this item goes onto the stack. And then what we can do is we can pop from the stack. And when you pop, it comes from the top. So the thing that I just put on when we pop from the stack comes off, right? And that's what we get. And then I can pop again and I can grab this thing and pop that off afterwards. So what are these things that we're pushing in and popping off in the stack for the stack in the EVM? So in the stack for the EVM, we store 32-byte words and we push them on and pop them off. So when I store something on the stack, it will be a hex 32-byte thing, right? So if I wanted to store the number 1, then I would have a bunch of zeros here. And then literally the very last hex character here would be 1. And then all of these, this would be 32 bytes. And remember, each of these 2 pairs of characters here makes up a single byte, right? So if we break this off, then we have 4 different spots. We have 0, 0, 0, 0, and this gives us the first character of 0 in our hex, and then we have 0, 0, 0, 1, and this gives us the second character in our hex of 1. And so that's our byte, and in this first word, the entire value for this first word is 1. So if I want to push 1 onto the stack, I take this 32-byte word and I push it onto the stack. And then you can push other words on top of that and pop those off. And of course, there are also functions to swap these around. So oftentimes you'll have different, so let's say you have multiple words. Let's say this is all on the stack. Here's a word, here's a word, here's a word. You have OX and then a bunch of zeros, right? So you have all these words. Now, often what will happen is the first 1 or 2 items, the top 2 items on the stack, will be used for interacting with a lot of opcodes, and we'll dig into exactly what opcodes are in just a minute. And of course, the types of things that are stored onto the stack and pushed on and popped off and used to interact with opcodes like this are uints, bools, addresses, or even pointers to areas in memory and areas in storage, which we'll get into right now. Now, memory is somewhat similar to the stack in that it also functions based off of 32-byte words, but it doesn't use any sort of pushing on and popping off. Instead, you can write to specific memory words and choose exactly the bits that you want to write to. And so memory is used to store, of course, structs, and it's even used internally by Solidity behind the scenes. So because memory is used in this special way, it actually has a very particular layout. So when we're talking about memory words, then we have, of course, OX00, which is the first position for a word in memory. And then, of course, you have all of the 32 bytes from there until you end up with OX20. And you'll remember that if we go to a Python shell here and we go and type in OX, we could just put 20 here and 16, then we'll get 32, right? So this is the hex value, OX20 converted to a decimal. So this is at a 32 byte offset from OX00 is the next memory spot. And both of these memory spots here, 00 and OX20, all the way up to OX40, everything here, all of the zeros stored here. So you have a bunch of zeros here, and that goes on, and you have 32 bytes here. There's 32 there. And then, of course, you have the same thing here. Both of these words from OX00 and OX20 are reserved for Solidity to have some scratch space to work around with when doing things like hashing functions and things like this. And then at OX40, this word is the first word that's not reserved as scratch space, but it is actually very special in that it is home to the free memory pointer. And this word will initially be OX80. So what is the free memory pointer and why does it point to OX80? Well, the free memory pointer points to the first spot in memory, the first word that doesn't already have something written to it or isn't reserved for some other reason. And so this is so that if we ever want to write something to memory, you can read the free memory pointer and then immediately know where it is safe to write something new to memory without overwriting something old. And so the follow-up question is, of course, why does it point to OX80 when, of course, the very next word is OX60? So OX60 is also going to be completely empty with just a bunch of zeros. But this word is actually intended to be empty always. This is used for the initial value for dynamic arrays as just a zero value. So of course, this word in memory should never be written to, and that's why the free memory pointer skips over it and points to OX80. And so at OX80, it's going to be initially completely clean. Nothing will be stored here, and it is actually safe to write new stuff to be stored in memory here. And it's actually interesting to note that OX40 is the free memory pointer, and it comes before OX60, because when initializing this memory to OX40, that means we only have to load in so many words before it and sort of allocate those as memory. And so this way, if a transaction never wrote memory beyond this OX40, then we actually wouldn't have to sort of load in another memory word here. And so this is a very slight optimization where if they were to be flipped, then you would always have to be loading in another empty spot when we initially write to the free memory pointer in a new transaction, which we'll see in a minute. And to make what I'm saying here really clear, if I go and I write to memory and I do what is called an mstore opcode, which we'll see in a second, and I say I want to write to some slot that is, like some really, really big number, I want to write to some really huge number down here, this is going to be extremely expensive due to memory expansion, right? So if I'm writing to this, then we now all of a sudden have to keep track of all of these memory words below it. And so as your memory expands like this, the gas costs are actually going to exponentially increase. All right, and the next is, of course, call data. So call data also stores arbitrary bytes But the difference here is that in Calldata, you can only read from this area. You cannot write anything to Calldata. And for this reason, it is much, much cheaper to be reading things and accessing things from Calldata. And so, of course, if you can help it, then always err on the side of simply reading things from Calldata and avoid copying things from Calldata into memory whenever possible. So if you never need to modify something that is Calldata, then always just read it from Calldata and do not copy it into memory. And of course, if you have a memory parameter for one of your functions, but you never need to modify that memory parameter, then use it as Calldata. Okay, and then finally we have storage. Now, storage is the most expensive of all of these different areas where you can store data, but it is also the only one of these areas that is permanent. All of these other areas like the stack, memory, and Calldata, they all go away. They're all temporary places to store data during a transaction. So in this sense, storage is almost like the blockchain database that you can think about. And it works in somewhat of a similar way to memory, where we have 32-byte words that get stored in storage. Except this time we have storage slots, and there are no reserved areas for solidity or no like free memory pointer or anything like this. And so essentially, if we think about the blockchain state and how we have, all these different accounts, like let's say we have account here, an account here, an account here, an account here, then for example, if we go to this account here, then this account has a nonce associated with it. It has a certain amount of ether, so it has native tokens. And then of course it might have some code associated with that address. Of course, if this is home to a contract, and then if it's home to a contract, then it is also likely to have some storage. And now storage also breaks down into these slots. So we have all these different keys for storage, and each of these keys is essentially a uint 256, a 256-bit number, or something that occupies a full word, whereas the keys for the state of the blockchain in each of these accounts is of course a 160-bit number or address, right? And then both of these, of course, the state of the blockchain with all of these different accounts, and then of course the tree here for different storage slots are Patricia Merkle tries. And we're not going to get into exactly this video, but this is essentially how the storage is ultimately laid out as a persistent piece of the blockchain state. So of course, how do all these different areas of the EVM actually come together to give us what we know as Ethereum? So what brings it all together and makes all of these things interact with each other and really workable is this idea of opcodes. So we're on the Ethereum yellow paper here, and we have all of the opcodes pulled up. And we can see that essentially what an opcode is a specific instruction to give to the EVM in order to do something. So imagine you had a little robot and you gave him 4 different spots to just put stuff. And then you just gave him stuff, you just handed him random crap and then told him instructions on what to do with it, where to put it. That's essentially what the EVM is. So we can see we have something like the add opcode, which literally just takes 2 items that are on the stack, like we talked about, and adds them together. And then of course stores the result of that addition into the first spot on the stack. And you can see along the side here that for each opcode we have a corresponding hex code here. And this will play into how exactly these opcodes are able to be translated into something that can be actually executed by the EVM. But first, before we get into that, let's examine a few opcodes that interact with the areas of storage and memory and the stack that we just looked at. So here we can see we have a number of push opcodes which correspond to pushing things onto the stack. So here we can see we have a push 1 opcode, and it goes to push 2, and it goes all the way up to push 32. And each of these correspond to pushing a n byte sized thing onto the stack. And remember, it goes up to 32 here because 32 bytes is of course a full word, and full 32 byte words are what is stored on the stack. And so if I only push 1, then the other 31 bytes are essentially padded out with zeros, and then you get that one single byte on the end. That thing is pushed onto the stack. Then of course here we have OX50, which is the pop opcode, which removes an item from the top of the stack. And right below that we can see imstore and imload. And so these opcodes are useful for storing things in memory, right? Imstore will take the actual position, and so imstore will save an entire word into memory, and it will take the first 2 things on the stack and use those as the value to be stored, and then also the position at which it should be stored. And then of course imload is doing the opposite. We are reading something from memory, right? So we're giving a location in memory to read, and then we are getting that value and putting it onto the stack. And then you'll notice we even have a imstore 8 opcode here, which saves a single byte to memory. And then right below that, we can see the sload and store opcodes, which do a very, very similar thing just for storage, right? So I can store and load things at a particular storage slot. So there are many, many opcodes, and I encourage you to go read the Ethereum yellow paper and actually see all of them for yourself, get familiar with all of them. But now it's time to see how these opcodes come into play and are actually used by the EVM. So we'll remember that if we go to our Ethereum yellow paper here, we can see these opcodes correspond to these hex values here, these single bytes. And we'll actually be able to see this if we go into Chisel. Here we have literally just a example contract set up here. And what we can do is we can get address this.code, and here we have individual byte codes for opcodes, right? So some of these hex characters here are opcodes. And so we can see if I add a variable here, we can add a uint I, and we can say it equals to the type uint256.max. Now if we go ahead and look at our contract, we've added this single declaration of I, which is the max value of the uint256. And then now we can have a look at address this.code. And you can actually see here that we've gotten a good amount of extra Fs here that we didn't have before, right? We had this 73 FFFFF here. This is this set of Fs, but we didn't have this big statement of Fs here. So if we actually count this out, the number of bytes here for this set of Fs is actually 32 bytes of Fs. And this is the value for our I variable here. This is the uint256 max, right? So uint256, of course, has 32 bytes, and each of the bits inside of all of those bytes are 1, and so we have F for every single byte. We have FF. And so before all of these 32 bytes of Fs, we can see we have this 7F byte right here. So if we go and find the opcode that corresponds to 7F, we'll see what exactly is happening with this big set of Fs here. So here we are at the 7F opcode, and this is the push 32 opcode. So we're pushing a 32 byte word onto the stack. And this perfectly makes sense, right? So we're taking this big 32 bytes of Fs and we are pushing it onto the stack. That's exactly what this statement here is doing. Now, there's actually a wonderful website for distilling things down and actually getting to look at the bare opcodes themselves, and that is EVM codes. So we can see we have a basic sort of default contract here for a counter already set up for us, and we can run the count method and we can see exactly all of the different opcodes that it's going to run through, and you can even step through all of them and see how the memory, the stack storage is manipulated throughout the transaction. But what we can do is we can actually walk through and see, okay, what is the EVM doing at the opcode level as we're reading this bytecode here and executing the call data, and then we can see how the transaction will function. So here we can see I've called the count function, and we can see a few things happening off the bat here. So I can see a push one opcode of 80, and then so we're placing 80 onto the stack. So that's our first 32-byte word on the stack, is literally just a bunch of 000s, and then in literally the very last byte, that byte corresponds to 80. So we have OX80 on the stack, and then we push another word, and this one is OX40. And then what we do with those two things on the stack is we store them. And so what we're doing here is exactly what we talked about just a little bit earlier when we were talking about this free memory pointer. So this is exactly what we're doing. We're taking OX80 and we are storing it at OX40. And so this is at the beginning of any transaction that happens, is we're going to start up by setting that free memory pointer. And then what we're going to do is we're essentially going to have a sequence of opcodes here to check if the call value was non-zero, because of course the function that we called is not payable. So we're going to get the call value that's going to place that onto the stack at the top. We're going to duplicate it. So now we have two of those. So this will check, is the last thing on the stack 0? If it is, put a 1 there. If it isn't, put a 0. And then we're going to push 2 for this. And so now what we're doing here is we're pushing 2 bytes onto the stack, and we've got this 0010 value. So basically OX10 here. That is the most recent word on the stack. And then remember, we have our is0 result after that. And of course, for this transaction, I did not provide any message.value. So this is0 will result in true, which means there will be a 1 there. And then we get to the jump I instruction. And if we go and find jump I in the Ethereum yellow paper, then we can see conditionally alter the program counter. So where the program is, and we'll look at that in just a second. So here the notation might be slightly confusing, but they set the program counter to what is on the 0th of the stack. So whatever is literally on the top of the stack, if that first value, our result of is0, is not equal to 0. So our is0 result was 1, and so it's not equal to 0. And so what we will do in our case is we will actually jump to this program counter of 10 here. And what this will do is it will essentially move us. You'll see, so the program counter here is right here on the side. So once we get to jump I, we're at OB. And then what we'll do is we'll end up jumping to 10 here. And so we can sort of step through that and see that now we're at the jump dest, right? We just jumped to this destination here. And you always have to jump to a jump destination, otherwise the whole program will revert. And then now that we're at the jump destination, we've loaded in, we've put the free memory pointer where it needs to be. We've had that safety check that makes sure that we didn't send Ether to a function that isn't supposed to accept it. Now what we do is we clean up the stack a little bit, and then we push on this 4 value. And then what we do is we get the call data size and put that on top of it. So what the stack looks like right now is we have 4 right here, and then we have the call data size right here. And then what we do is we have this less than opcode. And so the less than opcode will check, is this call data size less than 4? And that means 4 bytes, right? So if call data size is less than 4, then we're going to end up, so less than, I believe it will put a 1 onto the stack if it is indeed less than, which means that we will jump I to 004C if it is less than. And then if we jump to 4C, if we find 4C, then we see that this ultimately leads to another revert case. right? So if we provided some call data that was smaller in size than 4 bytes, meaning that it couldn't possibly even be a function selector, then we need to revert, as that's clearly invalid call data. You're not even attempting to call a specific function. And just really quickly on function selectors, they are essentially the first 4 bytes of the Kechek hash of the function sort of parameters and signature here, and we can actually easily get the function selector if we do a cast sig of, let's say, get, and we can see that this is the function selector for get using the handy Foundry cast. And then of course for the function that we called, which is count, we can cast that as well and get count, and then see, okay, here is the function selector for count. So when we supplied call data to call count, we immediately gave this function selector as the first 4 bytes as a part of that call data to specify this is the function that we are calling. So with that in mind, let's step through, let's see this validation of the call data size in action. So we push that on, we check if it's less than, we push stuff on, and we're going to see us not jump. So jump I, and then we're just going to go to 1A. So here we are on 1A, and then what we do is we load the call data, and then you can see we're about to do a shift right, and we're about to shift right by this E0 amount. So it's important to note that call data load is going to load in a single word of call data onto the stack. And then what we're going to do is we're shifting right by this E0 value. So let's find out what E0 corresponds to. We can see E0 here, and we can see that it is 224. So what's the significance of this, of course, is if we have 256 bits in a uint in a word that is 32 bytes, then if we're shifting it to the right, if we're taking a value, shifting it to the right by 224 bits, we end up with 32 bits all the way on the right. And so essentially what we've done here is we've taken the call data, whatever was in that first word of the call data, now we have shifted it all the way to the right until there's just these 32 bytes here, or I'm sorry, 32 bits here, 32 bits. That's literally all we're left here is 32 bits. Instead of having a full word, we shrunk it down to 32 bits, which is of course 32 divided by 8 bits per byte. We have 4 bytes here, and of course, what is 4 bytes but a function selector? So exactly what we're doing here is we're getting the function selector from the call data onto the stack. And then what we're doing, as you see, we have these push 4s. You might actually recognize some of these selectors, is we're pushing the function selectors in the contract onto the stack, and we're comparing it against this value that we just got from doing this shift from our call data. So we figure out essentially what function am I calling with my call data, and then we say, well, what functions do we have in this contract? And then we check one by one, and we see, does this function selector match this, for instance, this function? If it does, then ultimately we're going to push a location that sort of, it maps to where that function begins, where the opcodes that can basically play out the function logic actually live. And if it doesn't, then we're going to continue on and look at the next opcode. So you might recognize this OX666 because we did a sig of count, and that is exactly the function selector for count here. So we are actually on this first attempt going to see that these are equal, and then we're going to push this on, and then we're going to jump to that portion of the opcodes. But before we sort of step this through and actually go there, there's a few things to note. Of course, why is it that this was first? Now, you might be thinking that, oh, well, it's just because count was first here and it had the auto-generated view function, the getter function for count, and since it's first here, those were maybe just put at the top of the contract or something like that. But it's actually because the function selectors here are ordered by numerical value. So for instance, if I take this 0666 here, and if we want to make this into a decimal integer, we can see it's this value. Meanwhile, if I take the very next one and I go and we make this into a decimal here, then we can see it is considerably bigger. And then even more so, if I go to the next one after that, then what we'll see is we have this, and then that one's even much bigger than the one before it. So these are ascending in the numerical value of the bytes for the function selector. And so when we have, I think it's 4 functions or less in a contract, it will actually do a linear search like this where it will go through all of them one by one. And so it will actually be more gas efficient, technically speaking, at this opcode level. Call a function that has a lower byte value for its function signature, because you only have to get to this first one and then you say, oh, well, this is the first one that we're calling. We don't need to waste gas doing all these other opcodes, checking for all these other function signatures. We're just going to jump right to where that logic is and then execute it. However, when there are more than 4 different functions here in a contract, then it actually switches to using a binary search, right? Because all of these are actually ordered in order of ascending byte values. Okay, and then we can see that we continue to walk through, and then we push the selector on, we see if it's equal, then we push where the location of all that logic for this function is, for this getter function, and then we're going to jump to it. We're going to jump to 51 here until we will ultimately get to an S load to actually load in that storage slot and then ultimately return it as a part of the return value of the view function. So that is absolutely everything that you need to know about the EVM and how these things actually execute and, become executable as bytecode at a low level. I really hope that this video was informative for you. Perhaps the EVM was something entirely mysterious before this. I really hope that this made it very digestible and easy to understand. And for those of you who already had a very in-depth knowledge of the EVM, I hope that this just confirmed your understanding, and then of course maybe you picked up a few little things along the way that you didn't know. So I think what we'll do first is, before we go all the way into solidity, let me make a contract. So let's just call it test memory vessel string. So string memory test string equals hello. And let me change the compiler. Okay. So we've got this external pure function that doesn't really do anything but declares a string. So we'll deploy this, call this, and we're going to walk through. So let's find memory. All right, fantastic. So here we are with OX0. This is the first memory slot, right? This is the first 32 bytes. So we can prove this to ourselves and just measure how many zeros is this. This is 64. So remember, a single byte is 2 characters, so that's 32 bytes. OX20, there's the second sort of scratch space slot. Then we've got OX40 here. This is the free memory pointer, which we laid out here, OX40. And initially this is pointing to OX80. And we don't even see anything beyond this because, of course, OX60 is the 0 slot, there's nothing there, and OX80 is, as the free memory pointer is telling us, currently empty. It's all zeros, and we are free to write memory there. So if we continue to step through, this is before the string has been written. So now you can see the free memory pointer just changed. I'm going to step a little bit more. Okay. Okay. So here I've stepped. So before we were at, this is before the string was written to memory. Now after. So the free memory pointer was automatically updated by solidity. The language sort of handled that. So now We're pointing to C0, which is past A0. That's the next empty spot now. And that's because we've allocated 2 words. The first word is 5, and this is saying how many bytes are allocated in the next word for the length of my string. And then we've got 1 byte, 2 byte, 3 byte, 4 byte, 5 byte, and each of these bytes is H, E, L, L. We can see 6C, 6C, that's the byte representation of L, and then 6F, which gives us O. And so that's hello stored in memory. So are there any questions just based on that? All right.
Yeah, probably one question, Owen.
Yeah.
Why do we use it? Is it mostly for gas optimization?
Yeah, so why, of course, why would we use low-level memory like this? Or, inline assembly to interact with memory and things like this. So if we're using blocks like this, yeah, 100% this is for gas optimization. Sometimes, very esoteric things might not be able to be accomplished in straight up solidity, but the vast majority of cases is just going to be gas optimization, things that, you want to make hyper optimized. And you'll see this in, really more mature code bases or even simple stuff like proxies. So actually, let me find, we can look at an example of this. Let's find the Gnosis safe GitHub, and we'll just have a quick look at that. I think that would be a good intermediate step before we go to solidity. Let me see if I can find not this, but the proxy. So proxy, safe proxy. Okay, so here's one use case where assembly really makes sense. We are aiming to optimize to the nth degree. Now this safe proxy, this is a contract that's going to be deployed for every single instance of a Gnosis safe. So if you guys don't know, a Gnosis safe is a multi-sig wallet, and there are, I don't even know, hundreds of thousands of these that have been deployed, maybe millions, I don't know, but tons of these get deployed. And instead of deploying the entire logic for the safe, which is this big contract, which would be expensive to deploy every time, it inherits from a ton of things, as we can see. Instead, what we deploy is we deploy just this proxy. And this is really short, super optimized, and what it does is it just points to the implementation of that thing. And so every time you call this, it's going to hit this fallback function and do this thing. And we want this to be absolutely optimized because, first of all, it's a really simple thing to do, and second of all, on every single transaction, we're going to have to spend gas to do whatever happens in this function. So what do we do here in this assembly block? We'll just walk through quickly. So we're going to get the address of the singleton, which is the instance of the safe contract that we're going to be basically delegate calling to later on. So what we do is we sload slot 0, which is where this address is stored. We're ANDing it with 20 bytes of Fs. So I can read these bytes. We can go into a Python shell. We can do len of this, and we can see that it's 40. Right, so 20 bytes. Why did we do that? So an address is only 160 bits, right? It doesn't take up a full word. So we actually only need to, we're sort of like bit masking it, ANDing it with all of these ones. So the leading 12 bits get cut off. What does any of that mean? So as an address, let me see, what's a good USDC address? Let me just grab a example address. Okay, here's an example address. If we drag this up here, it doesn't fill a full word. In fact, there's 12 bytes in front of this that when I write an address to memory, it's got, a ton of zeros in front of it. It's got exactly 12 bytes of zeros. I don't know if I wrote enough, but it's got some amount of zeros trailing. So what we do when we AND it with FFFFF is, that is basically saying, F, 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 for all of these, and then all of this is 0. So then we literally just get the address when we AND it like that. So it's not super important to fully understand everything that's going on here, but that's how we get the singleton address. Then we are storing the singleton address at 0, and what are we doing? We are call data loading. So this is, we're checking basically what is the call data of the first sort of word here in call data, comparing it to this function selector. Let's talk about function selectors. So if I want to, here they're looking for master copy, this function selector. I can do cast to sig master copy. I think I need to put that in quotes. We're going to get the function. Maybe it's, I need cast help.
It's cast sig, I think.
Yes, you're right. Cast sig. There we go. Okay, that's a function selector. That's just the catch-all hash of whatever this is. Take the first 4 bytes. That's a function selector. We're seeing if we're trying to call that function, we're going to do this stuff. Now, master copy is just supposed to be sort of like a view function that returns, okay, what is the singleton, right? What is the implementation of this? What's the master copy? So we store that, what we've stored is the singleton, and then we return from 0 to OX20. So we wrote that at the first word, then we're returning the first word. And why did we, AND this to only get the address? Well, in some cases you don't know if there's a bunch of dirty bits up here. You don't know if this is one, F, F. You don't know what's written up here. Depending on, maybe there's some sort of compiler flaw, or there's, in some cases there can be dirty bits there. And I think, yeah, depending on, especially if you're accepting it as a parameter to a function, it is possible to have nonsense up here. So we want to cut that stuff off. We don't want to just blindly take it in. But, these are slightly more involved details that you really don't have to worry about unless you just happen to find yourself auditing something like this or something like the safe transfer lib. But those are just good things to know nonetheless. Okay, so that's kind of like a special case if we're trying to get what the master copy is. Then we're going to call data copy. We're going to go from 0 as the start to call data size. We're going to copy that to starting at the 0th slot in memory. So all the call data, we're going to put that all in memory. Call data, copy it into memory. And then we're going to delegate call, forward all the gas to the implementation from the 0th slot in memory to the call data size. So literally what we just copied, everything into memory, we're going to pass that call data on. So this is exactly, Demo, when you're asking, how do we put stuff into call data? At the Yul level, we can pass it to these functions, which are essentially opcodes, right? So the opcode will take the start of the input in memory to the end of the input in memory, and that is what will be used as the call data. So often when we're calling a function, we'll define like, hey, I'm calling this function. I want to give it the call data from here to here. That's the call data I want to use. That's how I want to put it into this function and call that thing with these bytes. And then this is when I'm returning something. Here is, the offset at which I want to copy the call data back into our memory, which is 0. And then this is the amount of call data I want to copy back into our memory from the return from this external call. So in this example, they're not copying any return data into anything. So does that right there make sense for taking memory into call data?
Yeah.
Okay, perfect.
I'll have to rewatch it, but Owen, please don't ask us to rewrite the perpetuals in assembly.
Yeah,
the final boss.
I can't even stomach that. So yeah, definitely will not. Okay, and then here's what they're doing is now they're doing a return data copy. They're copying all of this from, and I don't actually know why they didn't just move this into these last two here. Maybe this is because return data size at this point, I don't think actually it would be accurate. So I think that's why they had to do this on another line. But this is where they're getting the return value from this delegate call. And then if it failed, they're reverting and they're giving all the data about the revert. If it succeeded, then they're just returning and they're giving all the data. So I don't expect all of that to make 100% sense right off the bat, but of course, you know, watch this back if you get a chance, and that will hopefully start to click and make sense. So this is one instance of where you would want to use this. We just want to hyper optimize this proxy contract that gets deployed literally every single time a new wallet, a new multi-sig wallet is created. So things that are going to happen a lot of times. This is probably saved, I don't know, potentially hundreds of thousands of dollars. I mean, maybe millions on mainnet in terms of gas, just having this. So that can definitely be valuable. And then let's go to the safe transfer lib and let's talk about this one balance of function before we wrap up here. So there's not too many lines of assembly. We just tackled something that had a lot more, and there's a lot more dynamic. But Vectorized, who's the main developer behind Solidity, he uses memory in a much more dynamic way to be more efficient, right? To fit stuff into smaller amounts of memory words. Because the more memory you allocate, the more gas you're going to have to expend in that transaction. So the first thing that we're doing here is let me just make this bigger for folks. See if I can put that away. Okay. So hopefully this is big enough. First thing we're doing is we're storing at OX14, we're storing the account address. So let's have a look. What does that do? So we're storing 32 bytes. mStore will always store 32 bytes, a full 32 bytes. If the thing that you're storing is not a full 32 bytes, so we'll just pad it out with zeros. So here's 32 bytes. We're storing an address. So we know that an address, when we break this into an address, there's 12 bytes that are just kind of useless. That could be dirty bytes. We don't know for sure. And then there's 20 bytes that are home to the actual address. So let me copy this, make this, actually copy this, bring this down here. I don't know if this is actually 64 bytes or 32 bytes. It should be close. So here's what we just did. We stored this thing at OX14. That's what we did on this line. So OX14, what the heck is OX14? Let's do our handy cast to des. Let's figure out what is OX14. OX14 is 20. So before this in memory, there's 20 bytes. of just empty. We haven't assigned to it anything yet. And you'll notice this guy is breaking a fundamental like rule that we said, right? Right now he's writing inside of this first slot. This should be reserved for the EVM as scratch space, right? So I said, unless you really know what you're doing, don't mess with these first 2 slots. Well, this guy really knows what he's doing. And so he's messing with those first 2 slots. And, you know, in the case that he's using these, it's actually fine because, you know, there's none of the logic here is going to end up in the EVM needing to use that scratch space in the context of, you know, everything that's happening here. So this is actually fine in his very specific case. So this is all we've done so far. Just stored something here. Now he's storing something at OX00. And this looks pretty odd. There's a bunch of zeros here. He's got a function selector for balance of, which is ultimately what this function is calling on the token for the account. Why did he do all these zeros, right? So he's doing something very specific here. Remember that mstore always stores a full word, full 32 bytes at whatever offset this is. So if I go ahead and let me just copy this, if we go to OX00, we're storing a full 32 bytes starting at 0. So we'll just demark OX00. Now he specified this. Now what actually gets stored is we have to fill up this 32 bytes. So it actually gets padded out to a full 32 bytes. Now I'm going to pretend that I put enough zeros there. And look what happens. So what he ends up doing is he ends up overwriting all of this here, which was the useless piece of whatever this address was. So here's the actual address. It's these 20 bytes. Remember, we had these 12 bytes, which were just kind of useless. Well, that's exactly what all of these zeros are for. So if we just copy this, check this in a Python shell, this should be 24 characters, which is 12 bytes. So all of these zeros are very conveniently overwriting the start of this address. And he has to do that to be careful to avoid any dirty values in here. And so that's exactly why he has all these zeros explicitly like that. And then he's put the selector, the function selector, right at the start there. And of course, we always need a function selector at the start of what will be our call data to specify what is the function that we're trying to call. So this is the layout of memory thus far. Now we're going to do this big thing. So we're going to go in, we're going to ignore what's happening here, ignore what's happening here, ignore this, and we're going to go to this. This is actually the next thing that will get evaluated. And he has a note on this here. The arguments of AND are evaluated from right to left. So this thing will happen, and then this thing will be computed, and then we'll go on from there. So the next thing we do is we static call. So static call is like an external call, but it's specifying that no state will change. So it's like calling a view function. When you call a view function, you static call. And if state is attempted to be changed, it will just revert. That's not expected, we're just going to revert. So we're static calling, forwarding all the current gas, or 63, 64 of the current gas, calling the token, and we're calling it with an call data starting at the offset of OX10, spanning for the next OX24 bytes. That's our call data. And then we're going to copy some stuff starting at OX20 we're going to copy a full word, 32 bytes of return data. So let's break that down. So what's the call data for this here? Well, we had OX14 here. OX10 is exactly 4 bytes before that. So that is just enough to take our function selector plus all of these, the 12 bytes that we used to overwrite the sort of like useless space of the address. And then we get the full actual address. So how many bytes did we just cover? We covered 4 right here, plus 12 for those sort of useless zeros that we just need, plus 20. So we've covered a total of 36 bytes, starting at OX10. So OX10 is the starting point, and then OX24, we expect that to be 36. So if we cast to des, OX24 is indeed 36. So here's exactly what we're calling this token balance of function with. Boom. So here's the function selector for balance of. Then we're going to come and we've got this, the address here. Boom. We've got the address. So, and then we're calling the token with this data. So when the token gets called, it says, okay, you're looking for the balance of function. That's the selector for balance of. The balance of function accepts a single address. So we're going to look at the next memory word. We're going to get the address from that. Of course, the address is only 20 bytes long, so it's the last 20 bytes of that. So you're looking for the balance of for this address. We're going to call that function. It's a view function. We're static calling it. And we're going to return to you whatever the output is. Now, remember the return value is a uint 256. That's what we're expecting when you call a token balance of function. So we need to write that return value back. So when we do write it, we're going to start writing it at OX20, which is right here after the first word. So everything over here, that's the first word from OX00 to OX1F. Everything over here is OX20 to OX3F. Right, so this is the second word, this is the first word. We're writing the result starting at the second word, filling up the entire word. We're giving you 32 bytes. OX20 equals 32, 32 bytes. So we're just filling up, overwriting, we don't care whatever was written here previously. We're writing the result to this entire word. Let's say I have 100 tokens. You're going to write 100 tokens. Or, more explicitly, stored in hex. It will be OX64. So OX64, it will be prepended with a ton of zeros, padded out, and stored at OX20. So what that would look like is, OX20. So what that would look like is 64. It's stored right there in that slot. That's copied right there. He's asserting that the return data size is at least 32 bytes, otherwise something unexpected happened with this token. If the call successfully completed and there's more than 32 bytes, or 32 bytes and more there, then this is true, which means this returns 1. And then he's multiplying 1 in the success case with what was stored at OX20, which was, of course, the result, which is our balance. So this OX64 that was stored right here, e.g. my balance of 100, is what is assigned ultimately to the amount when this succeeds. And that is what is returned. That's how we get 100. So there's a few things that we just went over. There's a lot that just happened there. What questions do you guys have based on that?
I think too many at the moment. I will have to think about this.
Okay, yes. Yeah, definitely let that sink in, and you guys will have the video to play this back and go over that a few more times. And of course, you know, we can talk through the exercises in office hours, you know, if you guys start on those and start to get stuck. It's definitely a struggle to, you know, begin to sort of translate everything that's going on here into, you know, actually memory. But to be honest, once you can understand what is happening in this function and some of these other functions, you'll start to realize that, like, first of all, it's actually, you know, what's going on here is not too complex, as long as, you know, you just have to break it down and think about it step by step. But once you learn these like basic rules and you're able to walk through this is as hard as it gets, really, you know, beyond incorporating advanced mathematics, which, you know, to be honest, is just outside of most auditors' purview. This is as advanced as it gets. So once you guys can, you know, understand this, then you guys will be very well equipped to look at any other assembly in the future. So once again, you'll have the video to go back over this stuff, and then of course, any questions that you guys have, we'll be able to talk about those. So that is it for really the overview on memory. So first of all, I guess how was the assignment for folks? Did you guys find it challenging? Was it accomplishable, or just really confusing?
By watching your video, it was accomplishable and very good training to understand inline assembly. But your video, the record, was very helpful in order to do it.
Awesome. Glad to hear that. Yeah, were there any questions in particular that people wanted to go over, or do you just want to go over the whole thing? Yep, memory safety. Okay, cool. So let's see, which one is that? Okay, in the safe transfer from function, is this memory safe assembly? So first of all, let's have a look at the safe transfer from, and then let's define memory safe. Okay. So we've got this function here, and we've got memory safe denoted here. Is this true? Is this assembly block actually memory safe? Let's have a look. So first of all, memory safety. Let me see if I already have this written out. Yeah, we've got this up here. Nope. Somewhere we were going through memory. Right here. All right, so this is, there's a bit of junk here. So I'm gonna see if we can just clean this up. Okay, so this, we're gonna delete that. Gonna delete this. All right. So we've got, remember, this is our layout of memory. I don't know why this is like that. This will start out, let's say it's OX80, and let's say this is empty. So here, these first two words here, so remember a word is 32 bytes in memory. First two words, OX00 and OX20, are scratch space. So these are reserved for the EVM. So when we talk about memory safety, we want to be preserving basically the important properties of memory at a low level. So we've got this scratch space, and we expect that it will be fine to either, like in most cases you want to just avoid writing to scratch space, but as we'll see when we start to look at some of these functions, in some cases it is actually fine to use that scratch space when we know that, hey, we're not, it's not currently being used by any hashing functions or something like that. So after the scratch space, we have the free memory pointer. So here we've got this initialized to 0x80, that's where it will start off, and we saw that earlier, pointing to this, which is the first free memory slot, doesn't have anything stored here. And we've got the 0 slot here. So this is intended to always just be 0 uninitialized, nothing stored here. And then beyond 0x80, these are all just empty things that haven't been used to allocate stuff. And so what we mean when we talk about memory safety is really a few things. So first of all, is the free memory pointer still accurate, right? Does this still point to the furthest place in memory that is unallocated, right? So if there was something written here, the free memory pointer should go to A0, right? It should be pointing to this.
So when we're talking about the memory safety, is it looking at the result at the end of the function or throughout the function as well?
Yeah, basically at the end of the function. So if the free memory pointer, like in between here in this assembly, the free memory pointer might not be technically accurate or something like this, but then when you're restoring it or something like this after the function, then it can be valid. And as long as you're exiting this assembly block and the things that we're going to list out here are holding true, then it is considered memory safe. So yeah, the first thing is the free memory pointer still accurate? The next thing is, did you overwrite memory that was previously allocated? So if there was previously memory written here at 0x80, did this function overwrite it and turn it into something else, something that it wasn't before? That would cause issues if there was previously some, something in memory that was being referenced before this call to save transfer from, and then calling this internal function would somehow overwrite that and perturb that memory, so that if you then tried to reference back to that variable in memory, it would give you some value that wasn't what was stored there previously. So did you overwrite memory that was previously allocated? And basically what this means is only change stuff after the free memory pointer. We'll also see that they do some, in this library, they do some karate, I would call it jujitsu, but it's more karate, with using the scratch space and stuff like this. And this can also be memory safe in the sense of not overwriting memory that was previously allocated, because we know that the user will never have already allocated memory in this scratch space, or we know that if the scratch space was previously used, we just so happen to know that if we're getting to call this internal function, then we're not in the middle of doing a hash function or something like that. So it is safe to write to these two here. So thirdly, is the 0 slot still a 0 value? Right, so this 0 slot is important for, I think, a few different use cases, I believe, but at least I think the initial default value for like dynamic arrays or something like this, I think this is necessary for having them point to this to be like the length of this array is 0. This is a sort of like uninitialized dynamic array that has nothing in it yet. So it's important that the 0 slot maintains the 0 value. And these are really the the three things that we want to pay attention to exiting an assembly block, that this thing is memory safe. So in the case of safe transfer from, we are first caching the free memory pointer because he's actually writing to OX40, so this is where the free memory pointer is. You're actually overwriting it. The reason this is still safe is because at the end of safe transfer from, we are storing the free memory pointer back to what we saved it as at the beginning. So just like the comment says, we're restoring the free memory pointer, and we're doing the same to the 0 slot, because we'll notice that we're overwriting the 0 slot with the amount, and then we need to restore that to 0, of course. And then in terms of our first, so the free memory pointer, is this still accurate? So we know that the free memory pointer is going to point to something OX80 and beyond. We're not allocating any memory here beyond OX80, or yeah, we're not even getting to OX80 here. I think the furthest thing that's being stored is this OX60 word. So that's the furthest that we're going. And so we know that we're not allocating any additional memory, and we don't need to update the free memory pointer to go past that, whatever the free memory pointer previously was, which was at minimum OX80. If no memory was previously allocated, that is going to be fine to just write to the free memory pointer slot. So did we overwrite memory that was previously allocated? Again, we never touched anything that was past this OX60 variable, this OX60 word, and we know that the user wouldn't have any memory allocated in these 4 words here. So we're fine on that point as well. And then, of course, we know that we restored the 0 slot. So this function is indeed actually memory safe. So does number 3 make sense to folks now?
Yeah, but I have a question. Why sometimes there is like memory safe into parentheses in front of the assembly keyword? Does that mean that there is no, we are not writing, overriding the memory point, free memory pointer?
Yeah, so do you mean like they have here?
Not exactly. Let me show you an example.
Yeah, let's see.
In line 523. No, I sent you a link in the chat.
Yeah, let's see. 5. This is basically enabling some like optimizations to be able to happen. So this is beyond my specific knowledge of how the optimizer works for the Yul optimizer, but this will essentially, it's like a compiler flag almost, to basically let the compiler know we are using memory safe assembly here. And then I think based on that, there are certain optimizations that are safe to use in that case. So that's the greatest detail I can go into on that. But does that make sense?
Yeah, completely. It's like an unchecked or something to make the code more gas efficient, to avoid checks while compiling, something like this.
Yeah, exactly. Like to my knowledge, the way the optimizer works is it will take the solidity optimizer will take your solidity code, and it actually translates it, or sort of transpiles it into Yul, and then they have some optimization rules that can be run on that Yul to sort of restructure it and make that Yul code as optimal as possible, as gas efficient as possible. And then there's a second step to go from that Yul to actually go to like raw bytecode, raw opcodes, and then there's optimizations that can happen at that level. So I think this would probably affect that second layer of optimizations.
Thank you. Got it.
But I'm no means an expert on the compiler or optimizations. So that's my my 2 cents on that. All right, great. So that was number 3. Were there any other ones that people wanted to specifically go over?
Yeah, maybe you can go through that one. I think and that took a little bit of time to understand.
Yeah, let's see on line 191. Okay. Yes, so this one is actually a security concern. If you ever find yourself auditing something using assembly, using Yul, and using specifically addresses, you'll want to pay attention to this idea of shaving off the leading 12 bytes of the address. So we know that a word is 32 bytes. However, an address is 160 bits, or just 20 bytes, which means that there's basically 12 bytes of just empty space, right? And specifically what that would look like is, let's see, I think I had even an example. So here's an address, right? So I'm going to actually copy this. This is exactly what we're looking for. So this thing right here, this is an address. Now, 1, 2, 3, 1, 2, 3. Okay, so here's an address. I can't tell if that A belongs to the address. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so this should be the address. We'll see, maybe I miscounted by 1, but this is 20 bytes. So this is your actual Ethereum address here. I think it starts with that 0 and then it goes all the way to the end. And then we've got 12 bytes that are leading here. And these are just, for any address, these are basically useless, right? Because no address, like every address is just constrained to 20 bytes. So whenever I input an address as a parameter to a function, in Solidity, it's going to automatically only consider these 20 bytes. But when you go down to Yul and we start doing things such as storing the from into memory with mstore, remember mstore will always store 32 bytes. Let me just plug in my computer here. So we're always going to store 32 bytes, and we're not going to, out of the box, consider that we need to make sure that we clear these first 12 bytes, because a malicious person could actually put a bunch of like unexpected bytes here. So you could have a ton of like just dirty bits is exactly what they're called. So just a bunch of like, you know, non-zero things when canonically you'd expect these to be zeroed out. And that can cause issues. Specifically, if we didn't shift left by 96, which is these 12 bytes, and we kept those bits in there, then those dirty bytes can actually end up when we pass the call data to call the token. So we're going to pass the input from 1C to 6.4, or 1C with a length of 6.4. Those dirty bytes can actually be inside of that, and that's going to make its way into the call data of what we're calling. So in some cases that can be a critical issue. So let's walk through what's being done here to avoid that. So let's visualize what memory looks like. So we've got our memory here. We just delete that. So what are we doing? At 0x60, we're writing the amount. So let's say my amount, let's say I'm just doing 32. I think that's going to be a 220. That should be 32. So then OX40, we're writing the to argument. So I'm going to grab my address, and we're going to use the version that has dirty bits. So OX40, we're just writing the to argument. Let's pretend every single address has dirty bits. So I'm going to go to OX40, and this is what we wrote there. We wrote the address, but we've also got dirty bits here. So we need to make sure that those get cleared or they can affect the system somehow. So we'll be checking for that. All right, here at OX2C, we're going to store the from argument. So for this one, I'm going to need to pull up my terminal. Cast to des 2C, so that's 44. So let's see, so this is, you're going to see this is where the karate comes in. So 44 is here at this point, when we get to this byte, we're at 32. So I suppose I have no other option but to count this out. So I think that's what we're going to do. All right, so 32, I'm going to count up to 44. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Just put a little thing right there. So starting at 44, we're going to write a whole 32 byte thing. So this is 12 bytes right here, because I went from 32 to 44, so this is 12 for this section. Then remaining here, this is 20 bytes. Now I also know that this address goes like that. Here's the 20 bytes for the actual address. Here's the 12 bytes. That's a bunch of junk that we wrote there. So here's where we start to use some smart tricks. So we're storing at OX2C a full address shifted to the left by 96 bits. So what does this look like? So we'll take our address, we're going to shift it to the left. Let me just copy this. Shift it to the left 96 bits. So that means we take this, shift it to the left. Now these, when you shift something to the left, automatically just by default zeros come when we're going to write this, because we're still going to pad it out to a 32 byte thing when we write this. So so when you shift to the left, we're going to get these zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's what we get as our padded out thing.
I have a small question. So when you shift to the left, what happens with the dirty byte? Do they get pushed to the previous word, or do they just disappear?
Yeah, they just disappear, right? So we're just getting rid of them. So now here's the interesting part is we're writing starting at OX2C. So remember I counted up to OX2C, and this is exactly where we are. So OX2C, that's where I counted up to. That's 44 bytes from 0. So we write our 32 byte thing starting there. So here's what it looks like. We've got 20 bytes here, so that's going to be the actual address. So those 20 bytes go right there. And then these bytes go right here, and they overwrite those dirty values. So let me just put this in. Our address gets written there, and then these dirty things, they all get overwritten back to 0. Okay, so does that move, did that move make sense to folks? Did people see what just happened there?
Yeah, it was very clear.
Okay, cool. So yeah, just to reiterate, we wrote a 32-byte thing to the word starting at OX2C. You can write a word at any offset, right? I can write a 32-byte thing starting from here, anywhere. So for the following 32 bytes from here, we wrote that address that had these zeros at the end instead of zeros at the front. And that was a very smart move because with that one move, he protected against the dirty bytes in front of this address by just shifting to the left. And he also protected from the dirty bytes in front of this address because it was overriding this. So with that one move, he basically protected against both of those addresses having dirty bytes. And the reason that's important is because later on, when we eventually call the token and we attempt to call the transfer function, we are going to call it from OX1C, which is ultimately like somewhere right here or something like that. And then we're going to go for 64, so that's going to be a 4-byte selector plus 3 words. So that's going to take us to something like right there. I might be off a little bit, but the main point is that this is a part of the call data. And if we didn't overwrite those dirty bits in the call data, then those dirty bits would have made it through and they would have been basically included in the call data on the token. So when we were calling the token, they could have specified arbitrary bits there that could have potentially caused some issues. And so that's essentially the answer to question 2. So does that make sense why we want to clear the dirty bits?
Yes, I have one question. So the input offset, or where we start to read the arguments, start at 0x1c. Why do we go back all the way there and not start from the first argument?
Yeah, that's a good question. So we can see, so after we did that, then we're storing the function selector. And we're storing the function selector starting at OXOC. So let's find OXOC here. So go into my terminal, cast 2x, 2des, OXOC. So that's a 12-byte offset. So I'm going to eyeball it, and it looks like the 12-byte offset is perhaps right here. So here is actually OXOC. That's OXOC, not OX1C. So I'm just going to remove this arrow, remove this, label this OXOC. So here he's writing a 32-byte thing, and it's this. Now you might get confused if you attempt to write it like this, where that thing just starts like that. That is not actually what this is going to look like. So this thing has, let's see how many zeros. So this is, actually let me just check the length of this thing in Python. So we've got 32. So this is, and don't be confused, that's not 32 bytes. That is 16 bytes, because there's 2 characters for a single byte. So there's 16 bytes here, which means that the actual full word that's going to get written here is this plus, let's see, plus 16 bytes on front. So it's going to get, whatever you write is going to get padded out to be a full word, and those zeros are going to get added on front. So I'm going to do 1, 2, 1, 2. There's 2 bytes. There's 4 bytes. There's 8, 12, 16. This is the full thing that gets written starting at OXOC. Now I happen to know that this is 12 bytes over here. I just wrote 16, which means that this is 20, and this is going to get filled to be exactly the leading 16 bytes plus these 4 bytes here. So this will exactly be that. We'll just hope, and I won't spend the time to count it out. And then these things, so this should be 16 bytes minus 4 bytes. This should be 12 bytes. So this is 12 bytes of zeros. And indeed, 12 bytes of zeros fits perfectly right here. That's a little non-reassuring that changed in length, but I guess take me on my face value here for that one. So we want to know now where is OX1C, because that's the start of the actual input for the call data. So cast to des OX1C, it's 28. So I know OC is 12, so we're going to go another 16 bytes. So 16 bytes, that would put us right here, right before the last 4 bytes here. So we can count them out just to be sure. There we go, that's 32, which is 16 bytes. So here is OX1C right there. So this is the start of our input. And remember, when we make an external call, the function selector should be the first 4 bytes there. And so here's what our call data looks like. This will be good for understanding, what's the structure of call data. So we've got our function selector. Then the very next whole entire word is 12 bytes of zeros, followed by 20 bytes of an actual address. That's good. That's exactly what an address is. It's a full word where the first 12 bytes are always presumed to be 0. Then the next thing is another 12 bytes of zeros, followed by 20 bytes of an actual address. That's good as well. That's an address within a word. And let's look at what function we're calling. We're calling from transfer from address uint256. So let's see, the uint256 now should be stored at OX60, and of course it is, right? We look here, and at OX60 we were storing the amount, and so that's how we're getting address uint256 into the call data here. And like I said, the call data is spanning basically from right here into all these words right there. And that's why, to answer your original question, that's why we're going back and we're starting at OX1C, because we want to get this 4 byte selector, and then we also need to have that 12 byte padding, because the address is still going to be passed as a full 32 byte word. We're not just going to interpret addresses as 20 byte things. Does that make sense?
Yeah, it makes total sense. It's really cool to see. So when you set the call input, it will read word-wise. So it will start by just reading these 4 bytes at the beginning, and then each argument will be for each word, if I understand correctly.
Yeah, exactly. And you know what? I think we can actually do something really cool. So what we'll do is I'm going to grab this selector. I'm not going to do that. Grab this. I'm going to copy this. I'm going to construct what our call data looks like. So we've got this. So our call data starts off like that, and then we've got these 12 bytes. Let me just double check that this is indeed 12. That does not look like 12, so I missed something up there. So I'm just going to, actually no, that is 12. Yeah, so we got 24, That's 12 bytes, so that's perfect. All right, so I'm going to copy this. Boom. Then we're going to take, here's the address. Boom. So far we've got function selector, the word for the address, the first address. Now we're going to grab the second. This should be 12 bytes as well, so I'm just going to copy the one from before, append that on there, and we're going to grab, I believe this is, let me just check the length of this thing as well. So I'm expecting this to be 40. Oh, I guess we'll just add another 0. Boom. And then here, I'm just going to copy the whole word for this uint 256. So 32 bytes for that. And now, what we're going to do is we're going to do cast pretty Calldata, and there we go. So this, they've what Foundry's done is they knew exactly what method we're calling from the 4-byte selector. This is a common selector, so we know that that corresponds to transfer from or address uint 256. Here's the first word. This is the first address. So that's, I think it's the from. And then the second address is the to. So that's this word right here. And then at the offset of OX40, we've got the uint 256 amount, which we put as 32 or OX20. So yeah, that's basically how we construct the Calldata. Let's see if any of these are, I think this one was pretty easy. That's a function selector. We went over this. That is for dirty bit protection. We went over memory safety. We just went over why is 1C provided as the fourth argument. So let's see, 197. So yeah, 1C, that is the start of the Calldata, so the offset for where the Calldata begins, and then the length is OX64, and we went over why the start is right here. Safe transfer function, why is revert used with 1C and OX4. So at 1C, what we've done is we've stored at 0. We stored just a 4-byte selector, and so this is exactly what happens when you store at 0, just a 4-byte selector. You get this whole word padded with a bunch of zeros at the front, and at 1C is the beginning of the actual 4-byte selector. And so we're reverting, starting at that thing for the next 4 bytes. That is the revert data, and the revert data is just our selector here for the transfer failed error. On line 268, why is 0 stored? Right, so here again, this has to do with memory safety. So in this function, only part of the free memory pointer was written into. So we just are restoring that amount, that part of the free memory pointer. Number 7, why is safe approve? Function safe approve. We're checking for, imload of 0, 0. So imload 0, 0, why is that checked for equality with 1? So here, this will put so this is the out, the beginning of where the output, the return data should be copied into memory. And then this is the length of the return data. So what we're doing is we're calling this function, so that will be defined in the call data. I know that based on the function selector here, we're calling approve. And then when we get a response back from approve, we're looking at, okay, what is that response? We're going to return data copy that return data into memory. Starting at the 0 offset, we're going to copy a single word of that return data. There should only be a single word from the approve function. It should return just a Boolean. And so that's why we're checking, is the thing that we just copied, is that 1, which is going to be true, I think, unless I'm mistaken. I always get those confused, but 1 should be true. So if it's true, yes, if it's true and the call actually worked, so if the call didn't revert, then this will be 1, which means we will not go in here and we will successfully complete execution. So basically, the reason we're checking this for equal to 1 is we're checking if the approval actually worked. So like if an approval failed and you're using a token like USDT, it might return false, and then in which case this would be 0, and then there's an issue and this would be 0, and then is 0 would be true, and then you would revert. Okay, if the token returns false from the approve function, well, we just looked at this. So if it returns false, this will be false. Of course, we're ORing this with if the return data size is 0. It is not 0 if it returned false, right? We did return some data. So this will be false. So this OR will be false, which means this AND will be false, which means is 0 will be true, and we will revert. And that is every question there. All right, fantastic. So I have a transaction here pulled up, and this is actually a transaction on the Avalanche testnet. And this particular transaction is interacting with the GMX v2 system. And what this transaction is doing is it is creating an order, and then in a later transaction, the order will actually be executed. But this transaction here is specifically interested in the creation of an order. And we'll see exactly what kind of order. Is it a long? Is it a short? You know, what are we longing and stuff like this after we get to decode the call data here. So first of all, we scroll down and we can see this big blob of input data. Now this is what we're going to understand. We're going to actually decipher this blob of input data, and then we're going to understand what does all of this mean and how can we sort of take this and bring it into our understanding of how the system works and see that this is actually interfacing with a function in GMX. So right off the bat here, we need to understand one thing. We need to understand the idea of a function selector. And we've talked about these a few times before. Essentially, these are the first 4 bytes of the Kechek 256 hash of the API of a function, right? Basically the interface of a function. So let's see exactly what that looks like. We have a function selector here that is sort of prepended onto our call data. And this is so that we know what function we're trying to call with this huge blob of data, right? So we have all this data afterwards, and then we've got the function selector which tells us, okay, this is the function we're trying to call, and following these 4 bytes is all of the data we're trying to call it with. And so actually if we copy this selector, if we take these 4 bytes here, and then we go to the Ethereum signature database here, we can actually paste in these 4 bytes, and as long as it's a common signature here, we can actually see that this is the function for a multi-call that accepts a bytes array. And we can see actually, so if we take this function here, this signature, then we can use Foundry Cast to actually do this hashing and then grab just those first 4 bytes for us. So we're going to Kechek 256 hash the function name with the arguments here of a list of bytes, and we're going to get the function selector here. And so of course this function call is going to the exchange router contract. And of course, the exchange router contract is multi-callable. It has a multi-call function. And here's exactly where we get that. So this is the function that we're calling as the top level function in this transaction. Now this call data is going to be especially complex here because you'll notice the argument to the multi-call is a list of arbitrary bytes here, and each bytes item in this list is meant to be another function call, the data for another function call. So within this call data for this multi-call function, we actually have a list of other call data essentially, for which we're going to iterate through that list, and we're going to call that function with that independent iteration of call data. And what this is going to do is we delegate call to this exchange router. So essentially what we're just able to do is basically call multiple functions in this exchange router. We have all of these functions like send wrap network tokens, send tokens, create deposit, and create order, as we'll see. We can call these functions in an iteration, but we need to pass the list bytes call data to do that. So what that means is basically this big blob, what we're looking at here, is exactly that list of bytes. And each element of that list of bytes is itself more call data to be passed to one of these functions when we're delegate calling. So we're going to come back to this very top level view of the call data for the multi-call function at the end. So first starting off here, we actually want to just decode this and be able to get a nice view of just the list here. And then once we have a deeper understanding of how dynamic data is encoded in call data, then we will come back and we'll understand, we'll have the tools to completely understand exactly how that raw bytes array is encoded here. But before we get to that, we've already basically decoded that data here, and we can see we have decoded it into this bytes array. So now we have an array of, we can see it's only 2 items long, and we can see both of these look a lot like function calls. How am I able to tell this is because both of these sort of sets of data start with a selector here. So I can see that here's the selector for the first call data, and then here's the selector for the second call data. So let's have a look at this first call data here and understand this is the first function call that's going to happen. And we can see if I look in the Ethereum signature database, we have a function send wrap network token, send WNT. And of course, if we look on the exchange router, we can find this function that takes an address and an amount. And so this is the first function that is getting called in our multi-call. So now let's figure out from the multi-call data, what is the receiver and what is the amount parameters. If we go back to the transaction here, I'm going to copy all of this data, and then we can actually cast pretty call data and make this very readable. So we can see that it actually already told us exactly, somehow, you know, it knew to actually go and look up the common selector here, and it actually matched it up with send WNT. And so then we can see that, okay, there's address and a UNT 256, and we can see pretty clearly actually that this first slot and call data is indeed an address here. And if we actually go and look at this address, then we can see that this is an order vault contract, which makes sense in the GMX ecosystem. We want to be sending the wrap network token to the order vault to sort of fund the order. So this is the layout of call data here. We have these 32 byte words, which are probably familiar if you've looked at memory. And then we can see for these static types, and we'll understand what I mean more by static versus dynamic in just a second. For these static types, they are literally just encoded here one after another, and we have the address here, and then of course that means that this UNT 256 is in this second word here, and then of course we can see that if we want to decode this, we can of course do cast to decimal, and we can see that this is roughly, if we go into a Python shell, we can see that this is about 1 wrap network token, and then we have, you know, some leftover amount for, you know, possibly gas or things like this. So that is entirely what this 0th index in the bytes array here is. This is everything we need for this send WNT call, right? So we have the address parameter, and then we have the amount parameter here. So there's all the data we need for the first iteration of the multi-call, but now there is a second iteration of the multi-call, and we can see it is much larger. So let's see what this could possibly be. Well, actually, if we take this and we look it up in the Ethereum signature database, we can see that there is actually no common signature that is matching this. So what could this possibly be? Well, this is where some context comes in this particular transaction, because I know that this particular transaction was used to create an order. Of course, the first thing we're doing is we're sending WNT to the order vault. Then the very next thing that needs to be done is to actually create the order with the create order function. Now, the thing that makes this selector a little bit more complicated is, of course, that we have a create order params struct that's being used here. And this struct is not even just a trivial struct. If we go and we look at this struct actually contains several things here. It contains substructs, and it also contains enums. So if we go and look at this first substruct is also a non-trivial struct when we're talking about call data, because we have addresses, and then we have a list of addresses. And this is the first instance of dynamic data that we're seeing. So dynamic data is actually encoded distinctly different than static data, such as, all of these addresses and all of these uints, and this struct in general is static data because it doesn't contain any sort of dynamic data. So this one swap path here makes this entire struct considered to be a dynamic piece of data, which in turn makes this entire struct considered to be an entire dynamic piece of data. And so that is going to completely change, first of all, how this is stored in call data and how it's laid out in call data, and we are about to dig into that. But then also just the fact that we're using a struct here, and then also the fact that we have substructs and we have enums, this is going to make this function selector, first of all, obviously very rare, right? This is almost certainly the first time that this particular function selector has ever been used in a system, but it's also a little bit harder to compute exactly what the function selector is. So I've got the cast sig up here, and we can see this is actually how we get the function selector for this create order function. So we basically take each of those structs and we turn them into tuples, right? So we have, for that first struct, we have a tuple of address, a list of addresses. For that second tuple, we have all of these uints that make up that struct, and then we have the enums, right? And the enums are actually under the hood. This is essentially a uint 8, and then we have some booleans, and then we finally have the referral code here. So that's the referral code. We have our booleans, we have our uint 8s, and then these are our tuples here. So if we do this sig, we get this 4A393, and that is exactly the function selector that is right here. So we know that this call data, the second or the first index of this list, is referencing the create order function. And now everything that follows that function selector, this is the data that is going to become this top level dynamic struct. So let me go ahead and just copy this, and we will make this easy to understand. And so here we go. We can see here's our function selector, and then we can see a bunch of data, right? We have a bunch of different words here. How the heck are we going to figure out what all of this means, right? We've got a OX20, we've got an OX1A0, but what is all of this, right? So you might actually be able to sort of, guess and check and figure out, well, this looks like an address. This is also the first address in this piece of data, so I would guess this is like the start of the addresses here, and then we can see some subsequent addresses. So maybe this is the addresses struct, but then that would make this the offset for the swap path, but that doesn't really make sense as an offset, because of course C0, is that from the start of data? Where does it go? Or is it from here? And then it's like not even in the data. So you have a lot of questions if you don't understand exactly the difference between how memory is encoded and how call data is actually encoded. So in memory, for instance, if we had one of these structs and we were encoding these, then we would have an offset to that, the beginning of that actual struct. But of course, if you try to read this like that, then it doesn't actually necessarily sort of pan out like that, right? So we have an offset of just 20 bytes, which would put you here, and then this also looks like an offset. So it doesn't really make sense from that lens of the memory sort of layout. So what we need to do is we need to actually go to the Solidity docs, and we need to understand how is dynamic call data laid out. So first of all, we need to understand what are dynamic pieces of data, right? So first of all, we can see that bytes is a dynamic piece of data. We have a string, a list of any type, even a list for any dynamic type T, and then a tuple here, which is what we are interested in, because a struct is actually basically a tuple for Ti, T1 through, Tk, so all the elements of your struct. A struct is only dynamic if you have some T sub I, so one of these elements within your struct that is also dynamic. So we can see here, of course, the thing that is making this create order params struct a dynamic piece of data is the fact that inside of this struct we have a address of arbitrary length, and this here is one of these, right? We have an address array, and so this piece is a dynamic piece of data, which means that this is a entry in this tuple, and so this tuple fulfills this piece of criteria because this last swap path here is dynamic, which means that this is now a dynamic piece of data, which means that now this tuple, which contains this dynamic piece of data, is now also a dynamic piece of data. So that's going to affect how this whole thing is encoded. So then that, of course, begs the question, well, how is dynamic data encoded in call data? Well, we've got this definition here we can see for a tuple. For each element in the tuple, we have two options, right? Either the element is a static piece of data, otherwise the element is a dynamic piece of data. And then we can get this idea of a head versus a tail. So basically the data is going to be split up in a head. You'll see that earlier on in the words, and then it will basically point to a tail, which will be later on, and the tail is actually going to hold this, the actual encoding for the dynamic piece of data here. And we can see that if the element in the tuple is static, then the head is literally just the encoding, and then there is no tail, right? So if it is static, like if it's literally just an address or something like this, just put it there in that head word, and then there is no tail to go to. Otherwise, if it is dynamic, then we can see we have the head here, and I actually think that the docs kind of suck here. This doesn't make too much sense to me, but then this explanation here, the value of head is the offset of the beginning of the tail, and it's important to note that this is relative to the start of encoding X, and we'll see that in a second. But the head here points to the beginning of the tail, and then the tail is where the encoding of this dynamic piece of data actually is. So how can we take this and translate it and understand exactly how our sort of complex struct here is actually encoded? Well, what we can do here to make things very simple is we can actually remove all of the actual data values, and then we can see what does it look like when the struct is empty. We can see literally just the offsets. We can see just the heads and pointing to the tails and stuff like this if we just remove all of that. So what I've done here, what I've got here is an empty params object here, and what we can do is we can ABI.encode this. This will give us the call data encoding, and then I'm just going to log it, and so we'll be able to see what an empty params object here actually looks like in call data encoding. So we can run our test here, and we can see we got our call data here. So what I'll do is we will cast pretty call data, we will put this in, and then I'm just going to add 4 bytes, 1, 2, 3, 4, because we need that selector bytes there. So now we can see we have literally gone and wiped all of the data. We've cleared all the data out of this. If we go and look at it earlier, we could see we had all these values, but we still do have this 20, 1A0, and this C0 here at the bottom. So we've got 20, 1A0, and this C0. So interestingly enough, even after we cleared all the values, there's no values in this struct, we still have these here. So this indicates that these words here are actually dedicated to just pointing around, you know, here's the head of this, here's the head of this, and then each of the heads will, you know, point to the tail of the thing. And so these are sort of like the structure of this call data rather than the actual values of it. So now when we're looking at this, first of all, we'll notice that the first thing here is an OX20. Now we need to understand that this entire thing here, this entire struct, is a dynamic piece of data. This create order params, this is what we're looking at. This entire piece of data is an instance of this create order params. It's actually an empty instance of this create order params. And so that is a dynamic piece of data. What do we need? We have a head and a tail. So what does the head do? The head just points to where the tail is. So this is the head for the entire create order params tuple or struct. And what is it doing? It's pointing to the tail, and the tail is the actual encoding of that struct. So we can see this here, what I've highlighted, this is the actual encoding of the struct. And then we can see now we have inside of here, we have another piece of what looks to be pretty much a head, right? So this is another head here, and that makes sense because we can see that the very first thing in create order params is a dynamic piece of data, right? Remember, this has that dynamic address, so this is dynamic, which means that we need a head and a tail. So we take this 1A0, and of course the head is an offset from the beginning of the encoding that we're currently looking at. So this OX20 here, this is the beginning of the encoding for the create order params. So we go from OX20 and we add 1A0 to get to basically 1C0 down here. So this 1C0, this should be the start of our addresses. And so if we look, our addresses, we have a receiver, callback contract, UI fee receiver. So we have, this could be the receiver, callback contract, UI fee receiver, and then we would have the market here, and then the initial collateral token here, and then this position here is the swap path. Now remember how earlier we said, you know, this looks like an offset, but it doesn't really make sense right here as an offset, because if this was an offset from the beginning of data like we have in memory, then that would put us, you know, somewhere here. But that doesn't really make too much sense. And then of course, if it was meant to be an offset from this particular word at 260, then of course that would go beyond the call data that we even have here. But remember this one line from the docs here when we're talking about relative to the start of what we're currently encoding. So what are we currently encoding? We're currently encoding this overall struct of create order params. That's where this swap path lives in. So where did this struct encoding start? Of course, it started on 1C0. So if we have an offset of C0 from the beginning of the encoding of this struct, we add another C0. So we're going to go, right, if we take C0 and we cast to decimal, we can see that this is 192. And of course, if we want to go ahead and do 192 divided by 32 to get the number of words, then we have 6. So if we start at 1C0 and we go all of these 32 bytes, right? So there's one word. We go these 32 bytes. There's our second word. Here's our third word, fourth word, fifth word, sixth word, and then we go through the whole sixth word. That puts us right here at this byte at 280. And so here, this is our swap path. And this right here would be, of course, the length of the swap path, which we can see is 0, right? Makes sense. We just have an empty swap path. And so now, let's say we actually want to decode that actual instance of data here. So now we can go back to the transaction and we can cast pretty call data, and we can have a look at this original call data here. So now we can see all of our data is back, but we still have that same sort of scaffolding of this OX20 here, OX1A0 and then OXC0. So now we can go and understand word by word how is this data structured. So great, this is the head of the whole thing, points to this. Now this is the head to our first addresses here. And now if I leap down to 1C0, this should be the first address here. So here we go, this is the receiver, is this CB address. And if we come and look at the transaction here, this actually came from CB085, right? So this is the creator of the order. It is, pretty likely that the creator of the order set the receiver of, any outputs of this order to be themselves. So there's our receiver. And then we can see there's a callback contract and the UI fee receiver, which are both 0. In the context of the GMX v2 system, this makes sense. In most transactions, they probably won't have a callback contract or a UI fee receiver. And then we have a market here, and this is B7. We can take this, and if we go to the testnet scan and we look at B7, we can see this is a GMX market contract. And then we can see what's next. We have a initial collateral token. So this should be a token on the testnet. We take this address and we go here and we look and see what is this 1D3. Well, this is wrapped AVAX on the testnet. So our initial collateral token is wrapped AVAX. That's what we can tell from this. And then we get to the swap path and we see that, okay, yeah, we have C0. This is the head. It's pointing to the offset from this. So we go 1, 2, 3, 4, 5, 6. Start off, here we are. And then now this is empty, indicating that we have an empty array here. Okay, great. So we've just walked through and basically decoded this addresses struct. Now we can go back up. Remember, we left off at the head. Now we are sort of digging into the number struct here. And the first thing here is the size delta USD. But of course, why is there's no head and tail for this struct? That's of course because there's no dynamic data in this struct, right? We can see they're literally all uint 256s here. So if there's no dynamic data like a swap path like this, then this whole struct is a static piece of data. And we don't need a head and a tail for this particular struct. So we literally just fill in the values one by one, and we can see that our size delta USD here is some number. Let's see, cast 2 decimal. We can see it is this, and then I happen to know that these are in 30 decimals of precision for the GMX system. So if we do this and we divide by 10 to the 30th, we can see it's about $14 here. And then what we can see is the initial collateral delta amount. The initial collateral delta amount is actually 0, and this is fine for a increase order, which I'm assuming that this is. We'll actually see in a second, because a increase order actually derives what the initial collateral delta amount will be by how much was sent to the order vault. So this will be left 0 for increase orders. And then we have a trigger price, and I'm guessing that this is a market order, so that the trigger price is actually, not set, is not needed for a market order. And then we have the acceptable price here. So let's see, if we take this acceptable price and we cast 2 decimal, then we see here's our acceptable price. And I happen to know that in the GMX system, this price for a token with 18 decimals of precision, this price is going to have, of course, 12 decimals to be able to get that 18 decimals up to 30 decimals in the system. So of course, if we go ahead and divide by 10 to the 12 here, we see this is sadly the current price of wrapped AVAX. I remember when wrapped AVAX was like $70, and then we thought $70 was a really good deal. It used to be like $110 plus. But sadly, wrapped AVAX is down to about $14. And so we can see this is our acceptable price. And then it looks like then our size is about 1 wrapped AVAX, more or less. And so then after that, we can see the execution fee. So let's see, if we cast 2 decimal, we can see what the execution fee is. And this is 5. And of course, if we go into a Python shell and we divide this by 10 to the 18, we can see that this is exactly that extra amount. This is for the execution fee, right? So we saw the total value in the transaction that we sent with that send want, then that was 1.0005. So it looks like we're sending one entire wrapped AVAX. That's going to end up being our initial collateral amount, and then that 0.0005, that is our execution fee. And then we can see after that we have a callback gas limit. Of course, we don't have a callback contract, so there is no callback gas limit, and then a min output amount. And of course, there is no swap path or anything like this involved in this particular one, so there's no need for this min output amount. And then we get to this to value here, and then this of course is after we've finished with the create order params number struct. Now we move on to the order type, and we can see if we click on the order type, this is 0, 1, 2, and just as I thought, this is a market increase order. And then we can move to the next one here, and we see that the next is the decrease position swap type. This is not a decrease order, and so we're not going to be using that feature. So of course this is 0, and then we can see is long is true. So this is a market increase for a long position. And then we have should unwrap native token. This just happens to be true. And then a referral code. There is no referral code for this order. So that is it. We understand everything there is to understand in this piece of really, really complex dynamic call data. Okay, so I've actually gone and gotten the encoded bytes here from the transaction, and what we're doing now is we're decoding. We're using ABI.decode, and we can basically confirm that all of the suspicions that we had of, this is the receiver, this is the market, and things like this is actually true here, right? Look, we have no trigger price, no initial collateral delta amount. Here's the size delta USD, right? This is the acceptable price, the execution fee, all of it. We can see it all right here, and this is the decoded version of that dynamic struct. So now let's actually have a look and see what is the difference between this struct in memory versus when we have this struct in call data. And to do that, we'll go into Chisel, and then of course I'll want to bring in our structs here. So let me just copy and paste these, and then we will go up because we actually can just convert these to a uint8 and a uint8, so I don't have to get those as well. And then we can see we have our structs now up here, and then now what I can do is I can put in these bytes and decode them. So here's what I'm going to do. I'm going to put in the bytes here, so we will put that in, and then we can see what I want to do is I want to add a marker, so we know where, for example, where these bytes are in memory, where those end, and then we'll actually go ahead and decode these and then get the decoded version in memory, and then we'll be able to look at that and compare and contrast right there when we look at memory. So to add a little separator here in memory, or a little word here, what I'm going to do is we need to load in, we need to get the free memory pointer, and then of course we need to store, we want to store our separator, right? So I want our separator to just be like a bunch of F's, right? So when we see a bunch of F's like that, we know there's our separator. And then of course I need to update the actual free memory pointer, otherwise we're just going to end up overwriting our separator here, because remember, imstore does not update the free memory pointer for you. So then solidity, if you do stuff with solidity afterwards, is going to come in and is going to overwrite whatever you just wrote with mstore. So what I need to do is I want to write to 0x40, the position where the free memory pointer is, and I want to add on to whatever the free memory pointer was. So I want to add 0x20 to it. And so we'll do that. We can see here's what our function looks like so far. So we declare these bytes, and then I add this in this little separator for us. And then what we'll do is we'll decode it. So I'm going to just grab this so that we have this in memory. So now this is what it looks like. And so what we're going to look at when I look at memory here in just a second is we're going to see all of these bytes, a separator, and then we're going to see the words for this params, the same thing in memory now. So we can do MD, and cool. So we have a ton of data here, and we can see, somewhat helpfully, we have our offset here, or sorry, not our offset, our separator. So above this, we have, of course, like the free memory pointer here and stuff like that. But then, of course, right here is going to be the beginning of our the original bytes. But then below this, this is what this same struct looks like in memory. And this might be a little bit more familiar to you, is that here we have this 440. This is an offset to the first struct. Then we have 520. This is an offset to the second struct. And then we just get right into the sort of like static atomic pieces of data here. So if we go to 440 here, we can see, first of all, the first difference you'll notice is that this offset here is an offset from the beginning of data, right? It's not from the beginning of some encoding. It's from the beginning of data. So we go all the way to directly 440, and then we can see, right, this is the beginning of where our addresses was. And then if we similarly go to 520 here, we find 520. This is, of course, our size delta USD, right? This is where the start of our number struct was. And then also, noticeably, if you go to 500 here, you see this word is the offset for the swap path here. And of course, this just points to 500, which is of course 0, which indicates that the length of the swap path here is 0. So there we can see the differences between how this stuff is stored in memory and how it's stored in Calldata. And of course, the main reason for that is, of course, because Calldata is a read-only store versus memory is, of course, read and write. And so these encoding schemes are basically optimized for, each of these particular use cases. So finally, now we understand this first index here in this bytes array. Now we're ready to go back and sort of tackle this whole Calldata block here. So what I'll do is we will cast pretty Calldata, and we actually need to get out a chisel first. So cast pretty Calldata, and we'll put all of that data here, and then we'll see. So this thing is calling multi-call from a high level, and then we have all of these like offsets, right? Well, remember that a bytes array and even just an individual bytes object, right? If we go to this, the bytes, individual bytes, that's a dynamic piece of data. And then of course, an array of any type like this is also a dynamic piece of data. So with our multi-call Calldata, first of all, the entire thing is a dynamic piece of Calldata. So we have, of course, the head here, which points to the rest of everything else, the tail, which is the encoding for everything else. Then, of course, we have for each of these, then we have to understand that we have a list. And of course, when we have a list, the first thing at this OX20 word is going to be the length of the list. So we have a 2 here. This is the length of our bytes data array, right? Remember, we have, if we go here, we have just two items of bytes in this array. And then we have the head for the first item in the array, right? Remember, both of the items in this array are individually going to be dynamic pieces of Calldata or dynamic pieces of data. So this offset is from when we started to encode this current thing. So that's going to put us at OX80 here. And of course, this OX80, this is giving us the length of the bytes here. So we're getting 44. Now that includes 4 bytes for the selector and then 2 words. So here's the first word and here's the second word. And that is giving us exactly, we can see there's 3 zeros after this here. We're getting exactly 3 zeros after these bytes here. And right, there's our address and there's our amount. If we go back to where that head was, then we can see that the head for the next element was C0, right? And remember that C0 is 6 words basically. And of course, if we go 1, 2, 3, 4, 5, 6 here, then we get to where our length is going to be for this second bytes item, right? So we have 2A4. So this is of course 2A0 plus the 4 bytes here for this function selector, and that will essentially get you to the rest of this data here. And of course, we already have, trial and error sort of worked our way through this part of the bytes call data. This is of course the encoding of that massive struct that we've been looking at. So now we have fully worked through and understood every single byte here. We've looked at all of these bytes and we've worked through and we've understood everything about all of them here. So if you stuck with the video this far, then honestly, amazing job. Like, if you understand all of this, then yes, you have ventured into the advanced side of being a Solidity blockchain developer. So fantastic job. Watch this video over and over again until each part of this clicks, and let me know. Hopefully you learned something new. Hopefully you found this to be an interesting expedition into the world of call data here. All right, amazing. That was a lot of content that you just got through, seriously. So props to you for making it this far. And I recommend that honestly you go back and you watch some of the lectures again. Now, many of my students said that a lot of the stuff that we went over didn't fully click until their second or third rewatch of the recorded lecture. So this is an easy hack to get even more out of this dozen-plus hour security training. And I sincerely hope that you learned a ton from this, and I hope that you'll begin to apply it to your smart contract security reviews that you do and your research and studying that you do from now on. And of course, if you want to go a step further and actually apply this knowledge and work with me personally to take you from where you are now to a senior level auditor, then you can go down in the description below and you can get my proven formula to become a senior auditor in 6 months. All right, I look forward to seeing you in part 2.